So I wanted to start out with an introduction to the Go language itself. Now I know that this is much storied territory, but I have to start somewhere, and this is going to serve as a stepping off point for us to go through a survey of the entire Go language, as well as hitting some of the key libraries along the way. So the first thing that we need to know is that Go was created by a small team within Google, and that team was made up of Robert Griesemer, Rob Pike, and Ken Thompson. Now these guys have been around the software industry for a little while. For example, Ken designed and implemented the first Unix operating system, as well as had a key role in the development of Unicode. So when these guys got together and decided that they wanted to create a language, we had a lot of talent in the room as soon as these guys got together. But one of the questions that we need to understand is why create a new language at all? Well, to understand that, we have to look at the languages that are common inside of Google. And at the time that Go was being designed, there were really three languages that were key. The first is Python, then Java, and then C and C++. Now, each of these languages in and of itself is very powerful. However, the Go designers started to recognize that there were some limitations that Google was running into that might not be able to be fixed given the history and the designs of the existing languages. So for example, when we look at Python, Python is very easy to use, but it's an interpreted language, and so it can be a little bit difficult to run applications at Google scale that are based on Python. It can certainly happen, but that is one of the challenges that you can run into in very large Python implementations. Java is very quick, but its type system has become increasingly complex over time. Now this is a natural trend that a lot of languages go through. They start out very simple, but as additional use cases and additional features are layered into the language, it becomes increasingly more difficult to navigate things. C and C++ is quick as well, however, it suffers from a complex type system, and additionally, its compile times are notoriously slow. Now the type system has been receiving a lot of attention lately in the C and C++ communities. However, they still have the burden of needing to manage all that legacy code. And so similar to Java, it's very difficult for them to move past the history that they have because C++ applications written 10 years ago still need to compile today. And those slow compile times are another legacy issue that C and C++ have inherited as well. When C and C++ were designed, computers had nowhere near as much memory as they do today. So the decision was made to optimize the compilers to use a minimum amount of memory, and one of the compromises that brought about was the compile times can be a little bit sluggish. In addition, all three of these languages were created in a time where multi-threaded applications were extremely rare. Almost every application that was created really had to focus on a single thread at a time. So concurrency patterns built into these languages are patched in at best. And so working in highly parallel, highly concurrent applications like Google often runs into can be a little bit challenging when working in these three languages. So, enter Go. What does Go bring to the party in order to address some of these concerns? Well, the first thing that we need to understand is Go is a strong and statically typed language. So it inherits that same feature set from Java and C++. So what do we mean by strong and statically typed? Well, strong typing means that the type of a variable cannot change over time. So when you declare a variable a to hold an integer, it's always going to hold an integer. You can't put a boolean in it, you can't put a string in it. And static typing means that all of those variables have to be defined at compile time. Now, are there ways around that? Yes, Go does have features that allow you to get around its type system, but 99% of the time you're going to be living in a world that's strong and statically typed and getting all the benefits that come with that. Now, if you come from languages such as Java, then you might be a little concerned that strong and statically typed languages tend to be a little bit verbose. Well, we'll see as we get into some Go syntax how there's been a lot of effort taken to make the compiler do as much work to understand what you're talking about with the variable, so you don't have to explain to the compiler every time what your variable types and things like that are. In addition, Go, like a lot of recent languages, has a strong focus on the community that's supporting it. Just because Go is an excellent language does not guarantee success, because there are so many languages out there that it can become difficult for a new developer to ramp up on any one. As a result, there's a strong community built up around Go that's really focused on making sure that the Go language keeps moving forward and that new developers have as easy a time as possible ramping up onto the language. So what are some of the key features of the language itself? One of the first and I would argue most important features that Go has is a recognition that simplicity is a feature. So as we go through and start learning about the Go language, you're going to run into some features and you're going to ask yourself, well, why doesn't this exist? Or why don't we have that feature? And a lot of the reasons come back to this feature. there's a recognition that if the Go language recognizes simplicity is important, then that means that we're going to have to decide to leave out some other features that might be very useful but would add complexity to the language. Additionally, Go focuses on extremely fast compile times. A lot of modern development environments to write code fast, to build it fast, and to test it fast, and get feedback back to the developer as quick as possible. Well, if you've got a 45-minute compile time, it breaks that cycle, and developers have a very hard time staying in that design, build, test loop. And so Go focuses on keeping those compile times down, even though it's going to yield us fully compiled binaries at the end. Go is a garbage collected language, which means that you're not going to have to manage your own memory. Now, you can manage your own memory, but by and large, the Go runtime is going to manage that for you. And the reason for that gets back to this simplicity argument. There is a recognition that a garbage-collected language does have challenges when dealing with certain use cases. For example, real-time trading systems for stock market systems have a very hard time when you're dealing with garbage collection. However, the advantages on the developer of not having to manage their own memory all the time were deemed to be more important. Now, that doesn't mean that the delays that a garbage collector incurs haven't been paid attention to. If you go back through the history of the Go language, you'll actually see the past few versions have had a huge emphasis on reducing the amount of time that the application has to pause during a garbage collection cycle. And at this point, they're actually really, really fast, almost to the point that you don't know that a garbage collection happened. In order to address that concern of concurrency, Go does have concurrency primitives built right into the language. And we'll talk about that as we go through some of these videos. But instead of having a library that we're going to have to import in order to work with concurrency, we're going to be able to do concurrent development right there in the base language. Finally, Go compiles down to a standalone library, which means when you compile your Go application, everything is going to be bundled into that single binary that's related to the Go application itself. So the Go runtime is going to be bundled in there. Any libraries that you're depending on, they're going to be compiled in there. So you don't have to worry about reaching out to external libraries and DLLs and things like that in order to make your application work. And what that gives you is version management at runtime becomes trivial, because you simply have one binary, you deploy that binary, you run it, and all of its dependencies are there. Now keep in mind, when I say dependencies, I mean the Go dependencies. If you're going to build a web application and that has HTML resources and CSS, those have to be bundled along with the binary, but the binary itself is standalone and self-contained. Okay, the next thing that I'd like to do is show you some of the resources that are available to you as you start to explore the Go language. One of the most useful resources that you're going to be able to take advantage of as you're ramping up on Go is Go's website here at Golang.org. Now, why is it Golang.org? Well, if you take a minute to think about a language called Go, that doesn't really lend itself to unique search results in Google or Bing. So, Golang.org it is. As a matter of fact, a lot of places that you see Go mentioned, you're going to see it actually described as Golang because that makes it a little bit more unique when you're looking for search results. So the first thing that you might notice as we go into the homepage here is this isn't really laid out like a lot of traditional homepages. This, in my opinion, is very much an engineering homepage. So instead of a lot of design aesthetic, this gets right into the engineering aspects and shows you how to start working with the language. So this yellow box over here is going to be your entry point for your first Go application. So if we go ahead and click this Run button, you see that we almost instantly get an application sent back to the server, it gets compiled, and it gets run for us. So we can start playing around with Go code without installing anything on our local machines. And we're actually going to take advantage of that through this first few videos. As a matter of fact, if I make a small change here, so maybe if I say hello YouTube peoples and run that again, then I'm saying hello to you all. So hi. So it's as simple as that in order to get started with the Go program. Beside that window, we see this Download Go button, and that's going to take you to resources that you're going to be able to use in order to download the latest Go binaries, as well as download older versions of the runtime. And if there's an unpublished version, for example, at the time I'm recording this, Go 1.8 is at RC2, you can go ahead and download that, install that, and check that for bugs and play around with new features in the language. If we come across to the top, we see this Documents link here, and this is going to be another critical resource as you're starting out with the language. As a matter of fact, you're going to refer back to this page quite often. But if you really want to walk through on the website a tour of the Go language, then I would recommend you go to this Getting Started link. This is going to get you started downloading and installing the Go compilers and tools and things like that. And you can see as we navigate there, it's going to show you the different architectures that you're going to be able to use with Go, and there's quite a few, and how to get started on each one of those. If we keep continuing down, the tour of Go is kind of an introduction to the Go language that takes you through a gradual introduction. So it's going to start out with some very simple applications and then build up more and more and more and help you understand what's going on with Go concurrency and things like that. Effective Go is a very useful article, especially as you start to mature in your understanding of the language and really understand how the Go language is used. So I would encourage you to go into that. It's a pretty lengthy read, but you should consider this required reading if you're actually going to start building non-trivial Go applications. But we're not going to worry about that right now. We got plenty of ways to go before we need to get through all of this stuff. And then down here at the bottom is some reference information. This is more advanced documentation that you're probably not going to need right away. But for example, the command documentation gives you a lot of information about the Go tool itself that you're going to use for local development with Go. There's a lot of things that the Go program does, and this is going to help you understand how to navigate that. The packages link is perhaps where I spend the most time on Go's website, and this gives you documentation for all of the libraries that are built into Go. So when you install Go and you install the Go binaries and tools, you're going to get all of these libraries available to you. So just scanning down, you can see that we've got different libraries that are targeted at working with archives. We've got some cryptography libraries, database drivers. Continuing to go down, we've got some things for working with HTML and network traffic. Now, some things that you might find missing here are we don't have any GUI libraries. That's because at this point, Go really isn't focused on the use case of client application development. So Go is really targeted at building servers and web applications, and so that's where a lot of the libraries are going to be focused on. There are some projects that are working on mobile applications using Go, as well as client-side applications using Go, but they're not officially supported at this point. If we come over to the project link, we're going to find some information about history of the project, what releases have come out and when, as well as some links to mailing lists and resources that you can take advantage of if you want to keep track of the development of Go as a language, as well as if you find an issue in the Go language, you can see some information here on how to report that issue. And then we've got the help link here, and this is going to be one of your more important links as you get started here, because this is going to be your on-ramp into the community. Now, the two most active in my experience are the Go forum, which is a nice discussion forum that allows you to post your questions and get people to answer back. But if you want something a little bit more real-time, then the Go for Slack is a Slack channel specifically targeted at Go development. And there's multiple sub-channels in there for new developers, for library developers. Even a lot of the Go meetup groups have their own sub-channels on the Go for Slack. So if you want to get on the Go for Slack, then I would encourage you to come over here to another website called Golang Bridge. And this is what I consider the on-ramp to the Go community. Because Golang Bridge is specifically there to advocate for the Go language and to make sure that the community is healthy and strong. As I said, one of the key aspects of the Go language is a focus on having an excellent community. And really, it's Golang Bridge and the awesome people that support it that are making that happen. So if you scroll down a little bit, you can see some links to the online communities. If you want to join the Slack channel, you do have to receive an invite. So this link here is going to take you to the form that's going to allow you to get that invitation. And there's no problem getting the invitation. The only thing that they ask you is to read the community guidelines. There is a code of conduct that just makes sure that everybody's going to be treated respectfully in the community, just to make sure that we're all here trying to help each other out. And the last thing that I want to show you on the website is this play link here. Now this link just flies out an editor, and this is really nice because this is available throughout the site. So if I come to the packages, and let's just say I dive into the network package, and I'm learning about some network function, then I can go ahead and pop into the play. I can create a real quick proof of concept Go application in order to make sure that I understand how that's working. And again, just like we saw on that home page, if I click run, then I can go ahead and execute that. Now there are some limitations. Obviously this application is sent to the back end, and there are some limitations. You're not going to be able to read the file system of the back end, for example. But a lot of the things that you want to play around with, you can play around with in this online environment. Now another place to get at this playground is over here at play.golang.org, and this is the last thing I want to show you in this introductory video. So this is going to be the environment that we're going to focus on, and actually let me make that a little bit bigger so maybe it's a little easier for you to see. But this is going to be the environment that we're going to focus on as we start to learn the Go language. So we're going to learn the basics of a Go application here. We're going to start playing around with how we're going to work with variables and logic and looping and things like that. Now, eventually we'll get to installing a local environment, and you can certainly take advantage of the other resources on Golang's website if you want to get there before I create a video on it. But I think that there's a lot that we can talk about without making a commitment to setting up a local development environment by just going through this playground here. So if we take a second look at this application, we see some of the key aspects of any Go program. Now the first thing that you see at the top is this statement package main. Every Go application is structured into packages. So every Go file that you're going to have is going to have to declare what package it's a part of. And main is a special package because main is going to be the entry point of any one of your applications. Down below that, we have an import statement, and this is the statement that we're going to use in order to import additional libraries. So this library is called FMT, which, yeah, you actually say that in the Go community. I can't bring myself to say that, so if I call that FMT, I hope that you'll forgive me. But in the Go community, you will often hear this called FMT, and this is the package that's going to allow us to format strings. So you see down below here in our main function, which is the entry point of our application. So the main function in the main package is always going to be our application entry point. And this is going to be where we're going to contain our first code that's going to run in Go. So we're going to call into the FMT library, and we're going to pull out its println function. And that println function takes one argument, and that argument in this case is a string. So we're going to print out hello playground. Now if I go ahead and run this, then down below at the bottom of the screen here, you see hello playground gets printed out, and then it says program exited. If we have an error in the application, say if I delete this quotation mark and run, then you're going to get a compiler error printed out at the bottom that's going to help you debug your application. So this online environment is going to be very good for you to get started because it's going to help you through understanding what's going on. So for example, we see here in line 8, it got an unexpected semicolon or new line when instead it was expecting a comma or a parenthesis. And the reason for that is because this closing parenthesis actually became part of the string, so the line terminated early, and it didn't have an end to the function call. So if we go ahead and re-add the quotation mark and run, we're good to go, and we've got our first start in a Go application. So I hope that this was helpful for you. A little bit of background in a language that you're going to be learning, I always find is a little bit valuable. It helps to understand the motivations for the creation of the language and the major features in order to understand what problems that language is going to try and solve and how it's going to go about trying to solve them. What I want to show you is how to get started setting up your own local development environment to program with Go. Now I know in the last video I showed you this website here, and I said that this is what I want to use, that is the website at play.golang.org, and I said that this is the website that I want to use in order to show you a lot of the concepts that you're going to need to be familiar with the Go language. And that's still my plan, but as I thought about it, I decided that it doesn't really make sense to force you to use the playground just because it's a really good place for me to demonstrate concepts. So I want you to have all the tools available to you to set up your own local Go development environment so you can play around with creating your own applications as you learn about this wonderful language. So the first thing that we're going to need to do is we're going to need to download and install the Go language and the Go tools itself. And so in order to get started with that, we're going to start over here at golang.org, and we're going to click on this download Go link here. Now this link is going to take you to all sorts of different versions of Go. But in general, if you're getting started, just pick the latest stable version that's available for you, and it's not going to steer you wrong. Now, if you're a Windows user, then I would encourage you to click this MSI link. It's going to download an installer, and Go is going to be put on your system automatically. However, if you're using OS X or Linux, then I would recommend that you go to this installation instructions link here and follow the instructions here. Now, you're still going to need to download the Go binaries, but if you scroll down just a little bit, you're going to see this command here, and this is going to give you the tar command that you're going to need to use in order to unpack the Go binary and install it onto your system. So I've already done that, and I can show you that by opening up a terminal here, and the default location to put Go is in the user directory underneath local, and then in a folder called Go. So if we look at there, and I look at the contents there, I see that I have all the Go tools installed. So with the Windows installer, all it's going to do is it's going to place these into C:\Go, and I would strongly encourage you, if you can accept these default locations, that you go ahead and do that, because it's going to make setting up your environment just a little bit simpler. Now after we get Go installed, we have a little bit of configuration in our environment in order to be able to use Go effectively. So I'm going to come back to my home directory here, and I'm going to make a change to my bash rc file. Now I'm on Ubuntu, so it's going to be in my bash rc file. If you're in OS X, it's going to be your bash profile. If you're on Windows, basically what we're doing is we're setting environment variables. So if I open that up and come down to the bottom, then I see that I've got the pre-generated bash script. I'm not going to really worry about that, but there's a couple of variables that we're going to need to set. Hello everybody, I need to pause the video here for a second and make an important announcement. So as soon as I originally released this video, Dave Cheney came in within a couple of minutes and he expressed a concern about one of the things that I'm about to talk about. Now I'm about to talk about setting a couple of environment variables here and showing you how they work. Now one of those variables is called GoRoot. And setting GoRoot has been shown to cause problems as you move through different versions of Go, especially if you've got multiple versions of the language on your system. So, if you want more information about that, Dave has a really good blog post here that you can go to learn more information about it. But for now, please keep in mind, if you're able to install Go at its default locations, which on Unix or Mac is going to be /user/local/go, and on Windows is going to be C:\\go. If you're able to do that, please do that and then go ahead and avoid setting GoRoot. Now you will need to set the path variable to GoRoot's bin directory in order to access the Go executable, and you will need to set GoPath, which we're going to talk about after that. But if you can avoid setting the GoRoot environment variable, it's going to save you a lot of heartache. So while I'm going to show you how to do that, in case you do need to set it, please avoid that if at all possible. Okay? At this point, I'm going to resume the video and continue talking about the environment setup. Now the first variable that you're going to need to know about is called GoRoot. Now if you've installed Go to its default location, you're not going to need to worry about this. But if you decided to install Go somewhere else, for example, maybe you've installed it in your home directory, then you can go ahead and set GoRoot, and that'll tell the environment where to go to find the Go binaries. Now the next thing that we want to do is we actually want to set a path variable to the Go binaries themselves. So I'm going to go ahead and export a path variable. And that'll of course start with my existing path, and then I'm going to add on to that GoRoot, and then I'm going to whack on the path /bin. So there's quite a few binaries that you're going to be using on a regular basis, and those are in GoRoot /bin. So you're going to want to make sure that that's part of your path. Now once I do that, let me go ahead and save this, and then I will use the source command in order to get my shell to reread the bashrc file. And then I should be able to test to make sure Go is available by typing Go and version. And you can see here I'm running Go version 1.8, release candidate 3. Okay, now there's one more thing that we need to do in order to get our environment fully set up. And I'm going to go back into my bashrc file in order to do that. And that is the setting of a second environment variable. So we have GoRoot, and that's going to tell the environment where Go is installed. But we're also going to be downloading a lot of packages as we work with Go, because we're going to be taking advantage of libraries that other people have published in order to build our own applications out. So those applications, as well as our own source code, are not going to be located with the Go binaries. They're going to be located in a path that we're going to specify with another variable called GoPath. Now GoPath is either one of the most awesome or one of the most horrible things about Go, because it gives you this really nice way to specify where your Go projects are located. However, it does kind of push you towards having this monolithic repository of all these binaries and your applications tied together. So I'll show you a little bit of a hint on how to work with that. But for now, let's go ahead and set a GoPath variable in my home directory, and then I will call this golib. Now just like with GoRoot, we might have some executable binaries that are going to be stored in our GoPath. So I'm going to go ahead and export on our path again, and we'll start with our existing path, and then I want to add on GoPath /bin. That way, if we install any libraries that have executables, and we will be installing libraries that have executables, then we're going to be able to track that. Now, just to show you real quick what that's going to do, let me go ahead and save this out, resource my bashrc file, and then I've actually already created this folder here called golib. Now, if I go into golib and I look at the contents of that, it's currently empty. But I can change that by using a tool called goget. So if I get a library that's at github.com/nsf/gocode. This is historically the library that people use to provide autocomplete functionality in their Go applications. So if I go ahead and hit enter, and wait a second, then go back into my golib folder and look, now I've got some contents here. So if I look in the bin directory, I've got this Go code executable, and if I come back to the source directory, then I see that I've got this github.com folder, and inside of that is NSF, and inside of that is Go code. So if I come in here, here's all of the source code for the Go code library. So when I'm working with Go code, it actually downloads the source code and compiles it into the Go code library for me, and that's what that GoPath is going to do for you. The problem that you might run into is that this use of GoPath tends to drive towards monolithic repositories. So you're going to have Go code, you're going to have your own code, you're going to have all sorts of other libraries, all put into this one location. Now, when I create my courses, that creates a lot of visual clutter, and so that isn't exactly the form of GoPath that I use. what I do is, coming back into my bashrc file, is I actually use a capability of GoPath to create a compound GoPath. So instead of a single path here, I'm actually going to re-export GoPath, and I'm going to add on an additional path to this. And I'm going to add home, mic, and code. Now, a lot of times when I'm teaching courses, I only need 2 GoPaths, and so I've got golib, and that's going to be where all my third-party libraries go, and then I'm going to have another folder that's going to be what's called my workspace location. So let's go ahead and write this out. We'll source this again, and now I've got the full GoPath. So if I come into my golib, and I remove everything from it, now it's empty again. So if I go ahead and go get that repository again at github.com/nsf/gocode, and now you see that it actually goes into my golib folder. If I come into my code folder, which I also created earlier, that's still empty. So the first segment of your GoPath is going to be used by GoGet in order to store your files, but all of the segments of your GoPath are going to be searched for source code. So that's going to really help us as we're setting up our workspace. So speaking of which, that's the next thing that I want to do. So a workspace in Go isn't anything special. The only thing that you need in order to create a workspace is to have a single directory called src in it. So if I add a directory called src into my code folder, then I've got a Go workspace. Now src, as you might expect, is where you're going to keep your source code. So when I set GoPath to /home/mic/code, it's going to look for an src directory in order to find my source code. Now there are 2 other directories that you might find in a workspace that are interesting. Now we found one already when we installed that GoCode library, and that's bin. So anytime we're working with a project and a binary is created, it's going to be put into that bin directory. And that's also why we added that bin segment to our path. The last directory that you might find in your workspace is a pkg directory. So if we're compiling something and it's going to generate an intermediate binary, which means it's not going to be a fully compiled application, it's going to be an intermediate step. So for example, if we're taking a third-party library and we're integrating that into our application, then the pkg directory is where those intermediate binaries are going to be stored. And the reason those are created is so that they don't have to be recompiled every time. So when you compile your Go application, Go is going to check to see if any of the source files in that directory have changed since the last time it compiled them. If it hasn't, then it's not going to recompile that package. It's just going to go ahead and link them into the binary that it's creating for you. Okay, so let's go ahead and clear this out, because that's getting a little bit cluttered. And now let's set up an editor to work with GoCode. Now there's a lot of editors that are out there, and so what I'm going to show you is just one, but feel free to explore the options for your favorite editor, because there's probably a Go plugin for it, and all of these plugins are really good right now. So I'm going to show you the one that I've been using lately, which is Visual Studio Code. Now it might be a little bit surprising. Microsoft, oh my goodness, they're doing all this really awesome stuff for the open source community, but it's really true. One of the best development experiences that you're likely to come across with Go is in this Microsoft product running on Linux. So I've already installed it, but if you do need to install it, you can come here to code.visualstudio.com. It's going to give you the binaries. In this case, I'm running Ubuntu, so I would download this .deb file and install that onto my system. And then I'm going to be able to run that by simply typing code in my application launcher, or I've already set up a shortcut over here in my taskbar. So as soon as I run that, I'm going to be presented with this. Now you can see I've already opened up a folder here. You can open up a folder to your workspace by simply file open and then pick your folder that you want to be working with. So we're going to be working with code. But there is one setup step that I need to go through before Visual Studio Code is quite ready to go. And that is, I need to install the plugin that's going to allow it to work with GoCode. So if I click this button down here called Extensions, then I have a list of all sorts of extensions that I could add in for Visual Studio Code. Now right here is the Go extension by Luke Hoban. Now there's a couple of Go extensions, but I would strongly recommend you use this one here by Luke, because it is really amazing. It offers a lot of capability and really makes Visual Studio Code a first-class environment for developing Go. Okay, and as fast as that's been installed, and it was that fast because it's been cached from earlier, and then I'm all set and ready to build my first Go application. So let me go ahead into this source directory, and I'm going to create a folder that's going to contain my source code. Now your first temptation might be to just plug in your source code right here in your src folder, but I wouldn't recommend that. The standard structure that you're going to use in a Go application is to mirror where your application is going to be in source control, and that makes it Go gettable. So in this case, if I was going to keep this file in GitHub, I would create a folder called github.com, and then underneath that, my GitHub account is VANSIMKE. Don't ask, long story about why I called it that. And then I would have an application name. So I would call this maybe first app. And that's the folder that I'm going to store my application in. And the reason for that is if you think about if I check this into GitHub in a repository called first app, when I go get that, it's going to recreate this structure. And so you want to create your applications following that structure. So now I'm ready to create my first file, and I will call that main.go. And then I can start adding in my source code. So the first thing that I'm going to add is package main. And then when I save this, it looks like I expected something to happen here and it's not happening. I think it's because, it told me that I needed to reload the environment. So I'm going to go ahead and do that. So I'm going to exit out of Visual Studio Code and it should kick right back off, but it has to initialize the plugin. So now I see what I was expecting to see. And that is that the Go plugin has recognized that I don't have all the tools that it needs in order to provide me all the support that it can. Because the Go plugin for Visual Studio Code is actually like a lot of the plugins in other languages. It takes advantage of these language services. For example, it's talking to me about GoLint. GoLint isn't available on my system, and so it's not going to be able to provide linting capabilities. So basically, the Go plugin calls out to all these language services. The nice thing about that is if you decide to flip between different editors, your experience is pretty much the same because they're all relying on these same language services in order to provide you the capabilities that you have. So let me go ahead and install all. And you can see there's a pretty long list of libraries that it's installing for me. Okay, and now they're all installed. So that took about a minute to install all those dependencies. So I expect that you'd probably have a similar experience in your own environment. Now before we start adding anything else, I actually put some quotation marks around this package, so that's not going to be correct. And now I'm ready to start actually building out my program. So let me go ahead and put in an import statement here. And we haven't talked too much about imports, but we have mentioned a little bit about packages. Packages are how code is organized into sublibraries inside of Go. So for example, if I want to build a web application, then I might pull in the net HTTP package that you see here in order to set up my web request handlers. But for now, I just want to do a simple hello Go example, and so I'm just going to import the FMT package. But you notice that the Go plugin for Visual Studio Code gives me autocomplete. So any library that's available on my Go path is going to be found here. So now I'm going to create a simple function called main, and inside of that I'm going to access the FMT package, and notice that I get autocomplete functionality here. So I can go ahead and say I want to call the println function, and it gives me the signature for that function. So I can go ahead and add that in here, and then I just want to say hello Go. Okay. So in order to run this inside of Visual Studio Code, you do have the ability by pressing Control backtick. You can open up a terminal right here inside of the editor. And there's a couple of different options that I have in order to run my application. So the first thing that I can do is I can use Go's run command, as you see here, and I can give it the path all the way through to my source code. So if I come and I just keep tabbing through, then I'm going to get source/github.com/vansimke/firstapp/main.go. So if I run that, then it'll compile that temporarily and run that for me. And it'll also compile in any third-party libraries, so the FMT package was compiled in as well. Now that's a really good way to get a really quick run. Another way that you have available to you is to use Go build, and Go build takes the actual package path. So all we're going to do here is compile the first app package. Now, if it finds a main package with a main function, then it's going to compile that as an executable, like you see right here in my home directory, so I can go ahead and run that. Now, the last build tool that I have available is Go install. Go install is actually expecting to be pointed to a package that has an entry point, and it's going to install that into your bin folder. So let's go ahead and see that work. So we'll go to github.com. my username for GitHub, and then first app again. So notice I'm using the package address. I'm not using the folder path. If I run that, notice I don't get anything in my main directory, but if I come into this bin folder here, now I've got first app over here. So if I come back to my terminal, bin/first app, run that, I get hello Go printed out again. Okay, so the last thing that I want to show you, if I come back over to the terminal, so you see how we have all the packages that we're working with locally over here in this code directory. If I come to the first element of my Go path, which is golib, and look at that, you'll see that this has started to become a pretty busy place here, because now I've got 3 source folders, and if I come into github.com, you'll see that I've got quite a few packages. So now all of these third-party dependencies aren't cluttering up my main workspace. They're all in this golib folder, and then I can focus on my development in my code folder. Now the last place that you're going to see packages is over in the Go installation directory. So if I look in that folder, you see here that I have this directory called source. So the Go source code itself is in fact a valid Go workspace. So if I come in here, look at the folders in here, you see these are exactly the Go standard library. So here's FMT here. You see if I scroll down a little bit, the net package, if I go into the net package, you'll see that that contains the HTTP package. If I come into the HTTP package and list those contents, you see all of the source codes for all of the modules that you can see over here at golang.com. So if I follow that through over here, scroll down to net and HTTP, you see all of the capabilities that are available in here. Well, all of those are provided by this source code here. So if you have any questions about how any one of those libraries work or how something's configured, you can jump right into the source code and see how it's all put together. Over the last couple of videos, we've laid some foundation by talking about the history and the features of Go and working through setting up the local development environment. Well, today's the day that we're going to start a discussion about the Go language itself by discussing how to work with variables. So in order to fully cover how to work with variables, there's several topics that we're going to need to cover. We're going to start by learning how to declare variables. Then we'll move into a discussion about how Go considers redeclaration of variables and this concept of shadowing. After that, we'll talk about visibility, where we're going to learn how we can control what aspects of our program can see a variable that we create. Then we'll talk about naming conventions. And finally, we'll wrap up with a brief discussion about how to convert variables from one type to another. Okay, so let's go ahead and get started. So I'm going to be using the playground in order to host our conversation. That way you can follow along whether you've set up a local development environment or just want to follow along online. So as you can see, when we first load up the playground, we've got this one statement program, which is just printing out the string hello playground to the bottom of the screen when I click this run button here. Now this statement can only ever do one thing because we're passing in a string literal. And similarly, if I pass in the number, say 42, and run it, then we print 42 out. Now, no matter what we send to this println function, it's only going to ever do that one thing. So in order to provide a little bit more flexibility to our application, we're going to introduce variables. So there's actually 3 different ways to declare variables in Go, and we're going to go through each one of those, and then we'll talk a little bit about where you might use each format. So the first thing that we can do is actually declare the variable itself, and that'll be done using this kind of a statement. So we're going to start with the var keyword, then we're going to have the name of the variable and the type of the variable. Now if you come from another strongly typed language, this might look a little bit backwards, because you might be expecting to see something like int I. Well, that's not actually how Go works. And if you think about it, the way Go structures things actually looks more like how you read it. So I'm going to declare a variable called I that's going to be of type integer. So the way you declare variables in Go is pretty much the same way that you speak. And so it might look a little bit odd when you first start working with it, but it very quickly becomes intuitive. Now that we have our variable declared, we can go ahead and assign a value to it. And we'll do that simply with the equals operator. So once we have that set, we can go ahead and replace this with an I, run it, and we print the value 42 out. And since variables in Go can vary, we can go ahead and change the value of that to say 27. When we run again, we get the value 27 printed out. So now, even though the statement can only ever do one thing at a time, the program that runs up above this format statement can actually influence the value that's printed out to the console. Okay, so let's go ahead and get rid of this, and then explore another way to initialize this variable. Because one of the things that we're trying to do in Go is we want to keep things simple, so if we need multiple lines, then we'll go ahead and do that, but we don't want anything to be more verbose than we have to. So we can actually combine these 2 lines into one like this. So we can initialize the variable I as an integer and assign the value 42 in the same line. So if we go ahead and run this, then no big surprise, we get the value 42 printed out. Now this is actually still making us work a little bit harder than we need to, because since we're assigning the value 42 to this, the Go compiler can actually figure out what data type I needs to have. So we can go ahead and tell it to figure this out for us by replacing all this text with this text here. So if we just say I, and then use this :equal operator and the value 42, and run this, then we get this really nice, concise way of setting things up. Now, where are you going to need each one of these? Well, let me go ahead and add them back in so we can talk about them. So we'll set var I integer, I equals 42, and then we'll use var j integer equals 27, and then we'll set up k, and that's going to be equal to 99. So we have these three different formats. So when are you going to want to use each one of these? Well, the nice thing about this first format is there are going to be times when you want to declare a variable, but you're not ready to initialize it yet. So for example, if you want to declare a variable in the scope of this main function, and then you have a loop or something like that that sets up a local variable scope, and that's where the variable is actually going to be assigned, then you can go ahead and use this first syntax. The second syntax is valuable if Go doesn't have enough information to actually assign the type that you really want assigned to it. So to show that, let me go ahead and add another print statement here. And I'm going to need to comment these other lines out in order to make things happy for us. So let me go ahead and change this println to a printf. And what this is going to do is it's going to allow us to provide a formatting string and print things out that way. So I will print out the value, and then I'll print out the type of the variable. And then I'll pass in j twice. So if I run this, then we get the value 27, and no big surprise, it's an integer. But what if we want this to be, for example, a floating point number? Well, with this syntax, it's as simple as just changing this to float 32. When we run this, then Go understands that we want to use 27 as a floating point number. Now, if we try that with k down here, so let me uncomment the k, switch this over to use k, and run, then you see that the number 99 is inferred to be of type integer. Now we can influence that a little bit by adding a decimal point, and that's going to give a hint to making that a float 64, but there's no way to use this colon equals syntax to initialize a float 32, for example. Go is either going to decide it's an integer type or it's a float 64 type. So if you need a little bit more control, then the second declaration syntax is going to be valuable for you. Now the next thing that I want to show you is how we can declare variables. Now we've been declaring variables one at a time and inside of a function. Well, another way that you can declare variables is up here at the package level. Now when you're doing it at the package level, you cannot use this colon equals syntax. You actually have to use the full declaration syntax. So we can declare variable I as an integer, set it equal to 42. So that works. Come down, wipe out this code, and then replace this with I. And you see that we have the value 42, and it's of type integer. So just like we have before, we can go ahead and tell it to declare that as a float 32. And the compiler recognizes, well, I can make 42 a floating point number. That's not going to be a problem at all. Now, of course, if you try something like this, the compiler has no idea how to convert the string foo to a floating point number, and so it's going to fail on you. Another thing that we can do at the package level is we can actually create a block of variables that are declared together. And to show you why that's valuable, let me just drop in some variables that we can play around with. Okay, so as you can see, I've got a little bit of Doctor Who on the brain here, and say I'm writing a program that's going to print out some information about the Doctor's companions. So here we've got a variable actor name that's going to be Elizabeth Sladen, then we got her companion name, which doctor she worked with, and what season she was on. So by declaring these variables like this, things are actually a little bit cluttered, because again, we want things in Go to be as clear and concise as possible. So all these var keywords are actually cluttering things up a little bit. So what we can do instead of this is actually wrap this whole section with a var block, and then we can actually get rid of the use of this var keyword. And now all of these variables are going to be declared because they're inside of this var block, and we can actually show that they're related somehow. Now they don't have to be related, that's a design decision, but we can do that. So if we had another set of variables that were related to a different context, so say for example we had a counter, and that was going to be an integer initialized to 0, then we can have multiple variable blocks at the package level. And that's just going to allow you to organize your application a little better and keep your code a little bit cleaner. Now the next thing that I want to show you, and let me just drop in some code here, is how variables work when you're trying to redeclare them. So as you can see in this application, we're declaring the variable I up here in the package scope, then I'm declaring it here inside of the main function, and then I'm redeclaring it here on line 11. Now if I try and run this, I'm actually going to get an error. And the error comes on line 11 here because there's no new variables here. So I can reassign the value of I, 13, but I can't declare a new variable here. And that's because the variable is already declared on line 10, and you can't declare the variable twice in the same scope. However, if I get rid of this line, notice that the application runs just fine and uses the value 42. So even though I is declared twice in my application, once at the package level and once inside of the main function, that's okay. And what happens is that the variable with the innermost scope actually takes precedence. So this is called shadowing. So the package level I is still available, but it's being hidden by the declaration in the main function. And I can actually show that by copying this line up here and running this. And now you see I get 27, which is the package level scope. Then I create the shadowing variable, set it equal to 42, and when I print out I again, then I get the new value of I. Now another interesting thing about variables in Go is that they always have to be used. So let me just drop in this example here, and let's walk through it. So I'm declaring a variable I, setting it equal to 42, then I'm instantiating a variable j, setting it equal to 13, but I'm only using I. So what happens when I run this? Well, if I do, I actually get yelled at, because j is declared and not used. And this is one of the things that's going to keep your Go applications nice and clean. If you have a local variable that's declared and not used, then that's actually a compile time error. And the reason that's really valuable is as your application grows and evolves and new features are added and old features are deprecated, you're very likely to end up with some old code hanging around inside of your functions. Well, if any of your old code are variables and those variables are no longer used, then the compiler is going to detect that for you so that you can make sure that you can clean those out. Now, another important thing to know about when you're working with variables is how to name them. And there's actually two sets of rules that you're going to need to keep track of. One is how naming controls visibility of a variable in Go, and the other is the naming conventions themselves. So notice that I've been creating lowercase variables. Well, that actually isn't always the case in Go, because if I'm declaring a variable, and let's just declare it at the package level, and I declare it as an integer with the name I, and I go ahead and work with that, then that lowercase variable name actually means that this variable is scoped to this package. Now this is a main package, and so this doesn't really matter so much, but when we get into working with packages, this becomes extremely important. So lowercase variables are scoped to the package, which means anything that consumes the package can't see it and can't work with it. But if I switch to an uppercase letter, then that's what's going to trigger the Go compiler to expose this variable to the outside world. So it's a very simple naming convention, and there's really only 3 levels of visibility for variables in Go. If you have it at the package level and it's lowercase, it's scoped to the package, so any file in the same package can access that variable. If it's uppercase at the package level, then it's exported from the package and it's globally visible. And the third scope is block scope. So when we have this main function here, it's actually establishing a block scope. So when we declare this variable I right here on line 10, that variable is scoped to the block. And so that's never visible outside of the block itself. Now beyond that, it's important to understand the naming conventions in Go. And there's a couple rules that we need to follow. The first is that the length of the variable name should reflect the life of the variable. So for example, in this example, we're declaring a variable I and we're using it right away. So having a very simple variable name is perfectly acceptable. And this is going to be especially true if you're declaring counters and for loops and things like that. It's very common to have single letter or very, very concise variable names because the lifespan of that variable is very small and the amount of time that you have to keep the meaning of that variable in your head is very small as well. However, if you're declaring a variable that's used for a very long time, then it's best practice to use a longer name. So for example, if this was going to represent the season number that our companion was on, so say season 11, and we use that throughout this entire main function, then we'd want to use a name something like season number. Now, if you're working with a package level variable, and that package level variable is going to be used in quite a few other places, then that's where you're going to want to use the most verbose variable name. Now, you still shouldn't get crazy. You shouldn't have 50 character long variable names if you can avoid it. So keep your names as short as you can, but make sure that the names of those exported or package level variables are clear enough so that somebody who's outside of that source file understands the meaning of it. The other thing I'd like to talk about is how to work with acronyms, because in other languages you might see variables like the URL, and then maybe this is http google.com. You might see variables named like this. Well, the best practice in Go is actually to keep these acronyms as all uppercase. So if you're working with a variable called the URL, then URL should be all uppercase. Similarly, HTTP and any variables like that. So anytime you see an acronym, make sure that that's all uppercase. And the reason is for readability. It's very clear. We're used to seeing URL and HTTP all put together. So when you read this variable, it's very clear that you're talking about an HTTP. Maybe you're talking about an HTTP request. That reads a little bit cleaner than if you go ahead and make those lowercase. So just some rules to keep in mind as you're creating variables. Now the next example that I want to show you is how we can actually convert from one variable type to another. So notice that I have two variables here. I've got the variable I on line 8 that I'm declaring as an integer with the value 42. And then I've got this variable j that's going to be a floating point number. Now what I want to do is I want to actually treat I as a floating point number and assign that value to j. So the way that I do that is using this conversion operator. So if you look on line 12, it looks like float is being used as a function, and in fact it is. And this is a conversion function. So when I run this program, you see that the first print statement on line 9 prints 42 as an integer. The second print statement still prints the same value, 42, but now it's been coerced into being a floating point number. Now you have to be a little careful with this, because if you go the other way, so for example, if we go from a float 32 to an integer, and then I convert that and run it, it looks like everything's okay. But keep in mind, a floating point number can have a decimal on it. So now I've actually lost information through the conversion. So the important thing about this is I have to explicitly convert, because if I just tried to do this, then I'm actually going to get a compile time error, because Go is not going to risk the possibility of losing information through that conversion. So you have to do an explicit conversion when you're changing types. That way it's your responsibility to understand if you're losing information or not. Now the other thing that's important to know is if I decide to work with strings, it's a very common use case to try and convert an integer into a string. Say for example you want to print it out to a log file. Well, if I run this, I get a pretty odd result. The first line prints out okay, 42, and that's an integer, that's okay. But then I get an asterisk that's of type string. What the heck happened there? Well, in order to understand that, you have to understand how strings work with Go. A string is just an alias for a stream of bytes. So what happens when we ask the application to convert the number 42 into a string is it looks for what Unicode character is set at the value 42, and that happens to be an asterisk. So if you want to convert back and forth between strings and numbers, then you're actually going to need to pull in the string conversion package, which you can find on Golang under packages. If you scroll down a little bit, you see string conversion here, and this is going to expose all sorts of functions that are going to make it a lot easier to convert back and forth between strings and other data types. So in this case, what we'd want to do is use the string conversion package's I to a function, which converts an integer, that's the I, to, that's the 2, and then to an ASCII string. So if we go ahead and run that, now you see that it properly converts the integer 42 into the string 42 and prints it out for us. So if you need to work with converting between numbers and strings, then go ahead and use that string conversion package. But if you're converting between numeric types, just keep in mind you can't implicitly do that conversion. You have to explicitly do it. And if you need to do that, then you can go ahead and use the type as a function. Okay, so we just covered quite a bit of ground. So let's go through a summary of what we've talked about throughout this video. Okay, there's quite a few things to keep in mind as we're working with variables, so let's go through and review what we talked about. The first thing that we talked about is the 3 different ways to declare variables. So we saw that we could declare a variable and then initialize it later. We saw that we can declare it and initialize it at the same time. And then we also saw that we can use this : syntax as a shorthand version of declaring and initializing a variable, and then we let the compiler decide what type to assign to that. Now normally you're going to use this third version. The only time you're really going to use the second version is when the compiler is going to guess wrong. And then the first version is sometimes useful if you need to declare the variable in a different scope than you're actually going to initialize it. We then talked about how we can't redeclare a variable, so within the same scope, we can't initialize that variable twice, but we can continue to reassign values to it, but we can shadow them. So if we declare a variable in a package scope, for example, we can redeclare that in a function scope, and that's going to shadow the variable at the higher level scope. All variables must be used in a Go application. So if you declare a local variable and that variable isn't used in the scope that it's declared or one of its inner scopes, then that's going to trigger a compiler error and you're going to have to go back and clean that up before your application is going to run. And again, the reason that that's really nice is as code evolves and it continues to be refactored and improved over time and features get retired, you don't have all these old variables hanging around and requiring allocations of memory when they're not being used for anything anymore. We also talked about the visibility rules. The first thing that you need to know is when you're working with package level variables, a lowercase first letter means that it's scoped to the package, which means all of the source files that are in the same package have access to that variable. If you have an uppercase first letter, then it's going to be exported globally, and so anything can work with that variable at that point. There is no private scope, so you can't scope a variable to the source code itself. However, you can scope a variable to a block by declaring it within the block instead of declaring it at the package level. We also talked about the naming conventions, and there are really two naming conventions that are used. Pascal case, which basically means you uppercase the first letter, and camel case. So when you're naming variables, you don't want to separate the words in the variables with underscores. You don't want to have them all in lowercase. You don't want to do anything like that. Just use standard Pascal or camel casing rules. The only exception to that is if you're working with acronyms, all of the letters in the acronym should be uppercase. The names of the variables should be as short as you reasonably can get them. So if you've got a very short lifespan of the variable, say for example a counter in a for loop, then having a one-letter variable name is perfectly acceptable. However, if you've got a variable that's got a longer lifespan, say for example it's used in a fairly long function, or if it's exported from the package, then having a longer, more descriptive variable name is certainly something that you should consider. However, please don't go crazy. Keep those names as brief and concise as possible. And the last thing we talked about are the type conversions, and how these work a little bit differently than other languages. In a lot of other languages, you would have to put the type in parens and then what you want to convert. In Go, it acts more like a function. If we want to convert an integer to a floating point 32 number, then we use float32 as a function and we pass the integer into it, and it's going to do the type conversion for us. We also learned that Go does not do implicit type conversion. So if you try and take a floating point number and assign it to an integer, Go's going to throw a compile time error for that, and that's because of the possibility of losing information through that conversion. So every time you're going to do a type conversion that might lose information, you're going to have to do that yourself so that you're making the decision, and then you can write whatever tests are required in order to make sure that information isn't lost. The final thing that we learn is when we're working with strings, then type conversions can start to get a little bit weird. So in order to handle the conversion between integers and strings and other data types and strings, we can use that string conversion package that offers a series of functions that make sure that the conversions happen the way that we expect them to. In today's video, what I want to do is introduce the primitive types that we have available in the Go language. Now, we're not going to be talking about every basic type that you can create. There are certainly collections and some more complicated types, and we'll introduce those a little bit later. Today, I want to focus on three categories of information that we can store in Go. We'll start by talking about the Boolean type, then we'll move on to the numeric types, and in that category we have integers, floating point numbers, and complex numbers, and then we'll move on to the text types. Okay, so a fairly simple agenda, but we've got a lot to cover. So let's go ahead and get started by talking about how we can work with Boolean data in Go. Boolean data is probably the simplest type of data that we can work with in Go, and it represents two states. You either have true or you have false. So in order to show you a simple example of working with Boolean variables, we can create a variable here and make it of type bool. So that's the data type that you're going to use when you're declaring a Boolean, and we can set it equal to a value. So for example, we can set it equal to true. And then we can go ahead and print out, using our fancy printf statement here, we can print out the value and type of this Boolean. And if we run that, we see that the Boolean true is in fact got the value true, and its data type is Boolean. So we can also initialize this to false and run that, and now we see false is also a Boolean. Now there's a couple of uses for Boolean variables in our applications. Perhaps one of the most common is to use them as state flags. So for example, say you're creating an application and you want to store whether a user is signed up for notifications when a report is generated. Well, you can use a Boolean variable in order to store true if they want that report or false if they don't. The other case, and perhaps the more common case for using Booleans in Go, is as a result of logical tests. Now we're not ready to talk about logical tests quite yet, but I can show you how Booleans are used in those tests. So if we create a simple variable here, and we use the equals operator to test if 1 equals 1, and then create another variable, and then I want to test if 1 equals 2. Now, the double equals operator is called the equals operator, and that's basically checking to see if the item on the left is equivalent to the item on the right. So 1 obviously equals the number 1, and 1 just as obviously doesn't equal the number 2. So if we print out the value of those using these two printf statements, then we see that a Boolean is actually generated as a result of this equivalency test. Now, when we get into talking about logical tests, we'll see that there are actually quite a few other logical tests that we can use, but this is a very common use case that we have. So we see, looks like I need to add a new line operator here. We see that the first operation does in fact generate the Boolean true, and the second operation generates the Boolean false. Now, the other thing that's important to know about the primitives is that every time you initialize a variable in Go, it actually has a 0 value. So we are assigning the value of n and m in this example here, but what happens if I just do this and print out the value of that? Well, in some languages, that would be uninitialized memory, and we would have no control over what printed out. When Go, every time you initialize a variable, it has a 0 value, and the 0 value for Boolean is the value false. So you don't have to worry about initializing variables every time. If the 0 value is acceptable to you, you can certainly leave it like that. So Booleans are pretty simple. The next type that I want to get into are the numeric types. And these are a little bit more complicated. Because of all of the different types of numbers that we can work with in our applications, Go has a rich array of numeric types to choose from. Now, the first thing that we need to know about is the 0 value. And the 0 value for all numeric types is going to be 0, or the equivalent of 0 for that numeric type. So let's start talking about the integer types. So the first type of integers that we can work with are the signed integers. And those have several different data types. So we have the general int, which is an integer of unspecified size. And I say unspecified because every platform can choose to implement int as a different size. Now, the one thing that you're guaranteed is regardless of your environment, an int will be at least 32 bits, but it could be 64 or even 128 bits, depending on the system that you're running on. And this is going to be the default integer type. So if we do something like n equals 42, and then we print out the type of n, then you see that we get the value 42, and it's of type integer. Now, there are other types. So we can have 8-bit integers, which can range from negative 128 to 127. We can have 16-bit integers, which can go from negative 32,768 up to 32,767. Then 32-bit integers, which can go from approximately negative to positive 2 billion. And then if you need a really big number, you can go with 64-bit integers, and those go somewhere between plus and minus 9 quintillion. So if you need bigger numbers than that, then you've got a very large application that you're working with. And in that case, you're going to need to look into the big package from the math library, which can handle arbitrarily large numbers. So you can't get a number big enough for the big package to not be able to handle. Although, working with numbers that large, you're going to take a bit of a performance hit, and the numbers aren't going to be quite as easy to work with as using the primitive types that we're talking about here. Now, related to the signed integers are the unsigned integers. So we have the value 42 here, and just so you can see, we can create an unsigned integer, and I'll just pick a uint 16 and assign that the value of 42, and then let's go ahead and run that. And you see that now we have a uint 16. So there's an equivalent type of unsigned integer for every signed integer. We have uint 8, which is an unsigned 8-bit integer, which can go from 0 to 255. We have a 16-bit unsigned integer and a 32-bit unsigned integer. Now, what we don't have is we don't have a 64-bit unsigned integer, but we do have a type byte. And a byte is an alias for an 8-bit unsigned integer. And the reason we have that is because the unsigned 8-bit integer is very common, because that's what a lot of data streams are used to encode their data. Now, with these integer types, and again, unsigned and signed integers are basically the same type, we've got several different arithmetic operations that we can do. And these are built into the language. So if I just drop in this example here, you see that we've got an integer a set equal to 10, we've got another integer b set equal to 3, and we're doing the basic arithmetic operations that are available to us. So we can add, we can subtract, we can multiply, we can divide, and then this percent sign here is actually used for the remainder. So if I run this, you see that we get 10 plus 3 is 13, 10 minus 3 is 7, and so on. So we get the numbers that we expect. Now, the one that you might not expect is this a divided by b. So 10 divided by 3 is 3 remainder 1, and so we get the result 3 out because when you divide an integer by an integer, you have to get an integer result. So the type cannot change during the operation. So when we do this, we're doing what's called integer division, and we drop the remainder. Now, if the remainder is interesting, that's what this remainder operator is for, and then we can pick up that remainder 1 out of it. Now, just like when we're doing division, we can't change the type. So dividing an integer by an integer can't give us a floating point number, for example. We're also not allowed to add two integers of different types. So if we take this as an example, we've got the integer a set equal to 10 and an 8-bit integer set equal to 3, And if we try and add those together, we're actually going to get an error. So even though Go might be able to do that theoretically, it's very, very insistent that it's not going to work across types without your consent. So in order to make this work, we would actually have to do a type conversion on one of the variables to convert it into the type of the other. So just like we talked about in the last video, where Go is very, very hesitant about implicit data conversion, this is another example. Even though these integers are almost equivalent, Go is not going to make that assumption for you. You're going to have to do the type conversion. Now, a couple of other operations that we have are called the bit operators. So if I drop in this example, we see the 4 bit operators that we have. We've got the AND operator, we've got the OR operator, we've got the exclusive OR operator, and we've got the AND NOT operator. Now, what's going to happen when we run this? Well, let me just run this first and get these results. So you see that if we take A and B, then we get 2. If we take A or B, we get 11. And these might not make a lot of sense. So in order to clear things up a little bit, let me put in the binary representation of these, and then we can walk through what these are doing. So 10 is 1010 in binary, 3 is 0011. Now when we run into an AND operation, that's going to look for what bits are set in the first number and the second number. So as we can see, we've got 4 bits in each one of these numbers that are allocated. Actually, these are 32 or 64 bits long, but I'm ignoring all the zeros at the beginning of these numbers. So let's look at the 4 digits that matter. So if we look at these, then we see actually if we AND these together, we're going to get 0010. And in binary, that is 2. So 10 and 3 equals 2. Now if we do the OR means if one or the other is set. So we get 1 because A has the first bit set. Neither one has the second bit set. Both have the third bit set, so we're going to include that. And then B has the last bit set, so we'll have that. So now we end up with 1011, which is 1 plus 2 plus 8, which equals 11. Exclusive OR means either one has the bit set or the other does, but not both. So in that case, we're going to do 1001. The only difference between this and the OR operation is that third bit, where they're both set to true, and therefore we're not going to include that. Now in the AND NOT, that's kind of the opposite of OR, because with AND NOT, it's going to be set true only if neither one of the numbers have the bit set. So since the first bit is set in A, we're not going to include that. Neither one has the second bit set, so we're going to include that. Both have the third bit set, so we're not going to include that. And B has the fourth bit set, so we're not going to include that. So we get 0100, which is equivalent to the number 8. And that's how these bit operations work. The last example that I have to show you with integers is what's called bit shifting. So when we have this example here, the first print statement is going to bit shift A left 3 places, and the second is going to bit shift A right 3 places. So let's run this and see what that's going to do. And so we get the numbers 64 and 1. So in order to understand that, let me go ahead and put in these values so we can understand what's going on. So 8 is really 2 to the 3rd power. And when we do bit shifting, we're basically adding to that exponent as long as we're dealing with the power of 2. Because really what we're going to do is we're going to take this 2 to the 3rd and multiply it by 2 to the 3rd, which is equivalent to 2 to the 6th. And 2 to the 6th is 2, 4, 8, 16, 32, 64. So that's how we get the 64. Now, when we bit shift to the right, we're going to take our original number and we're going to divide it by 2 to however far we're shifting. So we're going to divide it by 2 to the 3rd. And in that case, we're going to get 2 raised to the 0 power, and any number greater than 0 raised to the 0 power is 1. And so that's how those operations work. The next data type that I want to talk about are the floating point types. So we have a lot of different integer types, so we can store a lot of different size numbers, but with integer types we can only store integers. So they can be positive or negative integers or 0, but we can't store decimal numbers. So in order to store decimal numbers in Go, we're going to use the floating point numbers. Now the floating point numbers in Go follow IEEE 754 standard, and in that standard, we're going to pull out 2 of the types. So we've got 32-bit floating point numbers and 64-bit floating point numbers. So if you're working with a 32-bit floating point number, you can store numbers between plus or minus 1.18 times 10 to the negative 38th, all the way up to 3.4 times 10 to the 38th. So from very small numbers to very large numbers. If you need even more precision than that, then you can use a float 64, and that can go from plus or minus 2.23 times 10 to the negative 308th, all the way through 1.8 times 10 to the 308th. So how do we create floating point numbers? Well, here's some examples of how we can do that. So line 8 here shows you how you're going to define your floating point literals almost all the time. So we're going to declare a variable n, set it equal to 3.14, and away we go. This next line here shows that we can use exponential notation. So we can use 13.7 times 10 to the 72nd, and that's going to be able to use the short form e72nd to stand for that 10 to the 72nd. So if I run this, we're actually going to get the final result here of 2.1 times 10 to the 14th as a floating point 64, but notice we didn't get any errors. So all three of those declaration syntaxes are okay. So that's how we can work with floating point numbers, and to show you how you can explicitly declare these, we can use, let me just do var n float 32, for example, and initialize that, and that's how you're going to declare a floating point number. Now, unfortunately, this number is a little big because we can only go times 10 to the 38th power. So if I comment that line out, things are going to run properly. If I come back in and make this a floating point 64, then we can restore this number. And that's another thing that's important. If you're going to use the initializer syntax on a decimal, it's always going to be initialized to a float 64. So keep in mind, you can't do arithmetic operations between float 64s and float 32s. So if you're just using the initializer syntax, you're going to want to make sure that everything's working as float 64. And if you forget, don't worry about it. The compiler will complain at you, and you can quickly go in there and make sure that everything's working properly. Okay, now speaking of arithmetic operations, let me jump in a couple of those, and you can see the arithmetic operations that are available with floating point numbers. So if I run this, we get the expected answers of adding, subtracting, multiplying, dividing two numbers together. Now, a couple things to notice here. When we divided a by b, we did in fact get a decimal result, because as long as we're working with floating point numbers on both sides, we can get a floating point result. As a matter of fact, we have to get a floating point result. The other thing to notice is we don't have the remainder operator available. That is only available on the integer types. Further, we don't have the bitwise operators or the bit shifting operators. So if you need to work with those, you're going to have to work with the integer types. The last type of numeric primitive that we have available in Go is the complex type. And this is really kind of exciting because this is fairly rare in the languages that I've worked with, where complex numbers are actually treated as a first-class citizen, and it opens up Go to be used as a very powerful language for data science. So if we come in and paste an example, you can see a very basic declaration of a complex number. Now, there are two types of complex numbers. There's complex 64 and complex 128. And the reason we have that is we're basically taking a float 64 plus a float 64, or a float 32 plus a float 32 for the real and imaginary parts. Now here I've got a very simple complex number that's 1 plus 2i. If I go ahead and run that, you see that in fact it prints out as 1 plus 2i, and that's complex 64. So Go's parser understands the I literal as an imaginary number, and it uses that when you're creating your variable. Now we can actually go even simpler than that, because I is considered special, and we can run this with just 2i, and we get 0 plus 2i down here in the result. Now what operations do we have available? Well, we can do addition, subtraction, multiplication, and division again. So I've got two complex numbers defined here. If I run this, then I get the expected result, where the real parts are added together and the imaginary parts are added together, or subtracted, multiplied, divide, whatever operation we're applying. Now what happens if you need to decompose this down? So if I come back to our first example here, where we have 1 plus 2i, not every operation that I'm going to do with these numbers is going to need this to work as a complex number. So what happens if I need to get at the real part or the imaginary part? Well, in order to do that, we actually have two built-in functions in the language. So let me wrap this n here with a call to the real function, and then I can follow that up with its partner, which is the imag function. Now what those are going to do is those are going to look at the complex number that you provide, and they're going to pull out the real part or the imaginary part. And these functions work with complex 64s and complex 128s. So if you run this on a complex 64, then the real and the imag function are going to give you float 32s out. If you run this on complex 128, it's going to give you float 64s out, because those are the data types used for the components. So if we run this, we see that we get float 32s out. If we convert this to a 128 and run this again, then we're going to get float 64s out, and it's going to break apart that complex number into the real and imaginary parts, so we can work with those however we need to. Now the complement to these two functions is the complex function. So if you're working along in your program and all of a sudden you need to make a complex number, how do you do that? Because you can't use this literal syntax. So in order to do that, we do have another function, and that's the complex function. And this takes two numbers. The first number is the real part, and the second number is the imaginary part. So let me go ahead and wipe out this line. get rid of these real calls here, and then run. And now that we see that we can take two floating point numbers, in this case they're considered to be floating point 64s because we're making a complex 128, and it creates 5 plus 12i for us. The last data type that I want to talk about is the text type. And text in Go falls into two basic categories. One I can talk a lot about, the other we're just going to touch on. So the first text type that we have available is a string. And a string in Go stands for any UTF-8 character. So that makes it very powerful, but that means that strings cannot encode every type of character that's available. For that, we need the other text type, which we'll talk about in a second. But let's just start by introducing a basic example here. So here I've got a string literal. This is a string. I'm going to print out its value and its type. So if I go ahead and run this, you see that this is a string prints out, and it's of type string. No big surprise here. Now, one of the interesting aspects of a string is I can actually treat it sort of like an array. Now, we haven't talked about arrays yet, but I can actually treat this string of text as a collection of letters. So if I do something like this, I'm actually going to ask it for the third letter because arrays in Go are zero-based. So I'm going to look for the 0, 1, 2. That's the third letter in the string, which is the letter I. So if I run this, I get an interesting result. I get the value 105, and that's a uint 8. So what the heck happened there? Well, what's happening is that strings in Go are actually aliases for bytes. So we can go ahead and convert this guy back, since a byte is just an alias for a string, and we can get our letter I back. Now, strings are generally immutable. So while I can inspect the second character, I can't do something like this. If I tried to run this program, let me just print out the full string here and run this, then I get an error. And there's actually quite a few things wrong with this. The first thing is I can't assign a string to a byte because I'd have to do a conversion. The second thing is I can't manipulate the value of the string. Now with the numeric types, I showed you that there were quite a few operations that we could perform with it. There is one arithmetic or pseudo-arithmetic operation that we can do with strings, and that is string concatenation, or in simpler terms, we can add strings together. So in this example, I've got the string s and the string s2, and as you can see down in the printf statement, I'm adding s and s2 together, and then we're going to print out their value and the type. So if I run this, you see that it just munges all the strings together, and it gives us the result. Now another thing that I can do with strings is I can actually convert them to collections of bytes, which in Go is called a slice of bytes. So in this example, I'm starting with a string, this is a string, and then I'm going to do a conversion to this collection of bytes, and I'm going to pass the string into that. So if we run that, we actually get this is a string, comes out as the ASCII values or the UTF values for each character in that string, and then you see that the result is a collection of uint8s, which is a type alias for bytes. Now why would you use this? Well, that's a very good question. A lot of the functions that we're going to use in Go actually work with byte slices, and that makes them much more generic and much more flexible than if we worked with hard-coded strings. So for example, if you want to send as a response to a web service call, if you want to send a string back, you can easily convert it to a collection of bytes. But if you want to send a file back, well, a file on your hard disk is just a collection of bytes too. So you can work with those transparently and not have to worry about line endings and things like that. So while in your Go programs, you're going to work with strings a lot as strings, when you're going to start sending them around to other applications or to other services, you're very often going to take advantage of this ability to just convert it to a byte slice. Okay, the last primitive data type that we have to work with is called a rune. Now a rune is a little bit different than a string type in Go, because where a string type represents any UTF-8 character, a rune represents any UTF-32 character. Now UTF-32 is a little bit of a weird animal, because while any character in UTF-32 can be up to 32 bits long, it doesn't have to be 32 bits long. For example, any UTF-8 character, which is 8 bits long, is a valid UTF-32 character. So there's all sorts of tricks that they have to do in the encoding of the characters in order to know whether the character is 1, 2, or 4 bytes long. So that makes things a little bit tricky to work with in Go. Now we're not going to get too deep into this subject, we're just going to talk a little bit about what runes are, and then I'm going to point you to some things that you can refer to if you actually need to work with runes in your application. So if we look at this example here, we're declaring the rune A. Now notice the difference here. If we were declaring a string, we would have double quotes. When we're declaring a single rune, we use single quotes. But if I run this, I'm going to get an interesting result. Notice I get the value 97, and it's an int32. Now that might seem a little weird. And the reason for this is because runes are just a type alias for int32s. So where strings can be converted back and forth between collections of bytes, runes are a true type alias. So when you talk about a rune in Go, it is the same thing as talking about an integer 32. Now you might think, well, that's just because we're doing some implicit initialization here. We're using that : syntax. So let's specifically and explicitly declare this as a rune and try this again. And we get the same result. And again, that's because a rune is an integer 32. Now, you might be feeling a little lost here. So if I've got a UTF-32 character set, how do I work with that? Well, the answer comes from the Go APIs. So if I jump out to Golang.org, come into the packages, and let me just jump to the strings package, and then I'll show you this. Notice this function here, read rune. So if you're working with a data stream that's encoded in UTF-32, then you have special functions that you're going to be able to take advantage of that's going to return those values out. So if we do read byte, which is going to read a single character, then we're going to get a byte out and a potential error. But with read rune, Go is going to look at the byte stream, it's going to pull off the next rune that's available, tell you the size of that rune, and then a potential error. So you're going to have all the information you need in order to re-encode that integer 32 that you're going to have back into its UTF-32 character. So things are a little bit more tricky when you're working with runes, and you're going to have to read into the APIs for the Go package that you're working with in order to understand how to work with them in your application. Okay, so that covers the primitive data types that you have to work with in Go. Let's go into a summary and review what we've talked about in this video. We covered a lot of ground in this video, and I understand that it might take a little bit of time to process this and really understand all the different options that you have for primitive data types in Go. Now, before we get into the summary, I do want to let you know that a lot of times the default data types that you're given are going to be perfectly fine. So if you're working with Booleans, you're going to get a Boolean type. If you're working with integers, you're going to get that signed integer type. Floating point is going to give you floating point 64, and so on. So you don't have to memorize every single data type. If you need a specific data type, then you can certainly refer to the Go documentation in order to find out what's available for you. So let's go through and review what we talked about. The first thing that we talked about was the Boolean type of data. We found out that it can take two values, true or false, and it's not an alias for other types. So in some languages, a Boolean is actually an alias for an integer, so you might use like -1 for true and 0 for false. When Go, Boolean is its own type, so you can't convert back and forth between integers and things like that. You're going to have to work with Booleans as their own type. We also talked about the 0 value for a Boolean is the value false, and so if you initialize a Boolean and don't set a value for it, it's going to receive the value false. Then we talked about the numeric types. And the first type that we talked about were the integer types, and that broke down into two different types. We have the signed integers, and there are two classes, I guess you could say, within the signed integer type. There's the int type, which has varying size, but a minimum of 32 bits, and this is going to be the most common type of integer you're going to deal with in your applications. But if you need a little bit more granularity or a little bit more resolution or control over how much memory is assigned to the integer, then you can go all the way from int 8, which is an 8-bit integer, all the way up to a 64-bit integer. We also have the unsigned integers, so where the signed integers have a plus or minus, and so they can't store numbers quite so large because they have to store a plus or minus bit. The unsigned integers can store larger numbers, but they can only ever be positive. And we have all the way through an 8-bit, which we can use the byte or the uint8 type for, all the way through 32-bit unsigned integers with the uint32. We have various arithmetic operations that we can perform on both integer types, so we can do addition, subtraction, multiplication, division, and that remainder operation. So remember, division with integers is going to give you an integer result, so you're going to lose that remainder portion. So if you need that, you can use that remainder operator to get it. We also have the bitwise operators, so we can do and, or, exclusive or, and the and not operations. And the 0 value for any integer type is going to be the literal value 0. So when you initialize an integer type and don't assign a value to it, that's going to be equivalent to the value 0. You're not just going to get whatever was in memory when that variable was initialized. And you cannot mix types in the same family. Now this is going to be true throughout all of the numeric types. If you have a uint16, for example, and a uint32, you cannot add those together. You're going to get a compile time error. The next numeric type that we talked about were the floating point numbers. So they follow the IEEE 754 standard. The 0 value is similar to the integer types, the value 0. And we have two different versions. We got 32-bit versions and 64-bit versions that we can work with. And we have several different literal styles that we can use to initialize them. So we can use a pure decimal like 3.14. We can use exponential notation For example, 13E18 or 2E10, and it doesn't matter if that E is upper or lowercase, or you can do mixed. So for example, 13.7E12 is a perfectly acceptable way to initialize that. We do have addition, subtraction, multiplication, and division that we can do with floating point numbers. Now, we don't have the remainder operation, but the division operation is going to give us a true floating point result, so we're not going to lose our decimal portion. The final numeric type that we talked about were the complex numbers. The zero value of a complex number is 0 plus 0i, and they come in 64 and 128-bit versions. And the reason for that is the two components, the real and the imaginary component, are either going to be floating point 32s or floating point 64. So when you add those together, that's where you get the 64 and 128-bit versions. We have some built-in functions that we can work with. So we can use the complex function in order to create a complex number. We can use the real function in order to get the real component, and we can use the imag function in order to get the imaginary component of a complex number. Now what the data type that comes out of that depends on the size of the complex number going in. So a complex 64 is going to give you a float 32 out from the real and the imag function, and a complex 128 is going to give you a float 64 out of the real and the imag function. We have the same arithmetic operations as we do for floating point numbers. We can do addition, subtraction, multiplication, and division. The final category of primitive data that we talked about were the text types. And in Go, there are really two different text types. The most common one that you're probably going to deal with are strings. Now, strings are represented as a collection of UTF-8 characters. They're immutable. You cannot change the value of a string after it's been initialized. You can concatenate strings together with the plus operator, and then you can convert them back and forth between a collection of bytes with this square bracket byte syntax and passing in the string. That'll convert it to a collection of bytes, and you can convert a collection of bytes back to a string by using the string conversion. The other type we talked about is a rune, and a rune represents any UTF-32 character. Now, runes are a little bit more complicated to work with because of the multi-step process that it takes in order to encode a character into the UTF-32 character set. So when we're working with runes as a primitive type, really all we're working with is an alias for an integer 32. Today I want to talk about constants and how you can use them in your Go applications. Now there are several things that we need to talk about with constants, so like we've been doing, I want to break this down into several categories. The first thing that I want to talk about is how we're going to name constants in our Go applications. Then we'll talk about typed constants, followed by a discussion about untyped constants, and we'll talk about the differences between those two and the options that each one gives us. And then we'll talk about a method of generating constants that are called enumerated constants. And finally, we'll end our discussion by talking about enumeration expressions, which are going to build upon the concepts that we're going to talk about in that first enumeration discussion. The first thing that I want to talk about is how we're going to name our constants. So all constants are going to be preceded with the const keyword that's going to let the compiler know that that's what we're trying to work with. Now, if you've come from other languages, you might be expecting that we're going to name our constants something like this, where we're going to have all uppercase letters and separate the words with underscores. The problem with that is if we do that in Go, then the first letter is going to be uppercase. And as you remember from our discussion on variables, if we've got an uppercase first letter, that's going to mean that the constant is going to be exported. And we don't always want that. So instead of this, we're actually going to name our constants the same way that we name variables. So if we had a variable that we wanted to call myConst, and we didn't want to export it, then we would start with a lowercase first letter, or in other words, we would use camel casing. And if we did want to export this symbol, then we would simply change that first character to uppercase. Now, assuming that we're going to be working with an internal constant, then we're going to switch this back to a lowercase first letter. And then let's talk about how we can create what's called a typed constant. Now, a typed constant is created very similarly to a typed variable. So we can start with the const keyword, then the name of our constant, and then we're going to list the type of the constant, and then we can set it equal to a value. Then if we want to prove that that worked out the way we expected it to, then we can go ahead and print out the value and the type of the constant, and we will do that by using this printf statement here. And then when we run this, we see that the constant is in fact created. It's got the value 42 that we assigned, and it's got the type that we assigned to it. Now, the reason it's a constant and not a variable is it has to remain constant. So if we tried to do something like this, change this to the value 27, then the compiler throws an error because we're not allowed to change the value of a constant. Another characteristic of a constant is that it has to be assignable at compile time. So for example, if I wanted to have a constant that represented the sign of pi over 2, then I might be tempted to do something like this. I'll create a float 64 constant, and I'll set it equal to the result of the sign function from the math library, and I'll pass in 1.57, which is approximately pi over 2. and then I can run this, right? Well, the problem with that is in order to determine the sign of that value, that actually requires the function to execute, which is not allowable at compile time. And so you can't set your constants equal to something that has to be determined at runtime. And that includes things like setting it equal to flags that you pass into your application when you run. If you're going to do that, you can't use a constant to store that value. Now, constants can be made up of any of the primitive types that we talked about in the last video. So if we have this example here, we've got an integer constant, we've got a string constant, a floating point constant, and a Boolean constant. And if we run this, we see that all of those print out exactly the way that we expect. We've got the integer, the string, the floating point value, and the Boolean value. Now, in an upcoming video, we're going to talk about the collection types. And the collection types are inherently mutable. So for example, you couldn't create an array and declare that to be a constant type. Arrays are always going to be variable types. Now, another characteristic that constants have in common with variables is they can be shadowed. So if we create a constant at the package level, and let's just make this an integer 16 and set it equal to the value 27, then we'll delete these guys and also these guys. Now we've got a constant called a declared at the package level that's an integer 16, and then we got a constant in the main function that's also called a, and it's an integer type. So if we update this printf statement to print the type of the variable, we see that looks like I need to print my variable twice. We see that the inner declaration of the constant wins. So not only can we change the value of the constant, but we can also change the type because the inner constant shadows that outer constant. And we can prove that by commenting this line out, running again, and we see that the package level constant wins. So you want to be a little careful here because if you're going to reuse constants, it's going to feel like those values are changing. So I wouldn't recommend that you take advantage of this, but if you do get into a situation where constants aren't evaluating the way that you expect them to, this is one possible reason. Now, when we're working with constants, they work very similar to variables when we're using them in operations. So if we bring this line back and set it equal to 42, and then what I want to do is declare a variable. So we'll declare a variable b as an integer and set that equal to the value 27. And then we can do a plus b. And let's see what happens when we do that. So if we run that, we in fact get the ability to add a constant to a variable, and the result is going to be a variable. And so since the constant and the variable are of the same type, we can perform the addition operation on there. Now, if our constant is of a different type, for example, if we made variable b an int16 and run this, then we get exactly the same failure that we get when we try and add two variables of different types together. Now, so far, all that we've been talking about are these typed constants, where after the constant name, we list the type. But we don't have to do that. We can use the compiler's ability to infer the type for us. So let's just go ahead and do that with this example here. When we run this, we see that the constant a is inferred to be an integer with the value 42. Now, given that the compiler's inferring the value, what do you think is going to happen if we do something like this? If we restore that previous example, where we're going to add this constant to an integer 16. Well, in fact, in this case, the operation succeeds, which might be a little bit confusing. But the reason that works is because what the compiler's actually doing when it sees this constant is it's basically replacing every instance. So the way the compiler sees this program is it sees it like this. So since we're taking a literal 42 and adding an int16 to it, that 42 is interpreted as being an integer 16. So the compiler doesn't say, oh, constant a equals 42, that's an integer and always an integer. Instead, the compiler is going to look for every time that we use the symbol a, and it's going to replace that with the value of the constant. And so we can do these implicit conversions when we're working with constants, which is something that we can't really do when we're working with variables. The next thing that I want to talk about are what are called enumerated constants. So let me go ahead and start that conversation out by wiping out what we have here, clean up our code just a little bit. And then I'm going to do this at the package level because this is where I've seen these most commonly applied. You could do these in a function level if that made sense in your application. So I'm going to declare a constant a, and I'm going to have that as an untyped constant, and I'm going to set it equal to this special symbol called iota. So when I run this, you see that a is evaluated to have the value 0, and it's inferred to have the type integer. So what is iota? Well, iota is a counter that we can use when we're creating what are called enumerated constants. So in this example, having an enumerated constant isn't terribly valuable. But one of the things that I can do with constants is I can actually work with them in a constant block like this. So when I'm doing this, I can create another constant, set that equal to iota, and another constant, and set that equal to iota. Now let's go ahead and clean up this because we already know what the type is going to be, so we don't need to be printing that out. And then let's print this command out 2 more times, switching to B and C. So now we're using iota 3 times, and when we get the result, we actually see iota is changing its value as the constants are being evaluated. So the first constant that's assigned has the value of 0, then 1, and then 2. Now another special feature that we can take advantage of with iota is that if we don't assign the value of a constant after the first one, then the compiler is going to try and infer the pattern of assignments. So in this example, we would expect to have an error because B and C don't have a value assigned. But since we've established a pattern for how to name the constants in this block, when we run, we actually get the same result. And that's because the compiler is going to apply the same formula. So it's going to apply B equals iota and C equals iota for us. Now, that value of iota is scoped to that constant block. So if we create another constant block, and in this case, we create a constant called A2, and set that equal to iota, copy this line, bring it down, and print out the value of A2. Then what we're going to find is iota resets to 0. So iota is scoped to a constant block. And what that lets you do is you can actually create related constants together, ensure that they have different values, and then if you have another set of related constants, you can start another constant block and ensure that they have unique values, but allow duplication between the values in one constant block and another. So what's an example where you might use this? Well, let me just drop in this simple application. And what we're doing here is we're setting up a constant block where maybe we're trying to store the specialty of veterinarians in a veterinarian clinic. So a veterinarian could be a cat specialist or a dog specialist, or maybe we can take a snake specialist too. Now, as you can see inside the const block, I'm setting the cat specialist equal to iota. And then in the main block, I'm creating a variable and setting its value equal to cat specialist. So if I check to see if the specialist type is a cat specialist, then I in fact get the value true. Now that works just fine. And this also works if I, for example, use a dog specialist, assign that specialist type to be a dog specialist, run that, then that's going to work out just fine. So everything looks really good here, right? And this is a very common use for enumerated constants. However, one thing that I would warn you about is what happens if I declare this variable and don't initialize it to a type. Well, if I check to see if it's a dog specialist, I get false, which makes sense. But remember, what is the initial value of iota? Well, the initial value of iota equals the 0 value for an integer. And so in fact, even though we haven't specified a specialist type, it does show up as the value cat specialist. So what do we do about this? So there's a couple of approaches that we can take here. The first is to use the 0 value of the constant as an error value. So we can set this equal to error, then we don't need this statement anymore. And now, when we check to see if the specialist type is a cat specialist, we get the value false because cat specialist is equivalent to the integer value 1, which is no longer the 0 value of the integer. This is a very valuable approach if you want to check to see if a value hasn't been assigned to a constant yet. So you can specify an error specialist, and then you can check to see if that value is set equal to the 0 value of that constant. And if it is, you can handle that error because presumably you expect that to be initialized in some way. Now, if your application guards against that, and there's no reasonable way for this to happen, then you can take advantage of this underscore symbol, which is goes one and only write-only variable. Now, what's the value of a write-only variable? Well, with iota, we have to have a 0 value. We always have to start with 0. But if we don't care about 0, then we don't have any reason to assign the memory to it. So we can use this underscore symbol, and we'll see this in quite a few places in our Go applications. And basically what that tells the compiler is, yes, I know you're going to generate a value here, but I don't care what it is. Go ahead and throw that away. So if we run our application again, everything works just fine. But in this case, we can't actually get at the 0 value of this constant block. Now, the ability to create lists of enumerated constants with iota is very valuable, but things don't actually stop there. And the reason is, remember, the value of a constant has to be able to be determined at compile time. But there are some operations that Go is going to allow us to do. For example, we can do addition. So if we do this and run, then we get false again. But what happens if we print out the value of cat specialist? If we do that, and we're going to have to remove this line, then in fact, that expression got evaluated. So the first line, line 8, is evaluated to iota plus 5, which is 0 plus 5. The next line, cat specialist, iota increments, and the formula repeats. So cat specialist is equal to the value 6, dog specialist is 7, and snake specialist is 8. So this can be valuable if you need some kind of a fixed offset. Now, a common use case for this is to use the bit shifting operators, because anything that we can apply to our primitive type, we can apply here as long as it's not a function expression. So we can do addition, subtraction, multiplication, and division. We can do remainder operations. We can do the bitwise operations. And we can do bit shifting, which is one of the more interesting use cases that we can take advantage of. And the reason is because we don't have the ability to raise to powers, because raising to powers in Go is a function in the math package. So we can't do that in our constant evaluations. But by bit shifting, we can raise things to the power of 2, because every time you shift a number one level, you're actually multiplying it by 2. So we have this example here, and I actually stole this from the Effective Go article on Golang.org. So what we have here is we have an example of a constant block that's giving you constants that are equivalent to kilobyte, megabyte, gigabyte, terabyte, petabyte, and so on. So down here in our main program, what I've done is initialize the file size to some arbitrary value, and then I've got this printf statement, and this is basically going to format our result to print 2 decimal places, and then the literal string GB afterward. So this string here is basically saying I'm expecting to format a floating point number, and I'm going to give it 2 decimal places. This GB is a literal GB that's going to be printed in the result, and then we've got the value that's going to be used to fill this in, and that's going to be file size divided by the GB constant. Now you notice this constant block is set equal to 1, and then we're going to bit shift that value 10 times iota. So the first time we're going to bit shift 10 times 1, so we're basically going to multiply this by 2 to the 10th, and then we're going to multiply by 2 to the 100th for the megabyte, and then 2 to the 1000th for gigabyte, and so on. So when we run this, we get a really convenient way to format an arbitrary file size into a human readable format. And in the Effective Go article, it actually shows you how to put a switch block, which we haven't talked about, so you can make a decision about which constant you're going to use based on the size of the incoming value. So here we get this nice way to format this relatively difficult number to read to be the very easily read 3.73 gigabytes. Now another thing that can be very valuable to do is using bit shifting in order to set Boolean flags inside of a single byte. So if I paste this example in, we can see an example of that. So let's just say that we've got an application, and that application has users, and those users have certain roles. So inside of this constant block here, I'm defining various roles that we can have. So for example, you might be an admin, you might be at the headquarters or out in the field somewhere, you might be able to see the financials or see the monetary values. And then there may be some regional roles. So can you see properties in Africa? Can you see properties in Asia, Europe, North America, or South America? So in order to define these constants, what I'm doing is I'm setting the value to 1 bit shifted by iota. So the first constant is admin is 1 bit shifted 0 places, so it's a literal 1. The second one is 1 bit shifted 1 place, so that's 2, and then 4, and then 8, and then 16, and so on. So what I have is each one of these constants is going to occupy 1 location in a byte. So down here in the main program, I'm defining the roles in a single byte, and I'm ORing together is admin, can see financials, and can see Europe. Now if you remember, ORing is going to be set to true if one of the values is true or the other one. So is admin has the binary representation of 00000001. I think that's enough zeros. 7 zeros followed by 1. Can see financials is going to end up with 100. Can see Europe is going to end up with the value 100000. And so when we OR those all together, we're going to get this byte that has these 3 flags set to true. So when we run this, we see that we've encoded 8 access roles for a user into a single byte of data. So we're able to store this information extremely efficiently. So if I want to see, for example, if this user is an admin, I can go ahead and print is admin and then print out the value. And then in order to determine if that's valid or not, then I can do a little bit of bitwise mathematics here. So I can take the constant isAdmin and that with the roles, and what that's going to do is that's going to apply what's called a bit mask. So only the bits that are set in the isAdmin constant and a roles are going to be left as true, which means if we're an admin, we're going to have the value 1 set at that first bit, and then I can compare that to the isAdmin constant. So when I run this, if we have the admin role, then we're going to get the value true. Now if I check something that I don't have the role, so let me go ahead and copy this down, and then let's just see if they're at the headquarters. So we'll put that in here, and it's exactly the same bitwise operations. We're just changing our mask. If we run this, we see that isHeadquarters equals false. Actually, let me put in my line return here, and then run this again. And you see that isHeadquarters equals false. So we can very quickly and very efficiently store a lot of different information about what roles and access rights a user might have in a simple byte. And having this constant defined with this enumeration expression makes that really fast and really efficient and really clear in our application. Okay, so let's go into a summary and review what we've talked about in this video. Constants are another one of those foundational elements that's going to be a part of almost every application you're going to write. Now the first thing that we learned about with constants is that they're immutable, but they can be shadowed. So we can create a constant, we cannot assign a new value to it, but if we create a constant on an inner scope from an existing constant, then not only can we change the value, but we can even change the type, because that inner scope is going to shadow the outer scoped constant. They have to be replaceable by the compiler at compile time, so the value must be calculable. So we're not going to be able to access functions or command line arguments in order to determine the value of the constants in our application, but we are going to be able to do simple expressions like we talked about in the enumeration section. They're named like variables, so if you want to export the value of a constant outside of your package, then you're going to use Pascal casing, and if you want to leave it as an internal value to the package, then you're going to use camel casing to name that constant. Typed constants work just like immutable variables, so you can use them in arithmetic operations, you can pass them into functions, but they can only interoperate with the same type. Untyped constants have a little bit more flexibility, so they work just like the literals. So if you replace that constant throughout your application with the literal value of that constant, that's how it's going to work. So that's going to allow it to interoperate with similar types. So we had the value 42 defined as an untyped constant, and we could add that to an integer 16, we could add that to an integer, we can add that to a uint 16, any of those would work because the literal 42 will work in all of those cases. Then we talked about the enumeration types that we can work with, and we learned about the special symbol iota that allows us to start with the value 0 and increments one time every time we use it inside the same const block. Now the one thing that we have to watch out for is that constant values that match the 0 values of variables can cause subtle bugs in your application because you might have logic that you expect to initialize the value of the constant, and if something happens and that initialization doesn't occur, then you're going to be working with the 0 value, which might give you a false match to a constant that you're evaluating against. Using that iota operator, we can actually create what are called enumeration expressions. So we can define the value of the constant dynamically by combining iota with any arithmetic, bitwise operation, or bit shifting operation that's allowable with the primitive type that the constant is representing. I want to talk about the first two collection types that we have available in Go, arrays and slices. Now, arrays form the basis of slices, so I want to start our discussion with those. And when we talk about arrays, we're going to talk about how to create them, the built-in functions that Go offers us to understand what's going on with our arrays, and then we'll do some exercises working with arrays and see how we can use those in our applications. Then we're going to follow the same pattern, but we're going to switch over to slices. So we'll learn the various ways that we can create slices, we'll learn the built-in functions that we can use to understand what's going on with our slices, and then we'll do some exercises working with those. Okay, so let's go ahead and get started by learning how to create an array. So the first thing that I want to discuss about arrays is the use case for them. Why do we need them, and what are they used for? So let me just drop in an example. Let's just say that we're building an application that's going to work with the grades of students in a class. So without arrays, we're going to end up with an application something like this. We're going to have maybe grade 1, grade 2, grade 3, and then we can print out those grades. So we can go ahead and run this, and we see that we get the scores 97, 85, and 93 printed out. Now this works sort of, but we got a lot of problems here because our application needs to know exactly how many grades we have to work with at the time that we're designing the application, and working with these grades as a collection becomes very cumbersome. So enter the array, and that's going to solve all of our problems. So in order to see what an array looks like, let's go ahead and delete this code here, and then we'll create an array that's going to hold the grades for us. Now the way we declare an array is we're going to start with the size of the array. So we're going to use square brackets, and then we're going to have an index that's going to be the number of elements that our array can hold. And then the type of data that the array is going to be designed to store. So an array can only store one type of data. So in this case, we're declaring an array of integers that can hold up to 3 elements. If we wanted to hold a different type, say we wanted to have an array of strings, then we would type this to a string, and so on. So you have to specify at the time that you're declaring the array what type of data you're going to store. And then we can use this initializer syntax to put in the values for our array. So we can put in the same scores that we had before, 97, 85, and 93. And then if we come into our print statement here and add our grades as what we're going to print, then we see that we have all of the grades printed out together in this collection called an array. Right now, that's a convenient collector. As we start getting into looping constructs and things like that, we're going to really find that having things grouped into arrays and slices and the other collection types is a very powerful way for us to work with our data. Now, another advantage that we have with working with arrays is the way that they're laid out in memory. So if you declare 3 different variables and specify their values, it's impossible to know how they're going to be laid out by the Go runtime. With arrays, however, we know by the design of the language that these elements are contiguous in memory, which means accessing the various elements of the array is very, very fast. So by collecting our data together in arrays, not only is it easier to work with, but it also makes our applications generally a little bit faster. Now, one problem that we have in this example here is if you look at it, we're actually declaring the size of the array twice, because we have this syntax here where we're saying that we're creating a 3-element integer array, but then we're adding 3 elements to it. And that's not really required. If you're going to be initializing an array literal like we're doing here, then you can actually replace the size with these 3 dots here. And basically what that says is create an array that's just large enough to hold the data that I'm going to pass to you in the literal syntax. So in this case, we're going to get an array that has 3 elements in it, and that's implied by the fact that in this literal syntax, we've passed 3 integers to it. We can also declare an array that has a certain size, but has its values zeroed out by doing something like this. If we declare an array called students, and let's make that a 3-element array that's going to hold strings, and then let's print out what we have in that array. So if we print out students, make sure I'm spelling everything correctly and run this, then we see that we have an array that's empty. So we have declared a 3-element array that can hold strings, but obviously there's no elements in there right now. So in order to specify a value in the array, we're going to use this syntax. So we're going to call upon the array, and then we're going to tell it which index we want to work with within the array. So in this case, we're working with the 0th index of the student's array, and then let's just assign the name Lisa to it. And then we can go ahead and print out our array again and run it. And now we see that we have, I always forget to add this line return here. Then we see initially we have an array of students that's full of empty strings. In the second instance, we've actually specified that first element. Now you may be wondering why we're starting with the value 0. And the reason is related to how arrays are made up of contiguous blocks of memory. So when we talk about students as the name of the array, what Go is going to do is it's going to have a pointer, or it's going to remember the location of the beginning of that array. And then the index that we pass, in this case 0, is going to tell it how many strings to walk forward. So it knows that when it has a string has a certain length, and so it's going to walk that many strings. So when we pass 0, it's going to be the head of the student's array moved forward 0 string elements. And so that's going to be the first element of our array. So we can finish this example out. If I drop some code in here, we can see what it would take to fill out this array. So in this case, we got the 0th element still Lisa, the first element is Ahmed, and the second element is Arnold. So if we print that out, we see the expected result where we have Lisa, Ahmed, and Arnold. And it doesn't matter what order we work with these. If we flip these around, then we find that they do flip around in the array. We can assign them in any order that we want. Now, if we want to add a specific element in the array, then we can use this square bracket syntax again and dereference the element from the array. So if we do this, and then change our label again, so we're going to get the second element of the array, which is index 1, then we can go ahead and run this, and then we see that the second element has the value Arnold. So we can use this square bracket syntax in order to assign values to the array, as well as to pull out the values that have been assigned. Now, another thing that we can do is we can determine how big the array is. Now, obviously, we created the array up on line 8, so we remember at design time that we created this, but there may be a situation where you need to go back and review the size of the array that you're working with. And the way that we can do that is using the built-in length function. So if I drop in another print statement here and format that, you see that we can get the number of students in an array using this built-in len function and passing in the array. So if we run this, then we see that we get the number of students equals 3, and that's going to print out the size of the array. So if we change the size of the array to, say, 5, then the results of printing out the array isn't going to change, but the size of the array does. Now, one thing that's important to remember is that an array can be made up of any type. It just always has to be the same type for a given array. So we've been working with arrays of integers and arrays of strings, so we've been working with primitives. But this example here shows that we can actually make up arrays of anything else. So in this case, we've got an array of arrays. So let's just say that we're working with some linear algebra, and we need the identity matrix, which is a concept that's used pretty often in linear algebra. So this array here stores a 3 by 3 identity matrix. So the first row is going to hold the values 1, 0, 0. The second row is going to hold 0, 1, 0. And the third row is going to hold 0, 0, 1. So if we go ahead and print this out, then we see that we do in fact get those values. Another way to look at this that may be a little bit easier to see is using this way here. So we're just going to declare the array of arrays, and then we're going to initialize each one of those rows individually. So this reads a little bit cleaner and might be a little bit easier for you to understand what's going on. And if we run this, we get the exact same result. Now, the last thing that I want to talk about with arrays is something that's a little bit different with arrays in Go than in other languages. And that is that arrays are actually considered values. So in a lot of languages, when you create an array, it's actually pointing to the values in that array. So if you pass things around, you're actually passing around the same underlying data. But in Go, that's not true. When you copy an array, as we're doing on line 9 here, you're actually creating a literal copy. So it's not pointing to the same underlying data, it's pointing to a different set of data, which means it's got to reassign that entire length of the array. So if I run this, you'll see what I'm talking about here. So on line 8, I assign an array. On line 9, I create another variable b and assign that to a. And then on line 10, I change the second element of the array to the value 5. And what you see is that when I print out the array a, it has the original values of 1, 2, 3, but b has the new values of 1, 5, 3. So when you're working with this, you have to be a little careful, because copying arrays, especially when we get into functions, if you're passing arrays into a function, Go is going to copy that entire array over. So if you're dealing with a 3-element array, that's not a big deal. If you've got 1,000,000 elements in your array, that could slow your program down a little bit. So what do you do if you don't want to have this behavior? Well, we haven't talked about it yet, but I want to give you a hint right now in order to cover this completely. And that is this idea of pointers. So the way that our program is working right now is that the value b is assigned to a copy of the array a. But if we do the address of operation, which is this character here, then what we're saying is b is going to point to the same data that a has. Now, we'll get into more detail about what this means later, but the long and the short of it is, if I run this, now a and b are pointing to the same data. So a is the array itself, and b is pointing to a. So when we change the value in line 10, we're actually changing the same underlying data for both. So when we print them out, we see that the array a has changed, as well as the array that b is pointing to, because they happen to be exactly the same array. Now, arrays are very powerful, and there's a lot of use cases where you can use arrays very efficiently. However, the fact that they have a fixed size that has to be known at compile time definitely limits their usefulness. So in Go, the most common use case for using arrays is to back something called a slice. So let's take a look at a slice. So the first thing that I want to do is comment out a couple lines in this example here. So we'll comment out this one, and this one, and then we'll change this over to slice syntax. So the way we're going to do that is simply by eliminating these 3 dots here. So a slice is initialized as a literal by just using the square brackets, the type of data we want to store, and then in the curly braces we can pass in the initialized data. So we go ahead and run this, we see that we get the values 1, 2, 3. It looks exactly like an array. And as a matter of fact, everything we can do with an array, we can do with a slice as well, with 1 or 2 exceptions. So in order to illustrate that, we had the length function that we talked about with an array. Well, we have the length function with a slice as well. So if I run this, we see that we do get the length of 3. So we initialize the slice with the values 1, 2, 3, so with 3 elements. So the length function gives us a value of 3. Now there's an additional function that we have available with slices, and that is the capacity. And that's because the number of elements in the slice doesn't necessarily match the size of the backing array, because the slice is really a projection of that underlying array. So we can have a very large array and only be looking at a small piece of it. Now if we run this example, we see that the capacity function returns a value of 3. So the underlying array is exactly the same size as the slice. But as we go along here, we'll see how we can get into situations where the length and capacity are different and why that's a very good thing. Now, unlike arrays, where we had this syntax here and we had to use this address of operation in order to point to the same data, slices are naturally what are called reference types. So they refer to the same underlying data. So if we run this example again, remember when we ran this with an array, we saw that B stored different data than A when we were done. So if we run this, we see that A and B are actually pointing to the same underlying array, and so when we change the value in B, we get a change in the value in A. So this is one thing that you're going to have to keep in mind when you're working with slices. If you got multiple slices pointing to the same underlying data, you have to keep in mind, if one of those slices changes the underlying data, it could have an impact somewhere else in your application. Now, so far, we've only looked at the literal syntax for creating a slice, and that's what we're seeing here on line 8. There's actually several other ways that we can create slices, and that is illustrated with this example here. So you see on line 8, we're creating a slice that has the values 1 through 10, and then on line 9, we're creating a slice B, and that's using this bracket with the colon in between. And what that's going to do is that's basically going to create a slice of all the elements of what it's referring to. So it's going to create a slice of all of the elements of A. On line 10, we're creating a slice C, and that's going to start with the third element of the parent and copy all the values after that. So that's going to start with the element with index 3, which is of course the fourth element, and every element after that. So this is going to copy 4 through 10 into the slice at C. Then on line 11, we're going to do the other syntax, and that's going to copy everything up to the 6th element, and that's the literal 6th element. That's not element number 7. That's actually the 6th element, which is going to have the index 5. And then on line 12, we actually see an inner slice. So we're going to copy the 4th element through the 6th element into our new slice. So let's go ahead and run this and see what prints out. So we see the first line printed out is the original slice that we have. The second line is the copy of that slice that's copying all of the elements. The third line is going to copy the 4th element on, so we see the number 4 through 10. The 4th line copies everything up to the 6th element, so we get the values 1 through 6. And then the last line printed out is a slice from 3 to 6, and so we're going to get the elements 4, 5, and 6 printed out. So that can be a little bit confusing because the first number has a slightly different meaning than the second number. So basically, the first number is inclusive and the second number is exclusive. So for example, if we look at line 12 again, we're going to copy from index 3 up to but not including index 6. So that's another way that you can look at it. Now, one thing to keep in mind, remember what I said, that all of these operations point to the same underlying data. So if we take element 5 and change that value in the A slice and run this again, notice all of them change their value because they're all pointing to the same underlying array. So each one of these operations includes the 5th index in their results, and each one of those gets updated to the value 42. Now, another thing to know about these slicing operations is they can work with slices like we're doing here, but they can also work with arrays. So if you remember, if I put these 3 dots in here, it's actually going to turn A into an array. And if I run this, we get the same result. And that's because slicing operations can have as their source an array or a slice. So whatever type of data you're working with, as long as it's one of those two, you can use these slicing operations. Now, the last way that we have available to us to create a slice is using what's called the make function. And that's a built-in function that we have to work with. So if I delete all this and drop this guy out, we're going to use the built-in make function, and this takes 2 or 3 arguments. So let's start with 2 arguments. So the first thing we're going to say is the type of object that we want to create. So you can use make for several different operations. In this case, we're going to be talking about making slices. So in this example here, we're going to make a slice of integers. The second argument is going to be the length of the slice. So in this case, I want to start with 3 elements. So now let's just get some information about the slice that we created here. And we'll do that by dropping in a couple of print statements. So we'll print out the values of the slice, the length of the slice, and the capacity of the slice. So if I run this, no big surprise, it's zeroed out. So when I create a slice, everything gets set to the 0 value, which is what we always expect in Go to happen. Every time we initialize a variable, we expect it to be initialized to the 0 values, and that's true for slices just like it's true for primitives. When we ask for the length, we get a length of 3. When we ask for the capacity, that's also set to 3. Now we can also pass a third argument to the make function, and that's going to set the capacity. So keep in mind, the slice has an underlying array, and they don't have to be equivalent. So if we run this, we see that we've created a slice of length 3. It's got 3 elements in it, but the underlying array has 100 elements in it. So why would we do that? Well, the reason is because, unlike arrays, slices don't have to have a fixed size over their entire life. We can actually add elements and remove elements from them. So in order to show you an example of that, let me drop in another example here. And this is going to start with a slice of integers that starts with no elements in it. So if we go ahead and run this, we see what we expect. We see an empty slice, length of 0, capacity of 0. Now if I want to add an element to this slice, I can use the built-in append function. So this takes 2 or more arguments. The first is going to be the source slice that we're going to be working with. So I'm going to start with A, and I'm going to add an element to it. And in this case, all I want to do is add the number 1 to it. And then let's go ahead and print out the value of the slice, the length of the slice, and the capacity of the slice again. So if I go ahead and run this, we see that in the second operation, we have a value 1 stored in there. We have the length of 1, and notice the capacity is 2. So that's kind of interesting. What happened here is when we initialize the slice to the value A, Go assigned a memory location for the slice. And since it didn't have to store anything, it basically created an underlying array of 0 elements for us. As soon as we added an element, obviously it couldn't fit in a 0 element array. So it had to assign an array for us. So what Go does is it copies all of the existing elements, in this case nothing, to a new array that's got a larger size. So when we reassigned, it actually did create a new array. This one has a capacity of 2, and then it put the value 1 into that array. Now, when we're dealing with small slices like this, things are pretty cheap and pretty easy, even if you're resizing the array quite a few times. However, as things get very large, these copy operations become very expensive. And that's why we have that 3-parameter make function. That way, if we know the capacity is going to be somewhere around 100 elements, you can go ahead and start there, and that way, as you're appending elements and building up the slice, you're not constantly copying the underlying array around. Now, if you remember, when I said the append function can take 2 or more arguments, the reason for that is this is what's called a variadic function. So everything after the first argument is going to be interpreted as a value to append to the slice passed in the first argument. So if we have this example here, we're actually going to append the values 2, 3, 4, and 5 to the slice returned by A. So if we run this guy, we see that we get the elements 1 through 5 created there, and the length is 5, like we might expect, but now the capacity is 8. Now it's not fixed in stone how Go resizes the arrays, but generally what I've seen it does is once it fills up the underlying array with a slice, when you add the next element, it's going to create a new array, and it's actually going to double the size from the previous array. So if we start with an empty slice, we see that the array would initially be of size 0, then it'll go to 2, 4, 8, 16, 32, and 64 elements. So that's something else to be aware of. If you're just over one of those powers of 2, you can actually end up with a lot of memory consumed that you're never going to be using. So again, if you have the ability to come up with a decent first estimate, then that's going to be beneficial to you. Now, one common situation that you're going to run into is if you have a slice of elements and another slice of elements and you want to concatenate them together. So you want to have another slice created that has all of the elements of the first slice and all of the elements of the second slice. So you might want to do something like this. If I convert this over to a literal slice, you might want to run a command something like this. Well, this unfortunately is not going to work. If I go ahead and run this, you see that we're going to get Go complaining to us, and that's because the second argument to the append function has to have the type of the slice. So Go can only accept integers here. It can't accept a slice of integers. But we do have a way around this. So I don't know what it's called in Go. In JavaScript, they would call this the spread operator, where if you add 3 dots after the slice, it's actually going to spread that slice out into individual arguments. So if we run this, this is going to work, and it works exactly the same as if this weren't a slice at all. It's basically going to take the slice and decompose it into looking something like this. So these work exactly the same way, but it's a convenient feature to know about if you have slices and you want to concatenate them together. Now, some other common operations that you might do with slices are stack operations. So let's just say that we're treating our slice as a stack and we want to be able to push elements onto the stack and pop elements off of the stack and things like that. Well, the append function is going to allow us to push elements onto the stack, but how do we pop elements off? Well, we have a couple of different ways that we want to do this. If we want to do what's called a shift operation, which means we want to remove the first element from the slice, then we can do this operation here. And what this is going to do is it's going to create a new slice that starts at index 1, which is the value 2 in this example, and takes everything else from that. So if we go ahead and print out the value of b, we'll see that that has the elements 2 through 5. Now, if you want to trim an element off of the end, then you're going to have to use a different syntax here. So we want all of the initial elements, so we're going to start with a colon, and then we'll use that length operation, figure out the length of the slice, but remember, that's going to return a number that's too large. We actually want to remove an element off. So let's go ahead and do length minus 1, and this will have the values 1 through 4 in it. So it's pretty easy to remove an element from the beginning of the slice or the end of the slice, but what happens if you want to remove an element from the middle? Well, here things get a little bit hairy, because what we have to do is we actually have to concatenate 2 slices together. The first slice is going to be all the elements up to where we want to remove the element. So in this case, we can take the first 2 elements by doing a slice of A and passing in colon 2 for the slice that we want to create. Then we have to concatenate to that all of the elements after the index we want to remove. So in this case, we're removing that middle element. So we'll take from 3 on, and then we have to use this spread operation in order to spread things out so that the append function is happy. So let's go ahead and run this, and then get my syntax correct here. And now we see that we've got the elements 1, 2, 4, and 5. So we've successfully removed an element from the slice. Now you have to be a little bit careful here, because keep in mind, we're working with references to the same underlying array, because these are all slicing operations. There's one underlying array, and everything is being done on that underlying array. So just to show you the havoc that we've created here, let me go ahead and print the value of A out here, and then print the value of A out afterwards, and go ahead and run that. And you see we start out with the elements 1, 2, 3, 4, 5, like we might expect. We do our slicing operation, removing the element from the middle. We get 1, 2, 4, 5, which was what we might expect. But then when we print A out, things look a little weird, because we have that slice that B represents, which is 1, 2, 4, 5. Our 3 is completely gone, and 5 is duplicated. So this is something to be very sensitive about. If you're going to be removing elements from the inside of a slice, using a command like we have on line 10, make sure that you don't have any other references to that underlying array. Otherwise, you're going to get some unexpected behavior. So what do you do if you have a situation like this and you really, really need A to stay the same and you really, really need B to change? Well, unfortunately, we don't have the tools to work with this right now, because what we're going to need to do is use a loop to create a copy of that slice that doesn't point to the same underlying array, and then you can make the manipulation. So when we get to the looping section, we'll show you how to do loops, and then you'll have all the tools that you need in order to handle that situation. For now, the only thing I could say is beware of this behavior. And if you get into a situation like this, understand that you're going to have to do a little bit of research in order to make sure that your application responds correctly. Okay, so that covers what I want to talk about with arrays and slices. Let's head into a summary and review what we've talked about. Arrays and slices are very common in Go applications, and I think you're going to see them all over the place as you start to work more and more with the language. So I hope that this conversation has really helped you understand what arrays and slices are and some basics about how you can work with them. We started our discussion by talking about arrays, and we learned how they're collections of items with the same type. So you can't create an array that has strings and integers and things like that. All of the types have to be the same, but it does collect them all together. And as we start to get into conversations about looping and things like that, we're going to find how we get some very powerful tools that we can work with when we're basing our data on arrays and slices. They are fixed size, so when you create an array, you have to specify at compile time how big that array is, and it can never change. So you can't make them smaller and you can't make them larger. There are 3 different ways that we can declare an array. We can do the literal style like you see on this first line, where we're going to specify the number of elements, and then we use a literal that's going to initialize those elements. However, we do have a shorthand notation that uses 3 dots instead of that first size, and that's going to be a little bit more robust in your application design, because if you run into a situation where you need to add another literal, you don't have to remember to update the size of the array. It's going to update automatically. We also have this third syntax where we can declare a zeroed out array. In this case, we're going to declare an array of 3 integers. Each one of those integers is going to start with the value 0. We also talked about how arrays are zero-based. So we're going to be counting from the head of the array. So the first element in the array has the index 0, the second element has the index 1, and so on. So in this example, if we ask for the index 1 of array A, we're going to get the value 3 out. We have the len function that's going to return the size of the array in case you need to know that some other place in your application, and you want to have a way to be able to handle that robustly that's not relying on the fact that you know at design time how big that array is. You can use the len function to interrogate the size of the array. Anytime you're moving the array around, it's going to copy the underlying data. So if you have a 3-element array and you assign that to another variable, all 3 elements are going to be copied to a new location in memory, and you're going to be working with an independent copy. So that can cause some unexpected behaviors, because if you change that copied array and you expect the changes to be reflected back in the initial array, that won't happen. And it can be very expensive because all that memory has to be allocated a second time. Then we moved on to discuss slices and how they're very similar to arrays. As a matter of fact, they're backed by an array. So every slice that you see under the covers, Go has an array that's holding all of that data for you. There are several creation styles. We saw that we can create a slice by slicing an existing array or another slice. We have the literal style that we can use, which is very similar to the array literal, except for we just leave those 3 dots out because the size of the slice is dynamic, and so it can be determined at runtime. We also saw how we can use the make function. So if we pass 2 arguments to the make function, the first is going to be the type of slice that we want to create. So in this example, we're going to create a slice of integers, and the second parameter is going to determine the length and the initial capacity of the slice. If we need a capacity that's different than the initial length, then we can pass a third parameter into the make function, and that's going to allow us to specify a capacity independent of that initial length. The len function returns the length of the slice itself, whereas the capacity function returns the length of the underlying array. So if, for some example, you want to control the resizing of the slice, you can go ahead and do that, and use that capacity function to understand when you're starting to get to your limits. You can also use the append function to add an element to the slice. Now what that's going to do is it's going to take in a parent slice, and it's going to take in 1 or more elements to add to that slice. Now through the course of that append operation, you can add elements that exceed the capacity of the underlying array. If that happens, then you are going to trigger a copy operation, and all of those elements are going to have to be copied to a new location. So be aware of that. If you're dealing with large slices of data and you end up resizing a lot of times, your application performance can suffer. You might want to think about using that 3-parameter make function in order to set the capacity of the slice close to where you need it to be. When you're passing slices around in your application, keep in mind that assigning a new value to an existing slice actually points to the same underlying array. So if you manipulate the slice in one location, it's actually going to affect all the other slices that are pointing to that same underlying data. So we talked about an example where we created a slice and removed the middle element out of it, and we saw how that actually affected the initial slice and could cause some behavior that we weren't expecting. I want to complete the discussion I started in the last video by talking about the 2 remaining collection types that are available in Go, and those types are maps and structs. So we'll start our discussion by talking about maps. We'll talk about what they are, how we can create them, and then how we can manipulate the data within the maps. Then we'll move on to the struct data type. We'll talk about what they are, how we can create them. Then we'll move on to the naming conventions that we're going to have to be aware of as we're working with structs. Then we'll talk about a concept called embedding and how we can use that to have a struct that we're creating inherit a lot of functionality from a base struct. Then we'll finish our discussion of structs by talking about a concept called tags and how we can use tags to provide some additional information about the fields within our structs to help the consumers of objects created from the structs get additional information about how that field is intended to be used. Okay, so let's begin our discussion by talking about what maps are and how we can use them. So the first thing that we're going to need to get our heads around when we're talking about maps is what exactly a map is. And I think the easiest way to show you what a map is by showing you a map. So we have an example here of a variable called state populations, and this represents a map of U.S. state names over to the population within those states. So what we see here is a map is going to take some kind of a key, in this case the state names, and it's going to map that over to some kind of a value, in this case the population of that state. So what this provides us is a very flexible data type when we're trying to map one key type over to one value type. Now there's a couple of constraints we're going to have to keep in mind. As you can see up in the declaration on line 8, we're going to map one key type to one value type. So all of the keys in this map have to be of type string, and all of the values have to be of type integer. Now we can use a lot of different types for the keys, and we can use any type for the value, but when we declare a map, that type has to be consistent for every key value pair within the map. So if we run this, we can see an example of what a map looks like when we print it, and it's not the best output in the world, but we can get an idea of what's going on. So we see that we get the key value pairs printed out, so we get California, Texas, Florida, New York, Pennsylvania, Illinois, and Ohio. So one thing that I just alluded to is that we have a lot of options with the key type, but we don't have an infinite number of options. So the basic constraint on the keys when you're creating a map is they have to be able to be tested for equality. Now most of the types that we're working with can do that. So booleans can be tested for equality, all of the numeric types, strings, pointers, interfaces, structs, arrays, and this thing we haven't talked about called channels. All of those can be tested to see if one instance of, for example, a string variable is equivalent to another one. However, there are some data types that cannot be used for equivalency checking, and those are slices, maps, and other functions. So for example, if we create a map called M, and we'll make that a map of, say we want to map slices of integers over to strings, and we'll use the literal syntax for that, and then we print that out, then you would expect a map to print out. But in fact we get an error because we've got an invalid key type because a slice cannot be a key to a map. However, if we had an index here, then it turns it into an array, and now we do get a successful printout. Of course the map is empty, so we don't see anything, we just see this empty map right here, but we were successfully able to create the map because an array is a valid key type, but a slice is not. So what are the different ways that we can create a map? Well, you see the first way here. This is the literal syntax, and this is going to probably be the most common way you're going to see maps created. So we just need to declare the type of the map, and we're going to do that using this syntax that we see here on line 8, where we're going to start with the map keyword. In square brackets, we're going to list the type of the key, and then after the square brackets, we're going to list the type of the value. Another way that we can do this is we can use the built-in make function again. Now we first saw the make function when we were talking about slices, but we can use that once again here. So if I copy this variable up here, and I set this equal to the result of calling the make function, and we're going to tell it what type of map we want to make. So we're going to use the map keyword again, the key is type string, the value is type integer, and now we can go ahead and remove this colon, and if we run this, we have to remove our M again from the print statement. Now if we run it, we get the same value printed out. So this is a common way that you can work with maps if you don't have, at the time that you're declaring the variable, the entries that you're going to want to put in it. So for example, if you're populating the map within a loop, you might use this syntax. Now another option that you have with the make is it will take a second parameter. So if I run it like this, then that works. However, I wasn't able to find the intention for this. So this is available, but it doesn't seem to affect the length of the map that's created. The map is always going to be the length of the number of elements in it, but it might have some effect under the covers. If you find out what that's for, please leave a comment down below so that I can learn along with you. Now let me go ahead and remove this because I don't know what it's there for, and I haven't seen that very commonly used, and run this again, and we can see that we're back to where our map used to be. Now, how are we going to manipulate the values in our map? Well, the first thing that we can do is we can pull out one single value from the map by using the square brackets and typing in the value of the key. So the key can be provided either as a variable or, as I'm doing here, as a literal. So if I go ahead and run this, we see that we get the population of Ohio is 11.6 million people. So we can interrogate the values of our map using this syntax here. We can also add a value to our map using a very similar syntax. So if we call on the state populations variable and I add a key, in this case let me add the next largest state, which is Georgia, and it, as of 2016, had a population of 10,310,371. Now I can pull that value back out, run this, and we see that we get that value printed out of our map. If we print the entire map out, we see right here Georgia gets added in here. Now, something you might have noticed, let me do this. I'm going to copy this print line here, put it above where we added the Georgia key, and notice the ordering is different. And this is going to be a very important thing to keep in mind as you're iterating through maps later on. The return order of a map is not guaranteed. So even though we declared California, Texas, Florida, New York, Pennsylvania, Illinois, Ohio, and then added Georgia, this is not like a slice. A slice or an array would return those elements in exactly the same order we provided them. In a map, everything is stored in a way that cannot guarantee the order upon returning. So even though we just added one entry here, it completely changed how everything was organized within the map, and we get a little bit different output. Now, another thing that I want to show you is that we can delete entries from a map. So we can do that using the built-in delete function. The first is the map that we want to delete from, and then we need to provide the key that we want to delete. So if we go ahead and delete Georgia back out, it wasn't there very long, but if we run it, looks like I need to add my S here. Now if we run it, we see that Georgia is no longer part of our map. So we can add by just calling on the map, providing a new key and value. We can delete using the built-in delete function, and we can interrogate a value from the map using those square brackets. Now, an interesting thing about deleting is if I ask for the value of that key again, what do you think I'm going to get? So we see here in the output, Georgia is no longer part of the map. So you might expect some sort of error to be raised. Well, in fact, if I run this, we get the value 0 out. Now that should cause you some concern, because does Georgia have a population of 0? Or is it missing from our map? Did I just misspell the key? What's going on? So for example, if I fat finger Ohio and I forget the I and run this, I get a value of 0. Well, did everybody move out of Ohio? What happened? Well, with what we know right now, there's no way for us to really know. So there's another way that we can interrogate our map, and that is using what's called the comma OK syntax. So with doing what we know right now, we're basically doing this. We're calling state populations, and we're asking for the key Ohio, and I'll continue that misspelling, and then we're printing out the value of that population variable, and we get the value 0. Well, we can also add an optional comma OK here, and when we do this, let's go ahead and add that OK variable to the output and see what that's going to do. So notice that this prints out the value false. So the OK is false if the key was not found within our map, but if we add the I back in and correct our spelling, we see that we get the value true out. So if you're in a situation where you're not sure if the key is in the map or not, then you can use this comma OK syntax. As a matter of fact, if you just want to check for presence, then we can use that write-only operator again in order to throw away the actual value, and then we just get the OK variable printed back out. Now there's nothing magic about the variable name OK, but it is conventional to use OK in your Go programs when you're using it for this kind of a test. The next thing that I want to show you about maps is we can in fact find out how many elements are in them. So we can do that using the built-in len function. So if I go ahead and run that, we see that we get the value 7, and we have, let's see, 1, 2, 3, 4, 5. Yep, we have got 7 states declared in our map right now. So if we added another state back in, then the length function would return 8. The other thing that's interesting to know is that just like slices, when you have multiple assignments to a map, which is especially important when you're passing maps into functions, the underlying data is passed by reference, which means manipulating one variable that points to a map is going to have impacts on the other one. So I can demonstrate that by creating another variable called SP and set that equal to state populations. And then let's go ahead and delete poor Ohio out of SP. It always seems to get left out. And then we can print out SP and print out state populations. So if I run this, we see that in our first result, we don't have the entry Ohio anymore, and in our second print statement, which is the original map, Ohio's been removed from there as well. So if you start passing maps around and you start manipulating the data within that map, keep in mind you can have side effects on the calling functions or any other place where that map is referred to, because manipulating the map in one place is going to have impacts on every other place it's used. So the final collection type that I want to talk about today is called a struct. Now at first, you might not think of a struct as a collection type, but go with me on this. If I drop in an example, we see here an example of a struct. Now I'm in kind of a Doctor Who frame of mind today, so we're going to run with an example that's talking about some information about one of the doctors from Doctor Who. So if I go ahead and run this, we can see that we're getting information on the third Doctor. The actor's name is John Pertwee. We see some of his companions listed out here. So the reason I call this a collection type is look at the declaration of the struct on lines 7 through 11. What we have here is a list of field names. So we've got number, actor name, and companions as field names, and then a type associated with that field. So the doctor number is an integer, the actor name is a string, and the companions is a slice of strings. So what the struct type does is it gathers information together that are related to one concept, in this case a doctor, and it does it in a very flexible way, because we don't have to have any constraints on the types of data that's contained within our struct. We can mix any type of data together, and that is the true power of a struct. Because all of the other collection types we've talked about have had to have consistent types. So arrays always have to store the same type of data, slices have the same constraint, and we just talked about maps and how their keys always have to have the same type, and their values always have to have the same type within the same map. When a struct, we can have our fields describe any type of data that we want. So we can have structs that contain other structs, anything that we want. So while in a lot of ways structs are the simplest type of collection that we're going to be talking about, they're also one of the most powerful. So we see down here in the main function how we can create a struct, and I'm using the declaration syntax where I'm using named fields. So we're going to create a variable called aDoctor, and we're going to use this literal syntax. So we list the type of the struct, doctor, we use the curly braces like we do with every other literal definition, and then I have a list of the field names, colon, and the value. So number, colon 3, actor name, colon John Pertwee, and then companions is set equal to this slice of strings. Now notice that when I'm setting something equal to a slice, I do actually have to tell Go what kind of collection type I'm initializing for that. And then down here on line 23, I go ahead and print the entire value of the struct out, and you see that I get the values printed out. I see 3, John Pertwee, and then the 3 companions that John Pertwee had in his time as the doctor. Now if we want to interrogate one value from a struct, then we're going to use what's called the dot syntax. So if we ask for the actor name of this struct, then we're going to put a dot after the variable name, put in the field name, and when we run this, we see that we get John Pertwee out. So we can work with the struct as a whole, or we can start drilling down. As a matter of fact, we can drill down through the structure. So if we ask for the companions, we can get that out, certainly. But this is a slice like any other slice. So if I just want the second item in the collection, I can get Joe Grant out by interrogating the slice that gets returned by asking for the companions field. Now another way that we can instantiate our structs is using what's called the positional syntax. So here I'm listing the field names, but I don't have to. So if I go ahead and take these out and take this out, so I print the entire struct out, then I get exactly the same result as I got the first time. Now this is valid Go syntax. I would encourage you not to use it though. And the reason for that is it can become a maintenance problem. So for example, let's just say that this is our struct and this is checked into source control and everybody's happy with it. But then let's say we have a change request come and we're going to add a list of the episodes that each doctor appeared in. So that's going to be another slice of strings, and that gets added right here. Well, if we use the positional syntax and try and run this, we've got a problem, because Go doesn't know how to map the fields that we provided into the initializer, because there's 3 values provided in the initializer and there's 4 values in the struct. So we have to find every place that we have one of these declared with the positional syntax, and we have to add, for example, a placeholder or populate it or something. So we go ahead and run this, and everything's working again. But now, what happens if another change comes along and somebody does this? Now they've changed the order of the fields. When we run this, everything looks fine, but when I ask for the doctor's companions again, I get an empty slice, because the positional syntax requires the fields to be declared in the correct order. Much better for us to go ahead and add in the field names. So let me drop those in real fast here. Now when I run this, I get the expected results out. And notice with the field name syntax, I don't even have to have it in the same order as they're declared in the struct. Go is going to figure out how to map the data from the initializer over into the object that's created by using those field names. The other advantage that I have is if I don't have any information about the episodes at this point in my program, I actually can ignore the fact that that field exists. And what this means is I changed the underlying struct without changing the usage at all, which makes my application a little bit more robust and change-proof. So, while it is possible for you to use the positional syntax, I would strongly recommend you do not use it unless you've got a very short-lived struct. We'll talk about anonymous structs here in a second, and in those situations, positional declaration might make sense because that struct is not going to live for very long. However, I would strongly recommend anytime you're taking the time to declare a type like we're doing here on line 7, then you're generally going to be better served by using field names explicitly instead of the positional syntax. Okay, the next thing I want to talk about are naming conventions. So as you can see here, I've got my type declared as doctor with a capital D and the fields declared as lowercase. So the rules in this situation follow the rules for any other variable in Go. If we start with a capital letter, it's going to be exported from the package. If we start with a lowercase letter, it's going to be internal to the package. So in this case, I can work with all of the fields because I'm declaring the doctor type in my main package. And so my main function, which is also in the main package, has access to it. However, nothing in any other package would have access to this. So it would be able to see that there is a doctor struct, but it wouldn't see any field names. So if I did want to publish these out so anything can use them, I would have to go ahead and capitalize these field names. Of course, I'll have to capitalize them in my declaration as well. And then when I run, I get the exact same result that I got up before, except for I've got to change this variable as well. Go ahead and run that, and I get the expected result out. So generally, we're going to follow the same convention as we do with any other variable. Uppercase is going to export, lowercase is going to import. You should use Pascal casing and camel casing. You shouldn't have underscores and things like that in your field names or in your struct names. Now, if you notice here on line 7, I have explicitly created a type called a struct. And that's going to be a very common way that you're going to see structs used. So you're going to define a type, and then everywhere you need to use that struct, you can just refer to it by its type. But we don't have to do that. And there are some situations where you might see a program like this. So on line 8, we're declaring what's called an anonymous struct. So instead of setting up a type and saying doctor, and that's going to be a struct, and that's going to have a single field called name that's going to take a string, we're condensing all of that into this single declaration right here. Now, I can't use this anywhere else because it's anonymous, and so it doesn't have an independent name that I can refer to it, but I can certainly use this just fine. So let me go ahead and delete this, and then notice I'm using the initializer syntax right here. So we got 2 sets of curly braces. It's very important to remember what each one is doing. So the first set of curly braces is paired to the struct keyword, and it's defining the structure of the struct. The second is the initializer, and it's what's going to provide data into the struct. So if we run this application, we see that we do get the struct with the value John Pertwee printed out, and everything's going to work just fine. Now, when are you going to use this? This is going to be used in relatively few situations. Basically, you're going to use this in situations where you need to structure some data in a way that you don't have in a formal type, but it's normally only going to be very short-lived. So you could think about if you have a data model that's coming back in a web application and you need to send a projection or a subset of that data down to the client, you could create an anonymous struct in order to organize that information so you don't have to create a formal type that's going to be available throughout your package for something that might be used only one time. Now, unlike maps, structs are value types. So if I take this example here, and let's just use the same basic manipulation that we've been doing with all of these collections. So I'm going to create another struct, and I'm going to assign it to the value of my current struct, and then I'm going to manipulate the value of that name field. So I'm going to create another doctor called Tom Baker, and then let's see what happens when we print both of these doctors out. So as you can see, even though I copied another doctor from a doctor and changed the values remain independent. So a doctor still has the name John Pertwee, another doctor has the name Tom Baker. So unlike maps and slices, these are referring to independent data sets. So when you pass a struct around in your application, you're actually passing copies of the same data around. So if you've got structs that are very, very large, keep in mind you're creating a copy every time you're manipulating this. Now, just like with arrays, if we do want to point to the same underlying data, we can use that address of operator. And when we run this, we have in fact both variables pointing to the same underlying data. A doctor is the struct itself. Another doctor is a pointer to the struct. So when we manipulate its name field, we're actually manipulating the name field of the a doctor struct. The next thing that I want to talk to you about in Go is a concept called embedding. Now, you may have heard in your research on the Go language that Go doesn't support traditional object-oriented principles. So, for example, we don't have inheritance. And oh my goodness, how am I going to create my program if I don't have inheritance available? Well, let me show you what Go has instead of an inheritance model. It uses a model that's similar to inheritance called composition. So where inheritance is trying to establish the is-a relationship. So if we take this example here, if we were in a traditional object-oriented language, we would want to say that a bird is an animal, and therefore a bird has a name, a bird has an origin, a bird has also bird things like its speed and if it can fly or not. Go doesn't support that model, but instead it supports composition through what's called embedding. So right now we see that animal and bird are definitely independent structs. There's no relationship between them. However, I can say that a bird has animal-like characteristics by embedding an animal struct in here like this. So I've just embedded the struct itself. I haven't provided a name. Now if I did something like this, then I would have a named field in the bird called animal. But I'm not doing that, I'm doing this. So I'm just saying embed the animal struct right into the bird struct. Now how can I use this? Well, let me drop in a new main function here, and then you can see. So I'm creating an instance of a bird, and then I'm initializing the variables. So name is going to be emu, origin is going to be Australia, the speed is 48 kilometers an hour, and it cannot fly. So if I print this out, I see that other than a little bit of a strange syntax with that inner type, I see that I have all of my fields defined. As a matter of fact, I can come in here and dig into any one of those animal fields, and everything works exactly like I would expect them to. So it kind of looks like bird is inheriting the properties of animal. But really what's happening here is there's some syntactic sugar. Go is handling the delegation of the request for the name field automatically to the embedded animal type for you. So if you try and pass these around and look to see if the bird is a type of animal, it is not. Bird is still an independent struct that has no relationship to an animal other than the fact that it embeds it. So it's not a traditional inheritance relationship where a bird is an animal. Instead, it's a composition relationship, which is answering the question, has a. So a bird has an animal or has animal-like characteristics, is how we would say it in this example, but it is not the same thing as an animal. They cannot be used interchangeably. In order to use data interchangeably, we're going to have to use something called interfaces, which we'll talk about a little bit later. Now we can see in this example that if we declare the type and we initialize the variables afterward, everything's pretty clear. We can just treat all of the fields as if they're owned by the bird struct, and we don't have to worry about the internal structure of the struct, and that's very intentional. However, if we're going to use the literal syntax, we do have to know a little bit about the bird's internal structure. So let me drop in this code here, clean up our formatting a little bit, and then remove these lines here. So this is declaring exactly the same object. We're going to have an emu from Australia. The speed is actually going to be 48 kilometers an hour, and can fly is going to be false. But notice what I have to do here. I have to explicitly talk about the internal animal struct. So when I'm working with the literal syntax, I have to be aware that I'm using embedding. But if I just declare the object and manipulate it from the outside, I don't have to be aware of it at all. Now, when should you use embedding? Well, I will say, generally, if you're talking about modeling behavior, embedding is not the right choice for you to use. When we get into methods, we will see that embedding will allow behaviors or methods to carry through into the type that has the embedding. However, the fact that we can't use them interchangeably is a very severe limitation. Generally, it's much better to use interfaces when you want to describe common behavior. So when is embedding a good idea? Well, if you're authoring a library, for example, and let's just say you're making a web framework and you've got a very sophisticated base controller. In that case, you might want to use consumers of your library to embed that base controller into their custom controllers so that they can get useful functionality out of it. In that case, you're not talking about polymorphism and the ability to interchangeably use objects. You're just trying to get some base behavior into a custom type, and in that case, embedding makes sense. The last thing that I want to talk about with structs is a concept called tags. So let me just drop in another example program here that we can work with. This is a simpler version of what we had before because we don't need two structs for this conversation. So we're just going to have a simple animal struct with the name and the origin fields. And then what I want to do is I want to add what's called a tag in order to describe some specific information about this name field. So let's say, for example, that I'm working with some validation framework. So let's just say that I'm working within a web application and the user's filling out a form, and two of the fields they're providing are the name and the origin. And I want to make sure that the name is required and doesn't exceed a maximum length. So I can do that with a tag that looks something like this. So the format of a tag is to have backticks as the delimiters of the tag, and then we have these space delimited key value pairs. So my first field is going to be required, so I'm going to say that the name field is required. And then I've got a max length argument, which in this case is set to 100 characters. So the value of the tag is arbitrary. You could actually put any string that you want in here, but this is the conventional use within Go. We're going to use space-delimited subtags, and then if you do need a key-value relationship, then you're going to use a colon to separate the key and the value, and then the value is typically put in quotation marks. So now that we have this, how do we get at it? Well, the way that we're going to get at it is using Go's reflection package. So there's no straightforward way from an object to get at the tags of a field. You have to use reflection in order to get that. But fortunately, Go makes this pretty easy. So the first thing that I need to do is I need to get the type of an object that I'm working with. So I get that using the reflect package's type of function, and I have to pass in an object to this. So I will just initialize an empty animal to get at that, and then I can grab a field from that type using the type's field by name method, and then passing in the name. In this case, I want the name. And now I can get at the tag by asking for the tag property of the field. So if I run this, we see that I do in fact get that tag out. Now what do I do with that? Well, that's really up to my validation framework to figure out. All tags do is provide a string of text, and something else has to figure out what to do with that. So this tag's value is meaningless to Go itself. We're then going to have some sort of a validation library that's going to have to parse this, figure out that yes, required is part of the tag, and then it's going to have to decide, well, if required is there, then I'm going to apply this logic, making sure the string is non-empty or whatever makes sense in our use case. Okay, so that finishes up what I have to talk about with maps and structs. Let's go into a summary and review what we've talked about. In this video, we talked about the two remaining collection types that are available in Go. We talked about maps and we talked about structs. Now, when we talked about maps, we learned that they are collections of value types that can be accessed by keys. They can be created as literals or via the make function, and members are accessed via the square bracket key syntax. We can check for the presence of an element within a map using this OK syntax. So we can ask for the value, add a OK, and what the map is going to return is the value type as well as a Boolean that's going to indicate if the value was found or not. Now, if the value wasn't found, your value variable is going to be the 0 value of the value type in that map. So for example, if you've got a map of strings to strings, and the element isn't found, you're going to get an empty string returned out. If you've got a map of strings to integers, for example, you're going to get the value 0. If you have multiple assignments to the same map, they all point to the same underlying data. So they're what are called reference types, which means that if you manipulate the data in a map in one location, any other variables that are pointing to that same map are going to see that change as well. We then went on to talk about the struct type and how they're a collection of disparate data types. So whereas arrays and slices and maps are all collecting the same data type together, a struct is unique in that it collects any type of data together. So you've got a common field name, but those fields can point to any valid data structure within Go. They're keyed by name fields, which generally follow the syntax of any valid variable, including whether they're exported or not. So if you capitalize the name of a field, then that's going to be exported from the package. If you leave it lowercase, then that's going to be kept internal to the package. They're normally created as types, but we can create anonymous structs if we need to. And again, common use cases for this are very short-lived structs, such as generating a JSON response to a web service call that's only used one time. Structs are value types. So if I assign a variable to an existing struct, then all of the struct's values are going to be copied over to create a brand new struct. So if I manipulate a struct in one location, it's not going to affect any other variables in your application. We don't have an inheritance system within Go, but we can use composition using what's called embedding. So when we want to embed one struct within another, we just list the type of the struct and we don't give it a field name. Go is then going to automatically interpret that for us and delegate any calls for fields or methods in the containing struct down to the embedded struct if that top-level struct doesn't contain a member with that name. We also learned a little bit about tags and how they can be added to struct fields to describe that field in some way. So there's a lot of different use cases for this. The JSON package uses this to provide ways to map field names from Go field names, which are typically uppercase, to follow JSON conventions, which are typically lowercase. We also saw that we can use this, for example, to pass information into a validation framework, and that framework could generate errors if we need fields to be required or have rules about their length or things like that. I want to start a discussion about the tools that Go makes available to control the flow of execution in our applications. In today's video, we're going to focus on two of these tools, the if statement and the switch statement. We'll start our discussion by talking about if statements, and we'll talk about all of the different ways that we can use them in our applications. And we're going to specifically focus on the various operators that are often associated with working with if statements, and we'll go through what those are and how you can use them. And then we'll talk about the relatives of the if statement, and those are the if-else statement and the if-else-if statement. We'll then move on to talk about switch statements, and we'll start that conversation with some simple use cases for switch statements. We'll then talk about cases with multiple tests, how we can fall through from one case to another in our switch statements, and then we'll talk about this special version of a switch called a type switch. So let's go ahead and jump in and start learning about if statements. In order to start our discussion about if statements, I want to start as simply as we can. So if you look at this application here, it's got just about the simplest if statement that I could come up with. So we're going to start with the if keyword, as you see here on line 8, and then we're going to have an expression that generates some kind of a Boolean result. And that's actually where we're going to spend a lot of time when we're talking about if statements, is how to generate these Boolean results. In this case, I'm just using the literal true, which is the simplest Boolean result that we can come up with. And then inside of these curly braces here, I've got the code that's going to execute if that Boolean test returns true. So in this case, since we're using a literal true, then the test is always going to pass, and when I run this application, I see that I get this test is true printed out in the results here. If I change this to a literal false, then we see that we don't get any output from the application because the code inside of the curly braces is not executed. Now, one thing to keep in mind if you're coming to Go from another language is you may be expecting this to be valid syntax. Well, if we try and run this, we actually are going to get a syntax error because one of the design decisions that was made with Go is that you are never allowed to have a single line block evaluate as the result of an if statement. So you always have to use curly braces even if you only have one line to execute. Now this style of if statement has the Boolean test right here, and that's the only thing after the if clause. There's actually another style that's very commonly used in the Go language, and that's what I would call the initializer syntax. So as you see here on line 17, we've got a call into a map that's pulling out the value from a map and is pulling out the OK variable. And then notice I've got this semicolon and then the Boolean result listed here. So this part here, this first part of the if statement, is the initializer. So the initializer allows us to run a statement and generate some information that's going to set us up to work within the if block. So in this case, I'm generating a Boolean result by interrogating the map, and then I'm using that as the test to see if the code inside the if block should execute or not. I also have access to the pop variable that I'm creating right here inside of the if test, and that variable is going to be scoped to the block. So if I execute this, you see that I get the population of Florida printed out, no problem there. If I try and work with that variable outside of here and print it out again, I'm going to get an undefined error because the pop variable is only defined within the scope of that if statement. The next thing that I want to talk about with if statements are the comparison operators that we have. I mean, obviously, as long as we can generate pure Boolean values, things are going to be pretty simple, but that's of pretty limited benefit because in a lot of applications, we need to do some kind of a comparison in order to determine if the branch should execute or not. So let me drop in this example here, and let's just say that we're building some kind of a number guessing game. Now, to keep things as simple as possible, this is going to be a pretty simple number guessing game because we're going to hard code the value that we're going to guess, and we're going to hard code our guess. So we're not going to have a user interface involved here at all, and we're not going to randomly generate the number. That way it's very clear what the application is doing. So right now what we have is we've got the number that we're going to try and guess, we've got our guess here on line 9, and then we've got a couple of tests. So in line 10, we're checking to see if the guess is less than the number. So this is the first comparison operator that we're looking at. This is the less than operator. We also have the greater than operator and the equality operator. So if we run this with the guess of 30 and a number of 50, we're going to get the value too low printed out because this first test evaluates to true and the second and third test evaluate to false. If I change my guess to 70 and run, then the second test evaluates to true and the first and third evaluate to false. And as you might expect, if I put in a guess of 50 and run this, then I finally got it. So this is the basics of a number guessing game. All you need to do is wrap this in loops, which we'll talk about in a future video, and add a little bit of a user interface, and you've got your first game written in the Go language. Now there are some other operators that we have available, and it's a little hard to justify getting them into this example, so I'm just going to go ahead and dump them here, and then we can take a look at them. So this first test is called the less than or equal operator, so it's going to check to see if number is less than or equal to guess. The second is the greater than or equal to operator, and the third is the not equal operator. So if I go ahead and run this, you see that We are less than or equal to because we're exactly on the number. We are also greater than or equal to, and we fail the not equal to test. So we get true, true, false printed here. If we go with 30 again, we're going to get false, true, true. And if we go with 70, we're going to get true, false, true. So these are the 6 different comparison operators that you're typically going to use in your applications. And these work with all numeric types. They don't, however, work with things like string types. So if you're going to work with string types, typically what you're going to work with is the equality operator or the non-equality operator. And that goes for any kind of reference type as well. Now, the next thing that I want to do in this example is add in some kind of simple validation. So if you imagine that we've got some kind of a simple user interface where the user is asked to enter a number on the keyboard, and then we're going to use that as our guess, then we're going to need some way to validate that number to make sure that, for example, they don't enter -5. So to do that, we can add another logical test, but we can also combine multiple tests together using what are called logical operators. So let me drop this code in here, and you can see our first logical operator. So this code here is conducting 2 tests. It's checking to see if the guess is less than 1, or if the guess is greater than 100. And if it is, then we're going to print out a message here. We can also put a guard around our actual game code, checking to see if the guess is greater than or equal to 1, and this is the AND operator, less than or equal to 100. So this first test case is going to execute if the guess is out of range. So if we enter -5, for example, then we're going to run this, and we see that the guess must be within 1 and 100. If we enter a number that's within range, then everything executes like we expect it to, and this code on line 11 doesn't execute. So this first operator here is called the OR operator, and this is checking to see if the test on the left is true or the test on the right is true. So obviously we can't have the guess less than 1 and greater than 100 at the same time, but one or the other could be true, and if one of those is true, then we're going to have an invalid guess, and it makes sense to print out a message to the user saying that. This other operator that we see here is called the AND operator, and it evaluates to true if both the test on the left and the test on the right evaluate to true. So if we had a guess, for example, of 105, then this code is going to evaluate to true because it is greater than or equal to 1, but this code is not because 105 is not less than or equal to 100. So with an AND test, both cases have to be true, unlike an OR test where only one of the two has to be true. So a guess of 105 is going to print out our error message, and it is not going to execute the code within this if statement here. The other logical operator that we have is called the NOT operator, and what that's going to do is it's going to take a Boolean and it's going to flip it to the other side. So if I take, and just as a simple example, if I take and print the value true out, then we're going to get the value true printed out here at the end of our program. If I put the NOT operator, which is just an exclamation point, and run that, then the true becomes false. Similarly, if I put this in front of a false, the false becomes true, and I can just prove that false is really false by taking that away, and false is false. So those are the 3 logical operators that we have. We've got the OR operator, which is the double pipe that you see here on line 10. We've got the AND operation, which is the double ampersand, which you see here on line 13. And then we have the NOT operation, which reverses a Boolean result, and that's done simply using the exclamation point. The other interesting thing to know about working with logical operators is a concept called short-circuiting. So in order to show you that, I'm actually going to have to jump ahead and add a custom function here, and we haven't talked about this, so let me just give you as simple of an explanation as possible. So I've got a function down here between line 27 and 30 called return true that's going to return a Boolean result. Now in order to make sure that we know that it executed, I'm printing out returning true here, and then I am returning the true value. So what happens when we call this function is it's just going to be replaced with the Boolean true in our application code. Now up here in line 10, I've changed our OR test to include this return true. Now this doesn't make sense in our demo example, but I'm doing this just to show you how this works. So in this case, we're ORing 3 tests together. So what's going to happen is Go is going to evaluate these guys, it's going to generate a result, and it's going to take that result and it's going to OR it against this guy. So basically it's going to evaluate all of them, and only one of those has to be true in order to generate a validation message. So as you might expect, if we run this like this, we're going to get returning true because the guess is not less than 1. So we're going to check this value, this returns true, and so we're going to evaluate if it's greater than 100. None of those are true, so our OR statement fails, and then we're going to drop down and we're going to execute this code down here like we might expect. If we generate an invalid value, so if we put a -5, Then, well, let's just run it and we'll see what happens. So if we run this, we get the validation message. The guess must be within 1 in 100. Well, that's okay, but what happened to our return true? If you remember, this function is supposed to print returning true out, and it didn't. So what happened? Well, what happened is a concept called short-circuiting. So as soon as one part of an OR test returns true, then Go doesn't need to execute any more code. It already knows that the OR test is going to pass. So it does what's called short-circuiting, which basically means it's not going to evaluate any other part of the OR test. It's just going to move on and say, well, the OR test passed, and therefore everything works. So in this case, since guess is less than 1, there's no reason for Go to evaluate these two tests here. So since this test is a function call, it doesn't even execute that function. Now, if we go the other way and we go out of range high, then this is going to return false. This is actually going to return true because it's hard-coded, and actually Go isn't even going to evaluate this because this is going to return true. However, this value is going to fail this test here. So if we run this, we see that now we get returning true printed out. So this is a concept called short-circuiting. Go is going to lazily evaluate the logical tests that we put in here. So when we give it -5, since it doesn't need to evaluate anything after this first test, it doesn't. So any function executions are not going to be evaluated. The same thing happens for an AND test. If one of the parameters returns false, then we're going to get a short-circuiting here. So if we get into a situation where this is false, Go will not even evaluate this test here. So for example, with the -5, when Go evaluates this, it sees that the guess is not greater than or equal to 1, so the AND test has to fail because both sides of an AND test have to return true in order to work, and so Go is going to exit early and it's not going to execute this code. So for the next thing that I want to talk about, I want to actually drop back into our baseline for our test here. And I want to talk a little bit about these two if tests. Now this code obviously works, but it's a little bit ugly, right? Because we have this logic here, guess is less than 1 or guess is greater than 100, and then we have this expression here, and this is exactly the opposite. So this is basically saying, well, if it's not less than 1 or greater than 100, then do this other thing. So while this code is perfectly fine, it becomes a little bit of a maintenance nightmare because really our intent is that we want to execute either this code or this code. So the way we can do that a little bit more elegantly in Go is by taking out all of this and just putting in the keyword else. So what's going to happen in this situation is it's going to evaluate the logical tests. If these tests return a Boolean true, then we're going to print this. Otherwise, we're going to execute this block here. So in this case, if we run this, we see that we get the value too low, and our logical tests down here on line 21 execute. If we put in the value -5, however, then we get the same behavior that we had before, but our code is a lot cleaner and a lot more clear as to our intent. Now related to that is the situation where we have multiple tests that we want to chain together. So let me paste in another permutation of our little game. And in this case, I've actually split out the validation logic. So I want to check if it's less than 1, I want to print out one message. If it's greater than 100, I want to print out another message. Otherwise, I've got a valid value. And to do that, I'm using this else if clause. So basically what this is doing is it's taking an if test, and then it's chaining on another if test if this fails. And so what Go is going to do is the first logical test that passes is going to be executed. Otherwise, it's going to drop down to the else clause. So with a guess of 30, we would expect our else clause to fire. So if we run, we see that in fact it does. If we put in a value of -5, then we would expect this first statement to run, and it does. And if we put in a value that's too high, then we see that we get the second validation message printed out. And those are the three different ways that we have to create if statements. So we've got the simple if statement that's just if, and if that evaluates to true, then the statements inside of the curly braces are going to execute. We've got if else, so we're either going to execute the first set of code or the second set of code. And then we have the if else if, which we can chain together with else in order to have very complicated branching so that we can have multiple code paths execute depending on how our logical tests execute. Now one thing to keep in mind is through these examples we've never been able to have more than one code path execute. So even if we did something like this, if we did else if guess is less than 1 or, then notice both the first test and the second test will pass with a value of -5. However, Go is only going to execute the first branch that has a succeeding test. So we get the result, the guess must be greater than 1 because this test passed, and so this test wasn't even evaluated. Go immediately went in and executed this branch of code and ignored all of the rest of our if statements. Now, another thing to keep in mind when you're working with equality operators, and this isn't specific to if checks, but it is something that's easy to demonstrate with an if check. So if I take a look at this example here, I've got a floating point number of 0.1, and I'm going to check to see if that number is equal to the number squared, and then I'm going to take the square root of it. So if you get out a pencil and paper, you're going to take 0.1 squared, which is going to be 0.01, and then you're going to take the square root of that, which is going to be back to 0.1, right? So this should evaluate to true. If we run this, we see that in fact they are. However, if I add in a couple of decimal places here and run this, now Go says the results are different. Well, the fact is that if you square a number and take the square root of it, it is the same number. So what's going on here? Well, the thing is, Go is working with floating point numbers, and floating point numbers are approximations of decimal values. They are not exact representations of decimal values, and so we have to be very careful with them. So when we're doing comparison operations with decimal values, this is generally not a good idea. The better approach is to generate some kind of an error value and then check to see if that error value is less than a certain threshold. So in this case, since we're taking a floating point number and comparing it to a floating point number, what we can actually do is divide the two numbers and subtract 1, and now what we have is a value that's close to 0. So if we take the absolute value of that, so we'll use the ABS function which does that from the math package, and then check that to see if it's less than, for example, 0.001. What this is doing is saying divide these two numbers, and if they're within 0.1% of each other, then we're going to consider them to be the same. So if we run this, then you see that the results are the same, and we can add as many decimal places as we want right now, and the errors that are associated with floating point numbers aren't going to get in our way. Now, this isn't a perfect solution because you could get two numbers that aren't truly the same and get them to pass this test. So the key to that is tuning this error parameter here, making sure that it's sufficiently small to catch those cases, but sufficiently large so that the errors introduced with floating point operations don't affect your results. Okay, so the next thing that I want to talk about are switch statements. So let me start that conversation by dropping in an example, and we'll see a basic switch statement. So a switch statement is a kind of special purpose if statement. So where an if statement has a logical test and runs a block of code if that test is true, and then you can add an else if to run a second test and another else if and as many else ifs as you want. A lot of times in application development, we run into a set of comparison operations that are very similar to one another. So a lot of times it's more efficient to use a switch instead of an if statement. So we have a simple example here. We're going to use the switch keyword, as you might expect. And in this example, we're going to start with this value here, and that's called a tag when we're working with switch statements. So this is what we're going to compare everything against. Then we're going to have a series of cases, and you see here we got case 1 and we got case 2. So what's going to happen is the value here is going to be compared to the tag, and if it's true, then the statements after the case are going to execute. If not, then they're not going to execute. And just like with if statements, the first case that passes is going to be the one that executes. We also have this default case down here, and that's going to execute if none of our other test cases pass. So if we go ahead and run this, we see that we get 2 printed out. If we add the value 1 here, we get the value 1 printed out. And if we have 3, then we get the default case printed out. So it's a very simple way to compare one variable to multiple possible values for that variable. Now, in a lot of languages, if you want to compare against a range, then you'd have to do something like this. You'd have case 2, you'd have case 3, and then we use what's called falling through in order to compare multiple cases together. Well, we don't actually have falling through as a default behavior in Go, but what we do have to make up for that is the ability to have multiple tests in a single case. So if I extend this example out here, and I say that this is going to test 1, 5, and 10, and this is going to test 2, 4, and 6, then I'm going to say this is going to print out 1, 5, 4, 10, and this will print 2, 4, 4, 6. And then I put in the value 5, and let's just change this message to, this is going to say another number. Okay, so if I run this, then I get the first case is going to pass because I matched this second test. So this is going to execute if I have the value 1, 5, or 10. So I can also get into that same case by passing in the value of 1. If I pass in the value of 4, then like you might expect, I'm going to have the second case evaluate. And naturally, if I pass in an unknown number, then I'm going to have the default case execute just like I had before with a single test. Now, one thing we have to be aware of is the test cases do have to be unique. So if I try and run this, where I'm going to have 5 in the first case and in the second case, that's actually a syntax error because you can't have overlapping cases when you're using this syntax. Now, just like with if statements, we don't have to have a simple tag here in our switch. We can use an initializer, just like you're seeing here. Now, in this case, the initializer doesn't have to generate a Boolean result because we're not doing a Boolean test in our switch statement up here. The Boolean test is comparing the second parameter in the switch statement to our cases. So in this case, we're just going to initialize that value. So I'm doing some simple math here. I is set equal to 2 plus 3, so obviously that's going to be 5. Then I've got the semicolon and the tag that we're going to be testing against. So as you might expect, when I run this, the first case executes because 2 plus 3 is 5. 5 is matched by the first case, and so we get this statement printed out. Now, another syntax that we have available to us in switch statements is a tagless syntax. So both of the styles that we've been talking about, we've always had a value that we're comparing to our test cases. Well, there's actually another syntax, this tagless syntax, and this is arguably more powerful than the tag syntax, although it is a little bit more verbose. So in this case, on line 8, I'm establishing a variable, which is going to come from some other logic in my application. And then I've got the switch statement that's standing all alone and immediately opening a curly brace. So notice I don't have a tag here. However, in my case statements, now I've got full comparison operations. And I can use the comparison operators, I can use the logical operators. So in this case, the cases are standing in for the logical tests that we have in our if statements. They're doing exactly the same job. So in our first case, I'm checking if I is less than or equal to 10. And if it is, then I'm going to print that out. And then in our second case, I'm going to check if I is less than or equal to 20. And then, of course, we've got the default case if the value falls through. So if I run this, I see that I do get the code executing, which is an interesting thing, and it executes the first case. Now, why is this interesting? Well, if you notice, the first case and the second case overlap. Because 10 is less than or equal to 10, it's also less than or equal to 20. So unlike the tag syntax where I've got multiple test cases and I said they cannot overlap, when we're using this tagless syntax, they are allowed to overlap, and if they do, then the first case that evaluates to true is going to execute. Now, another thing that I should have pointed out earlier is notice that we don't have curly braces around this. Any statement that's after this case and before the next case is going to be part of the block that's going to execute. So I can have as many statements as I want here. The delimiters in this case are the actual case keywords, the default keyword, or the closing brace. So any of those delimit the end of a block in a case statement. Now again, if you're coming from another language, then this syntax might be looking a little weird because you might be looking for this word coming in here, and we'll have to add this word here, and we'll have to add this word here. So you might be wondering, where the heck are my break keywords? Well, in Go, the break keyword is actually implied because so many use cases for switches have breaks in there, and forgetting a break is the cause of innumerable errors when working with switch statements. The design decision was made to have an implicit break between our cases instead of an implicit fall through, which most other C-based languages have. So, what happens if you do in fact want your case to fall through? So in this example, let's just say that we do want to print out that we're less than or equal to 10 and that we're less than or equal to 20, and we know that if we pass this first case, we're going to pass this second case too. In that case, we can actually use the keyword fall through. So if I run this, you see that both messages print out. So I'm going to get less than or equal to 10 and less than or equal to 20. Now, one thing to keep in mind here is fall through is logicless. So when we say fall through to the next case, it will do that. So if I, for example, change this to be greater than or equal to, then we know that I fails this second case. But if I run, it still executes because fall through means that you are taking the responsibility with the control flow and you intentionally want the statements in the next case to execute. Now in Go, you don't use fall through very often because we have that tag syntax that can take multiple tests per case, and so a lot of the use cases for falling through are taking care of that. However, if you do have a use case where you need fall through, then it is available to you. The next thing that I want to talk about with switch statements are a special use of a switch statement called a type switch. So I'm going to drop in this example here, and this should be pretty familiar except for what we're switching on. So notice that we are switching on a tag, but the tag variable is typed to type interface. which can take any type of data that we have in a Go application. So the interface type can be assigned to an integer like we're seeing here. We can assign it to a string, to a boolean, to a function, to a struct, to a collection. Anything we want to assign to an interface is going to be permissible. So then in Go, we can use this syntax here. So we can put in the dot operator, and after that put in parens with the word type in the middle. And what that's going to do is tell Go to pull the actual underlying type of that interface and use that for whatever we're doing next. Now, you don't just use that for type switching, but this is a common use case for it. So in this case, I'm going to assign the variable I the value 1, which as we know is going to type I to be an integer. And then I can actually use Go types as the cases. Because this is going to return a type, then I can use those type keywords here as my cases. So if I run this, knowing that 1 is an integer, I should not be surprised when I see the first case passes and the other two are ignored. If I add a decimal point 0 here, then that's going to turn this into a floating point 64, and we see that Go recognizes that. Similarly, if I put 1 in a string here, then we're going to see that Go understands that. And I can even make, for example, an array, and we don't need to initialize any values here, but if we see that, then Go recognizes that as another type. And if I want to have a case to catch that, then I can actually have a case for arrays of 3 integers, and then I can print that out. Now if I run, we see that it recognized that. And this is different than 2. So if I use a 2-element array, please be aware that those are different types. Arrays are not equivalent to every other array. You have to have the same data type and the same array size in order for them to be evaluated as the same type. Okay, the last thing that I want to talk about, I can illustrate with this example here. Now in this example, we're extending on the previous one with type switches, and notice that I've got these two print statements here on line 11 and line 12. So if I run this, I see that I is an integer, and this will print 2. Well, in some situations, you might need to leave a case early. So maybe inside of the case, you're executing some kind of a logical test, and you find out that there is some logic in the case that you don't want to execute in certain situations. Well, if you want to do that, you can actually exit out of the switch statement early by using the break keyword. So if I add that and run, then I have a way to break out of the switch early, and I'm not going to execute any code below that break statement. So you could wrap this in a logical test to determine if you've got a validation error, for example, on some incoming data. You might not want to save that data to the database, and then you can use this break keyword in order to short circuit that save operation. Okay, so that pretty much wraps up what I have to talk about with if and switch statements. Let's go into a summary and review what we've talked about. In this video, we started our discussion about the different control flow tools that we have available to use in our Go applications. And we started out by talking about the very basic if statements and how we can use a Boolean variable to determine if a block of statements will execute or not. We then talked about the initializer syntax and how that allows us to execute a statement that's going to set up variables that we can use to run our test against, as well as use within the statements of our if tests. We then talked about the comparison operators, and we talked about how there are 6 of them. We've got less than, greater than, less than or equal to, greater than or equal to work with primarily the numeric types, as well as the double equals operator and the not equals operator that are available to be used more generally. We talked about the logical operators, the AND operator, the OR operator, and the NOT operator that allow us to chain together Boolean operations, as well as reverse the result of a Boolean operation in the case of that NOT operator. We talked about short-circuiting and how when you're chaining together tests with an OR operation, for example, if any one of those logical tests evaluates to true, then the remaining tests are not executed. So any side effects or any functional operations that might occur with those are not going to be executed. Similarly, with an AND test, the first part of an AND test to return a false result is going to halt the execution of that AND test. So any side effects you might be relying on afterward are not going to occur. We then talked about the 2 different variants of if tests. We talked about the if-else statement and how we can use that to execute one of 2 branches of code. So if the if test succeeds, then we're going to execute the first block of statements. Otherwise, we're going to execute the second block of statements. Related to that is the if-else if statement. And in this case, instead of determining between one of 2 paths and forcing your code to execute one of those, you can add additional logical tests. So at most, one block is going to execute. But if all of your if tests fail, then you might not get any blocks executing. And finally, I took a minute to talk about equality operations, especially when working with floating point numbers, and how equality and floats don't really get along that well. So if you do need to do some kind of an equality operation with floating point numbers, then you're going to want to turn that into some kind of a comparison operation against an error function. So for example, we were checking to see if two floats were equal. Instead of checking to see if they're actually equal, we divided them, subtracted 1 from that result, and checked that against an error parameter. So we decided if they were within 0.1%, they were going to be considered the same. You can use a similar type of error function with your operations, but in general, you should not test to see if two floating point numbers are equivalent to one another. We then moved on to talk about switch statements and the various ways that we can use those in our applications. We started by talking about how to switch on a tag, where a tag is just another name for a variable, but that variable has a special significance in a switch statement because all of your test cases are going to be compared back to that tag. We talked about how with Go we can have multiple tests with our case statements, and by doing that we can actually eliminate a lot of situations in other languages where we need to fall through and chain multiple cases together. Well, in Go, we can just add those multiple tests in the same case and eliminate the need to do that falling through. We also do have initializers available with switch statements, but instead of the initializer generally generating a Boolean, as we do with an if statement, the initializer is going to generate the tag that's going to be used for the comparisons in our cases. We talked about switches with no tags, and how it adds a lot of flexibility to the switch statement, but it is a little bit more verbose syntax. So instead of the cases being compared for equivalency with the tag, we're going to actually put in the comparison operation ourselves, so we can use more than just equivalency testing. We can check less than or equal to, or any other comparison function, including chaining comparisons together by using logical operators. We talk about how we have the fall through keyword available in switches, and how that replaces the break keyword in many languages. So where many languages have implicit fall through and explicit breaking, in Go we flip it around. So we have implicit breaks, but if you do need one case to fall through to the next, then you can use this fall through keyword. Now, one thing to keep in mind when you're doing that is when you're falling through, any additional case logic is not executed. The fall through will override any case logic that you have, and so the next statements will execute regardless of if that case would normally pass or not. We also talked about type switches and how we can use that special syntax by adding a dot, paren, type, paren on an empty interface in order to get the underlying type of that empty interface. So for example, if we've got an empty interface that's holding an integer, then we can use that syntax in order to get that underlying integer value. Then in our switches, we can switch against those types, and then we can make a decision based on the data that we got in. And finally, we talked about breaking out early. When we've passed into a case in our switch statement, there are times when in the middle of the case we need to exit out early because we've done some additional analysis and we've decided that we should not proceed executing this case. So for example, we've got a switch statement, and inside of that case, we're doing some validation on the data before we save it to the database. We might decide that data is invalid and we should not proceed to save it to the database. So in that case, you can use the break keyword, break out of the case, and continue execution after the switch statement. I want to continue our discussion of the control flow structures that we have available in the Go language by talking about looping. Now in the last video, we talked about the two ways that we have to introduce branching logic into our application, if statements and switch statements. Well, when we talk about looping in Go, things are actually going to be a little bit simpler because we only have one type of statement that we're going to have to learn. And that statement is the for statement. Now we're basically going to break this conversation down into three different parts. We're going to talk about simple loops, we're going to talk about how we can exit a loop early, and then we're going to talk about how we can loop through collections. Okay, so let's go ahead and get started by learning how to do some simple loops in Go. So in order to start our discussion about looping in Go, I want to start with this, perhaps the most basic for loop that we can create. So we're going to start with the for keyword, as you might expect, and then we're going to follow the for keyword with three statements. The first statement is going to be an initializer. Now this is the same as an initializer in if statements and switch statements, so we can add any kind of statement that we want here, and normally we're going to use that in order to set up a counter when we're using a for loop like this. The next statement that we have here is going to be some kind of a statement that generates a Boolean result, and that's going to be used by the for loop to determine if it's done looping or not. And then the last statement is going to be the incrementer, and normally we're going to use that in a situation like this to increment a counter variable. So if we run this, we see that we get the numbers 0 through 4 printed out. We could also increment I by 2, and there you see that we only get 3 iterations of the loop because I has the value 0, then it has the value 2, and then it has the value 4. When it comes through the next time, it has the value 6. Well, 6 is not less than 5, therefore the comparison operation results to false, and we exit out of the loop. So this is certainly possible to do, and you will occasionally see this, but the most standard way that you see these loops created is like this, using an increment statement. Now, if you're coming from another language, you might be expecting to be able to do something like this. So maybe we want 2 variables to increment in our for loop, and so we're going to initialize j there, and then we're going to increment j with each loop. So if we go ahead and try and run this, we see that that's actually not allowed because we have no comma operator in the Go language. So you can't separate 2 statements like this using the comma. So this is an error and this is an error. So if we want to do that, though, we can use Go's ability to initialize multiple values at the same time by adding a comma here, getting rid of this part here, adding the comma there. And then we can't treat these as individual statements because you can only have one statement here, and in Go, the increment operation is a statement. It's not an expression, so we need to figure out a way to do both of these at one time. So we will simply come in and set I and j equal to I plus 1 and j plus 1, and go ahead and run that. And now we have I printing out. If we add j here, we see that j prints out as well. We can actually increment j by 2 here, and we see that I and j are incrementing independently, and we have no problems here. Now, just to come back and revisit that increment comment that I made earlier, you might be tempted to do something like this if you just want to increment them by 1. If we run that, we're actually going to get an error because, again, in Go, unlike a lot of languages, the increment operation is not an expression, so we can't use it as part of a statement. It is a statement on its own. So when you're just incrementing one variable, you can certainly do this because I++ is a statement, but we can't use that in combination with anything else. We can't use it as an expression. Something else that's interesting, let me go back to our initial example here so we can play around with this a little bit. So at first blush, if you're just coming to programming, this I variable might seem like it's something special because it's used up in the for loop. And the fact is, it's a variable just like anything else. So we can do whatever we want with it. As a matter of fact, just to show you that, let me drop in this cool little bit of code. As you can see, what we're going to do here is we're going to take the modulus of I and 2, and we're going to see if that's 0. So basically, we're checking to see if I is an even number or an odd number. If I is an odd number, then we're going to divide it by 2. If I is an even number, then we're going to multiply it by 2 and add 1 to it. It's just a couple things to play around with the incrementer. So let's run this and see if this actually goes to completion. And in fact, it does. And you see that the I variable is going all over the place. So we start with 0. 0 is odd, so it divides that by 2, which stays 0. The next iteration, I is going to be 1 because we're incrementing by 1. So it's actually going to be multiplied by 2 and 1 added to it. So we print the 1 here. But then by the time we're done here, 2 times 1 plus 1 is 3, and so I is 3. That gets incremented to 4, so we're printing 4 out here. 4 is even, so we divide that by 2. 2 gets incremented again, so we print out the value 3. 3 is odd, so 3 times 2 is 6 plus 1 is 7. 7 is greater than 5, and so we leave the comparison operation. So we can do whatever we want with the counter. Now, just because you can play with the counter doesn't mean it's a good idea. As a matter of fact, normally it's very bad practice to manipulate the counter within the for loop. So maybe the best reason to show you that you can do this is to make sure that you avoid doing this, because there can be times when you're inadvertently changing the counter variable within a loop, and your loops might start to act really strange like we're seeing in this example here. Okay, so let's go ahead and restore our original example, make sure that that's running again. And it is. We're printing out the values 0 through 4 again. Now, the next thing that I want to show you is that we don't actually need all 3 statements here. So one thing that we could do, let's just say that I is initialized somewhere else in our application, so we don't need I to be set up here, and we can run with this first statement being empty. Now, you can't leave this first semicolon out, because if you leave that out, then everything's in the wrong place, and it thinks that this is going to be the initializer, and this is going to be the comparison operator. So if we try and run this way, we're going to get an error. But if we leave the semicolon in, then Go recognizes that we simply don't have an initializer in this for loop, and it executes everything the way that we expect it to. And of course, that variable I is taken in just like we would expect. Now, the difference between this format and the previous one is in this, I is scoped to the main function, but when we had this syntax here, I is scoped to the for loop. So if I tried to print the value of I out here, we're not going to get a valid value because I is not defined. But in this other form, when we're putting I out here, then I is scoped to the main function, and we are actually going to get the final value of I printed out, which is the value 5, because 5 is the first value that fails this test. So this is actually coming from this statement right here. Okay, the next thing that we can do, let me go ahead and wipe this out. We also don't need the incrementer value, so we can eliminate that. Now, if I run this right now, we're actually going to get an error, because what this is going to do is it's going to generate an infinite loop, and in the Go playground, they don't let us do infinite loops, and so after it runs for a little bit of time, it's going to shut the process down on us. If we were actually running this in a local environment, all you'd see is the value 0 printed out over and over and over and over again, until eventually you got bored and shut the application down. Now we can, of course, since I is a variable just like any other, we can put the incrementer in here, and everything works just fine. So, once again, we have to remember to put the semicolon here. If we remove the semicolon, then Go doesn't know what the heck we're asking it to do, because this is invalid syntax. So if you have the first semicolon, you need the second semicolon. Now, this case does happen actually quite a bit, where we need a for loop and just a comparison operation. And this is how Go does do-while loops. So in a lot of languages, you have two more keywords. You've got the do keyword and the while keyword. And normally those work with simply a logical test, and then you have some other increment operation. So you either have an incrementer inside of the loop, or you're pulling the next value off the stack and comparing that on each iteration, or something like that. Well, Go has the same problems to solve, but it didn't make sense for the designers of the language to introduce a new keyword just for what is basically a special case of a for loop. So what they allow us to do is we, of course, can use this double semicolon syntax here, but you can also leave them both off. So if I run this way, we see that this works, and this is going to work exactly the same way as if we have both of these semicolons here. So this is a little bit of syntactic sugar. It's exactly the same construct. It's just you don't need to have the additional semicolons, and it reads a little bit cleaner. So in this case, our for loop is just doing a comparison operation. Go is going to assume that we're taking care of where those variables for the comparison are coming from somewhere else. Now, the third form of a for loop that we have available when we're working with counters like this is the infinite for loop, because we also have a situation with do-while loops in other languages where we need the application to run through the loop an undetermined number of times. And by undetermined means we don't actually know when to stop by an obvious logical test. We need some complex logic within the loop in order to determine when to leave. So in Go, the way that we do that is we simply leave off the logical test, and we run like this. So if I run this again, as you might expect, the playground's going to crash out on us because there's no way for the program to exit, and so it's just going to run forever. So we need some way to tell our infinite loop when it's done processing and when to leave. And the way we're going to do that is using the break keyword. Now normally the way that you do this is you'll put some kind of logical test inside of the loop. So we can say if I equals 5, then we're going to use that break keyword. And we saw the break keyword the first time when we were talking about switch statements. Well, the break keyword is actually more commonly used inside of for loops, especially this kind of infinite for loop here. So what we're doing here is if I is equal to 5, so we're going to print out the values 0 through 4. Then when I equals 5, we're going to break out. So if we go ahead and run this, we get exactly the same values that we had before. Now when we do this, we actually leave the entire for loop. So execution of the loop stops, and we're done processing. Now another thing that we can do is use what's called a continue statement. So let me drop in an example that shows you that. So in this case, we're looping from 0 to 9 because we're going to keep incrementing as long as I is less than 10. And then we're checking to see if the value is even. If it is even, then we're going to use this continue statement here. And what this does is it basically says exit this iteration of the loop and start back over. So what's going to happen when we have 0, 0 modulus 2 is 0. So we're going to continue, which means we're not going to hit this print statement. When we have 1, 1 modulus 2 is 1, so we're not going to hit this continue, and we're going to print out 1, and then 2 is going to hit the continue, and 3 is not. So what we should see is we'll only print the odd numbers out. So if we run this, we see that that is in fact what happens. So continue statements aren't used very often, but they can be very, very useful if you're looping through a large set of numbers, and you need to determine within the loop whether you want to process a record or not. Now, to show you the next thing, I'm actually going to do this. This is actually going to print out a nested loop. So what we're doing here is a pretty simple example. We're starting with the variable I, initializing it to 1, and we're going to run as long as I is less than or equal to 3, and then we're doing the same thing with j on the inside. So basically I is going to be 1, then it's going to loop through j from 1 to 3, then I is going to be 2, it's going to loop through j from 1 to 3 again, and then inside this inner loop, we're just multiplying the two numbers together. So if we run this, we see that we get all of the permutations of I times j, where I and j go from the values 1 to 3. So we get all of these values printed out, and everything works the way that we expect. Now what happens if we want to leave the loop as soon as we get the first value that's greater than 3? So what we want to do is something like this. So we're going to multiply I times j, we're going to repeat our logic here, and we're going to see if that's greater than or equal to 3. If it is, then we're going to break out of the loop. Now if I run this, we don't exactly get the expected result. And the reason for that is as soon as I times j is greater than 3, it breaks out of the loop. But the loop that it's going to break out of is the closest loop that it can find. So it's actually breaking out of this loop here, and this loop just restarts because there's nothing to tell it to stop. So you might ask the question, well, how do we break out of the outer loop? Do we have to have more logic here and check to see if I times j is greater than 3 again and then break out? Well, the answer is, of course, no. We do have a concept called a label that we can add. So a label is put together something like this. We're going to start with a word and follow it with a colon, and we're going to left justify that in our code blocks. So once I have a label defined, I can actually add the label after the break keyword, and it basically describes where we want to break out to. So since this label is just before this for loop, we're going to break out of the outer for loop. So if I run now, I get to the value 3. 3 is greater than or equal to 3, and so I break out of both the inner and the outer loop. The last thing that I want to talk about in this video is how we can work with collections with for loops. So we've seen this before. We have a slice of integers. In this case, we're containing the values 1, 2, and 3. And we've seen how we can work with this as a slice. So we can print this out. If we run this, we get no big surprise. We get the slice printed out with the values 1, 2, 3. But what happens if I want to work with each individual value? Well, we've seen how we can do this. We can pull out one value from the slice, and we get the value 2. But how do I work with an arbitrarily sized slice? So I don't know how big this slice is going to be at runtime. I want to be able to loop through all of the items within the slice. So the way that I'm going to loop through a collection is using a special form of the for loop called a for range loop. So I'm going to start that with the for keyword, as you might expect. And then what I'm going to get is both the key and the value for the current item in the collection. So I'm going to have two variables that I can set there. And then I'm going to set that equal to this special range keyword and then provide the collection that I'm going to range over. So what this is going to do is it's going to look at the collection here, and it's going to take each value one at a time, give us the key and the value, and then we're going to be able to work with those values independently. So inside of this, let's go ahead and just print out the value of the key and the value and run that. And you see that we get the indexes for the items in the slice, and we get their values. So the indexes are coming first, those are the keys, and then the values are the actual values in the slice. And this is the only syntax you have to remember when using the range keyword. You're always going to get this key comma value result coming out. So this syntax is going to work for slices and for arrays. So if we make this an array by just adding a size here, we see that we get the exact same output. We can loop over maps. So if I pull back the state populations map that we used for a couple of videos now and loop over that, once again pulling out the key and the value and ranging over the map this time, then if I print the key and the value, I'm going to be able to split that out and I get the state and their population printed out separately. And I can even use a string as a source for a for range loop, because what we're going to be able to do here is pull each letter out of this string as a character, and look at that. And we see that we do get each position, and now we get this numeric value, which if you've been paying attention over the last few videos, you're going to remember that this is actually the Unicode representation for that digit. So we can cast it back to a string by just using a simple conversion operation, and we see that we get each letter printed back out as we would expect. The other type of data that we can range over in Go is what's called a channel. Now, channels are used for concurrent programming in Go, and that's a topic for a future video. So I'm going to leave that topic right now, I promise. When we talk about parallelism and concurrency in Go, I'll revisit the for loop and show you how you can use for loops with channels, because there are some special behaviors that you have to be aware of when you're ranging over channels. Now, if I come back to this example and print this out, you see that we have access to both the key and the value every time. Now, this isn't always true. You don't always need access to the value, and this can lead to some problems, because if I only want to print the keys out and run this is actually an error, because in Go you have to use every variable that's declared. So we got this situation where we've got this variable v, but we're not using it, and so that's going to cause us a problem with our application. Now in Go, what you can do, if you only want to get the keys out, you can actually skip the comma value, and when you run that, it's going to ignore the value. But what happens if you get into a situation where you only want to print the value out? So if I restore this and I only want to print the value, of course I get the same error, but I can't just say this because Go is going to assign the keys to that. So what do I do? Well, in this situation, when you only want the values, then you can use that underscore operator, that write-only variable that we've seen a couple of times. And basically that's going to give a hint to the compiler that we don't actually care about the key, but we need this in this first position in order to get at the value. So when we run this, we do see that we get those populations printed out. Okay, so that covers what I want to talk about with for statements in Go. Let's go into a summary and review what we've talked about. In this video, we talked about the second major control flow construct that we have in the Go language, the looping construct. And we talked about how we're going to use the for statement for all of the loops that we need to do in Go. So we don't have to remember a do keyword and a while keyword and a for keyword. When we use the for keyword, that's going to allow us to loop over every collection that we have. We started by talking about simple loops and how there are three basic forms for the simple loop. We've got this first syntax, which is the most basic. That's the initializer test incrementer syntax. And we're going to use that initializer to set us up in our loop, normally by initializing a counter variable. Then we're going to follow that with our test. Our test is normally going to look at the incrementer to see if it's at a certain value that's out of range for our for loop. And then we've got an incrementer, and that incrementer's job is to move the incrementer along at every iteration of the loop in order to move to the next case that we want to loop through. Now we also learned in this first syntax, we actually can leave the first and last statements on that out, but if we're going to use any of this syntax, we have to leave the semicolons in place. So leaving a semicolon out confuses the compiler. It starts to assign things to the wrong places, and so you're going to get an error in your application. So if you need an initializer or an incrementer, then you're going to have to use this full syntax. Now the second syntax eliminates the need for the initializer and the incrementer, and it assumes that the test conditions are being managed somewhere else. So in this construct, you only have the for test, and as soon as that test is false, you're going to exit the loop. The last construct that we have is the for loop on its own, and that will run indefinitely until somewhere within your for loop, the break statement is called. That leads us to how we can exit early from a for loop, and we have three concepts that we talked about with that. We've got the break keyword that will break out of the immediate loop that's executing and continue the application execution after that loop. The continue statement is similar to the break statement, except for it doesn't break out of the loop, it just breaks out of the current iteration, goes back to the incrementer, and continues execution of the for loop at the next increment. Now we can also use labels in our application and combine those with break statements in order to break out of an inner loop, and that's typically how they're used in Go. So for example, if you have a nested loop where you're iterating over two collections and you need to break out of the outer loop, then you need to set up a label and then follow the break keyword with the name of that label so that Go knows where to break out to. And finally, we talked about how to loop over collections and how the collections that we have available, there's quite a few. We've got arrays, slices, maps, strings, and channels that we can loop over, but they all have this similar syntax. We're going to use that for keyword, we're going to get a key and a value, and then we're going to set that equal to the range keyword followed by the collection that we're looping over. So the keys when working with arrays, slices, and strings are going to be the index within that collection, so you're going to have that zero-based index. With maps, we're going to get the key from that map. And the values are what you expect them to be. They're the value for that current index. Now when we're talking about channels, it's going to follow very similar syntax, but channels have a little bit of a special interpretation for these, and we'll talk about those in a future module. I'd like to finish our discussion of control flow constructs that we have in Go by talking about defer, panic, and recovery. We'll start that discussion by talking about deferred functions, and how we can actually invoke a function, but delay its execution to some future point in time. Then we'll talk about how an application can panic. So in this conversation, we'll talk about how a Go application can enter a state where it can no longer continue to run, and how the Go runtime can trigger that, as well as how we can trigger that on our own. And then related to panicking, we'll talk about recovery. Now when your application starts to panic, ideally you'd have some way to save the program so that it doesn't bail out completely. So we'll talk about if your application can be saved, how you can use the recover function in order to signal that to the rest of your application. Okay, so let's go ahead and get started. In a normal Go application, control flows from the top to the bottom of any function that we call. Now, of course, we can alter that a little bit by introducing branching logic so that we can skip some statements, and we can use looping that we talked about in the last video to repeat certain blocks of statements multiple times. But generally, a function is going to start at the first line and execute through until it gets to the last one. So if we run this program right here, we see that it's no big surprise that we print start, then we print middle, and then we print end. And what we can do if we want to defer the execution of one of these statements is precede it with the defer keyword. So if I put that in front of this print line here, then run that, you notice that middle is actually printed after end. So the way the defer keyword works in Go is that it actually executes any functions that are passed into it after the function finishes its final statement, but before it actually returns. So the way this main function is executing is it's calling line 8 and it's printing out start, then it recognizes that it has a deferred function to call, and then it prints out end, and then the main function exits. Now when Go recognizes that that function exits, it looks to see if there are any deferred functions to call, and since we have one, it then goes ahead and calls that. So deferring doesn't move it to the end of the main function, it actually moves it after the main function, but before the main function returns. Now if we put the defer keyword in front of all of these statements, then we'll actually see an interesting behavior, because the deferred functions are actually executed in what's called LIFO order, or last in, first out. So the last function that gets deferred is actually going to be the first one that gets called. And this makes sense because often we're going to use the deferred keyword to close out resources. And it makes sense that we close resources out in the opposite order that we open them, because one resource might actually be dependent upon another one. So if we run this like this, we actually see that we've reversed the order of printing this. So we're now printing end, middle, and start. And just to remind you, these aren't executing in the context of the main function. They're executing after the main function is done, but before it returns any results to the calling function. Now these are good theoretical examples, but in this situation, I felt it makes sense to get a little bit more practical example for you to look at. So for this, we're actually going to need to go into Visual Studio Code, because we're going to need to run a program that's going to make some resource requests through the HTTP package, and you can't do that in the playground. So if we look at this program here, we're importing a couple of packages, then we're using the get function from the HTTP package in order to request the robots.txt file from google.com. Now this example you can actually find in Go's documentation. I basically stole this as an example for how you can use the deferred function. Now as you can see with this request, we're going to get a response and an optional error, and we're going to check to see if that error is nil, and if it's not, then we're going to log that out and exit our application. If it is not nil, then we got a good response. So then we're going to use the readAll function from the IOUtil package. What that'll do is that'll take in a stream, and that'll parse that out to a string of bytes for you to work with. So if we look at the robots variable here, we see that that is a string of bytes. And then we close the body of the response to let the web request know that we're done working with it, so it can free up those resources. Of course, the read operation can fail, so we're checking for that error. And then we're finally going to print out the value of the robots variable here. So if we run this application by invoking it with the go run command, we see in fact that we do get the robots printed out, and everything worked out just fine. So we got this entire response printed out to the console here. Now one thing that we're doing here that the defer keyword can help with is handling this body close. Now in this application, we only have one statement that's really being worked with between the request being made and the body being closed. However, in many applications, you might have quite a bit of logic that's involved that needs that body to be open and continue to work with it. Maybe you're reading the stream one character at a time, and you're doing some pattern matching or something like that. So you can actually end up with quite a few statements in here. So what can happen here is that you might make this request and open up this resource up here, and then it might be dozens of lines later that you actually get around to closing it. Well, that introduces the possibility that you forget to close it. Now, it's going to be hard to find that, and it's going to be hard to remember to close the resource, and so you're introducing the possibility of bugs coming into your application. So what we can do is add the defer keyword here, and then we can go ahead and move this up a line. So if we run this, then it looks like we're closing the resource and then we're trying to read it. But if we run the application, we see that it worked just fine. Everything comes out the same way it did before. Now, if we leave the defer keyword off, then we do get an error because we closed the response body before we were done reading it. So what this allows you to do, and this is the most common use case that I've seen for using defer, is it allows you to associate the opening of a resource and the closing of the resource right next to each other. So you see this pattern a lot, where we're going to open a resource, we're going to check for an error, and then we're going to close the resource. Now you want to check for the error first, because if there's an error generated here, then you actually never got this resource, and so trying to close it will cause your application to fail. But as long as you know that you have the resource there, then it makes sense to do a deferred call to close it. Now, one thing I would warn you about is this is a pretty common pattern, and you're going to see this all the time. But if you're making a lot of requests and opening a lot of resources within a loop, then using the defer keyword to close it might not be your best choice. Because remember, the deferred statements don't execute until the function itself executes. So if you've got a loop that's going to loop over 1,000,000 resources, you're going to have 1,000,000 resources open before all of those get closed at the same time when the function finally executes. So if you're working with resources in a loop, then you might not actually want to use the defer keyword. You might want to explicitly close those resources when you're done with them. Or another option would be to delegate the processing of those resources out to another function and have that function close the resource. That way you're not keeping a bunch of resources open at one time and wasting memory. Now the next thing that I want to show you, we can do back in the playground. So I want to do that because I think that's the most accessible environment that we have, is this program here. So when I run this program here, what do you think is going to print out when I run this? Now there's two lines of thought that you might have. The first line of thought is, well, I'm defining A as the string start, and so I'm going to print start out, but you might also realize the defer statement is going to cause this statement to print after the main function is done, and before main is done, we've already changed the value to end. So you could make an argument that this is going to print start or end. Well, the fact is that we're going to get the value start printed out. And the reason for that is when you defer a function like this, it actually takes the arguments at the time the defer is called, not at the time the called function is executed. So even though the value of A is changed before we leave the main function, we are going to actually eagerly evaluate this variable, and so the value start is going to be put in here. We're not going to pay attention to this value as it changes. Now the next thing that I want to talk to you about in this video is what's called panicking. Now in Go, we don't have exceptions like a lot of applications have, because a lot of cases that are considered exceptional in a lot of languages are considered normal in a Go application. For example, if you try and open a file and that file doesn't exist, that's actually a pretty normal response. It is reasonable to assume that you might try and open a file that doesn't exist, and so we return error values, we don't throw exceptions because that's not considered exceptional in Go. However, there are some things that get a Go application into a situation where it cannot continue, and that is considered exceptional. But instead of using the word exception, which has a lot of connotations because of its use in other languages, we're going to use another word, and that word is going to be panic, and that's because our application can't continue to function, and so it's really starting to panic because it can't figure out what to do. So if we take this example here, I'm declaring two variables, A and B, and setting A equal to 1 and B equal to 0. Now, obviously, the answer of 1 divided by 0 is invalid. We can't do that in a Go application. So if I run this, we're actually going to see that the runtime itself will generate a panic for us. And the runtime error is printed out, integer divide by 0, and then we get a stack trace letting us know where that error occurred. Now, if you're going along and writing your own program, and you get to a situation where your program cannot continue to execute because of a certain state that gets thrown, then it makes sense for you to panic as well. So to do that, you're going to use the built-in panic function like we see here. So we're printing out start, then we're using the built-in panic function, passing in a string, and then we're going to print out end. Now what's going to happen when we run this is very similar behavior to when we had that divide by 0 error a few seconds ago, but the error message that's printed out is actually going to be the string that we pass into the panic function. And then notice we get the same stack trace out. We do get start printed out, but of course we don't get the string end printed out. Now, a more practical example, now this will not run in the playground, but that's okay because it probably wouldn't fail in the playground anyway, is this one here. So this is a very simple web application where you're going to use the handle funcs. So we're registering a function listener that's going to listen on every URL in our application. And then this is a callback that gets called every time a URL comes in that matches this route. And all this is going to do is print out the string hello go. As a matter of fact, why don't I go ahead and do this over in Visual Studio Code? That way you can see what this program is going to do. So we'll go ahead and save this and we'll get it up and running. Now there's no errors. It went ahead and started okay. So if I come in and hit that URL, which is at localhost 8080, then you see that we get the string hello go printed out. There you go, an entire web development course in one video. So we've got a very basic web handler that's printing out the string hello go, and that's coming from this line right here where we're writing to this response writer. This response writer is basically giving us access to the response to this web request, and we're printing out the string hello go. Now, what's interesting here is this error handler right here. So the listen and serve function returns an optional error object. So when might that happen? Well, one situation that can happen all the time when you're firing up a web server is the port could be blocked. So if I open up another terminal here and go ahead and try and run this again, you see that we get our application panicking. And the reason for that is we're trying to access a TCP port that's already been blocked. And it's been blocked by the fact that we're running the application over here. So this is a situation that happens all the time. Now, the listen and serve function doesn't have an opinion on if that's a panicking situation or not, because it just tried to execute something and it's going to return an error value saying, well, that didn't work. It's reasonable to assume that listen and serve can fail. And so it's not going to panic, it's going to return an error. Now, we're the ones writing the web application, and we know that if that doesn't work, the entire application gets brought down and nothing happens. So in that situation, we decide that we're going to panic passing out that error that comes from the listen and serve method, letting whoever's trying to start this up know that something very bad just happened. So this is a common pattern that you're going to see in Go. Go is rarely going to set an opinion about whether an error is something that should be panicked over or not. All it's going to do is tell you, hey, this didn't work the way that you expected it to work. It's up to you as the developer to decide whether that's a problem or not. So in this case, we say, yeah, that is a problem. We failed to start our application, and so we do want to generate a panic. So what are we going to do in the situation that our application is panicking? And we can get ourselves to a situation where we can recover the application. So panics don't have to be fatal. They just are if we panic all the way up to the Go runtime, and the Go runtime realizes, well, it doesn't know what to do with a panicking application, and so it's going to kill it. So we come back to this application here and run. We see that once again we're getting this panic. But something I want to show you related to our deferred discussion is this modification here. So I've added this line, a deferred print statement that says this was deferred. So if we run this application, something interesting is going to happen. We get start printed out, that's not a big surprise, but then we get this was deferred printing out, and then the panic happens. And this is really important because panics happen after deferred statements are executed. So the order of execution is we're going to execute our main function, then we're going to execute any deferred statements, then we're going to handle any panics that occur, and then we're going to handle the return value. So there's actually quite a bit that happens in a function after it exits this closing curly brace here. So why is this important? Well, the first thing that's important is that deferred statements that are going to close resources are going to succeed even if your application panics. So if somewhere up the call stack you recover from the panic, you don't have to worry about these resources being left out there and left open. So any deferred calls to close resources are still going to work even if a function panics. But the other thing that's really important is if I change my deferred function here to something like this. Now this is a custom function and we're not going to talk about this for a couple of videos yet, but this is important in order to talk about this, so I need to jump this ahead in the queue a little bit. So what we're creating here is what's called an anonymous function, and an anonymous function is simply a function that doesn't have a name, so nothing else can call this. This is defined at one point and we can call it exactly one time. These parentheses here are making that function execute. And this is an important thing to know about the defer statement. The defer statement doesn't take a function itself, it actually takes a function call. So you want to invoke that function, otherwise things aren't going to work properly. Now inside of this custom function, notice that we're using this recover function here. So what the recover function is going to do is it will return nil if the application isn't panicking. But if it isn't nil, then it's going to return the error that actually is causing the application to panic. So in this logical test, we're checking to see if it's not nil. So if it's not nil, that means our application is panicking. And in this situation, we're simply going to log that error out. Now what happens in this situation is the execution still stops at the panic. And let me import this log package before we run this. And we see that the application still executes. So we got the string start printed out. Then we printed out the error using the log package, but we didn't get this end function printed out. So it looks like our application is still dead, but recover does have some important impacts if we have a deeper call stack than what we're dealing with right here. So let me drop in this example in order to show you. So in this case, we got the main function that's going to be our application entry point, of course, and then we've got this other function called panicker. And all this thing does is it's going to print out a line that says it's about to panic, and then it's going to panic, and it's going to go ahead and recover from that panic using that deferred function that we saw just a moment ago. Then we're going to have this line here, done panicking. And then up in our main function, we're going to print start, we're going to call the panicker, and then we're going to print end. So let's see what happens when we run this. So as you see, we get the start line printed out like you would expect. We see the about to panic string print out. Then we panic, something bad happened. We go into our recover loop because we're not going to execute this because our application panicked, and so our panicker function is going to stop execution right there and execute any deferred functions. And inside of that deferred function we call recover. So in that recover, we're going to log out the fact that we have that error, and we're going to log that error message out that we see here. But then in the main function, execution continues. So in the event that you're recovering from a panic, the function that actually recovers still stops execution because it's in a state where it can no longer reliably continue to function, and so it makes sense for it to stop doing whatever it was trying to do. However, functions higher up the call stack, those functions that called the function that recovered from the panic, they are still presumably in a situation where they can continue because your recover function said that your application is in a state where it can continue to execute. Now this is a little bit limiting as well, because in order to determine what that error is, you actually have to call the recover function, which basically means that you're saying that you're going to deal with it. So what happens if you get that error and you realize that this isn't something that you can deal with? Well, in that case, what you're going to do is repanic the application. So all we need to do in order to do that is just rethrow the error, or you can come up with another error string, whatever makes sense for you. But in this case, inside of the handler, we're throwing a panic again. Then we actually see that we don't get that end statement printed out. Our main function panics because we rethrew that panic. So we get the full stack trace of when the panic actually happened, and we see that we're inside of func1. Func1 is actually this anonymous function right here. And we see that we do get that stack trace printed out, and we don't get the string end printed out. So if you're in a situation where you're trying to recover from a panic and you realize you can't handle it, you can feel free to rethrow that panic and defer the management of that panic higher up the call stack. Okay, so let's go into a summary and review what we've talked about in this video. In this video, we talked about the final two control flow concepts that we have to be aware of in Go programming. Now, one could argue that defers and panics aren't really control flow constructs because they're not the traditional branching or looping logic that we consider, but they definitely do alter the flow of execution of our program, and so I'm going to lump them together in this category. The first thing that we talked about was the use of the defer function in order to delay the execution of a statement until the end of a function. Now these are useful to group open and close functions together. So if your open function is going to open up a resource and you need to make sure that you close that, then you can defer the call to close that resource to make sure that you're freeing up the memory and not holding onto that resource any longer than you need to. The one thing I would warn you though is be careful in loops. If you're opening and closing a bunch of resources inside of a loop, then you probably want to explicitly handle that close without the deferred keyword, because when you're using the deferred keyword, all of those resources are going to stay open until the function finishes execution, and that can cause you some memory issues, especially if you're dealing with a very large number of resources. Now, if you've got multiple deferred statements inside of a function, then they run in LIFO order, or last in, first out. So the last deferred statement that you call is going to be the first one that actually executes. And again, this makes sense because if you're opening a bunch of resources and those resources are dependent upon one another, then you're going to close them in the reverse order that you open them, which is typically the right way to go. Arguments in a deferred call are evaluated at the time the defer is executed, not at the time the called function is executed. Now that's important to keep in mind because you could pass in variables into a deferred function call, and it can be a little bit confusing if you change the value of those variables further on and those aren't reflected in your deferred statement. So just keep in mind, when you call defer, the value of those variables are going to be captured at the time that that defer is executed, not at the time the function actually executes. Now, something unplanned happens in our application, then we've got two ways that a Go application can go. It can return an error value, which is the normal case, or it can panic. Now, what you generally want to do is you want to return an error value because in Go programming, we typically don't consider a lot of things that go wrong in an application to be exceptional events or to be events that should cause the application to shut down, for example. A classic example of that is making an HTTP request and you make the request and you don't get a response from that server. Well, that's something that happens all the time. No response is a valid response. It just happens to be an error because you're looking for that resource and you got a 404 return back. So in that case, you're going to return an error value. You're not going to panic the application. Panics are used when an application gets into a state that it cannot recover from. For example, if you hand the runtime a divide by zero problem, there's no way for Go to figure out how to divide a number by zero, and so it has no way to manage that. And that's a situation where the application is going to panic. So just to summarize that, they occur when an application can't continue at all. Don't use them when a file can't be opened, unless it's a critical file. For example, if you're opening a template that's used in a web application to generate your view layer, then that might be something that's worth panicking over. But if you're trying to open up a log file and you can't get there, well, there's no reason to panic for that necessarily. You just need to return an error value and then inform somebody that the logs aren't available. Now, a situation where you might want to panic is unrecoverable events. So if you're starting up a web server and it can't get a hold of the TCP port that it's supposed to be listening on, then that's probably a situation where a panic makes sense. The function will stop executing immediately at the point of the panic, but deferred functions will still fire. If nothing handles that panic, then eventually the panic is going to go up the call stack, it's going to hit the Go runtime. The Go runtime has no built-in handling for panicking situations, and so the program will then exit. If you do have a panicking situation that you feel that you can recover from, then you can recover using the built-in recover function. Now, that function is used to recover from panics. It's only useful inside of deferred functions, and the reason for that is because of the behavior of panic. Remember, when an application starts to panic, it no longer executes the rest of that function, but it will execute deferred functions. So the proper place to use the recover keyword is inside of a deferred function that's going to look for a panicking situation, and if the application is panicking, then it can go ahead and decide what to do with it. The current function will not attempt to continue, but if you do recover, then higher functions in the call stack will continue as if nothing went wrong. Now, if that's not the behavior that you want, if you call that recover function, you look at the error that's returned from the recover function and you can't handle it, remember that you can go ahead and rethrow that panic by calling the panic function again, and then the panic will continue to propagate up the call stack. I want to talk about pointers and how we can use them in the Go language. We'll start that discussion off by learning how to create pointers, and then we'll talk about something called dereferencing a pointer, which is basically using a pointer to get at some underlying data. Then we'll talk about the new function, and then we'll talk about a special type in Go called nil, and then we'll wrap up our discussion by talking about built-in types in Go that use internal pointers, and so their behavior is a little bit different than other types that you'll work with in your applications. Okay, so let's dive right in and learn how to create some pointers. To start our discussion, I want to start as simply as I can, and so I'm going to use this example here. As you can see, I'm declaring a variable a, and assigning it the value 42, and then I'm going to go ahead and print that out. So it should be no big surprise that when I run this, the value 42 gets printed out. Now, if I extend this application a little bit, and I create a variable b and assign it to the value of a, and print both of those out, then again, it's no big surprise that 42 prints out 2 times. Now, since a and b are value types, when I put in this line here, what Go is going to do is it's actually going to copy whatever data is stored in a and assign it to b. So we're not actually pointing to the same memory, and we can prove that by changing the value of a to, for example, 27, and then printing out everything again. And if we run this, we see that the value of a changes to 27, but the value of b stays at 42. Now we can change this behavior a little bit by having b point to a using something called a pointer. Now in order to demonstrate that, I'm going to actually change our declaration syntax a little bit and go to more of a long form syntax. And the reason for that is to make things a little bit more clear about how the pointer notation works. So I hope you'll agree with me that this line 8 is exactly the same as the previous one that we had, it's just a little bit more verbose. Now if I want to change b into a pointer and use that same long form syntax, what I can do is declare the variable b, and then I'm going to declare it as a pointer to an integer. And the way I declare it as a pointer is by preceding the type that I'm pointing to with this asterisk here. So then if I want b to point to a, then I'm going to use a special operator called the address of operator that you see here. So what line 9 is now saying is that b is a pointer to an integer, and I want to point it to a. Now what is a pointer exactly? Well, let me remove these lines here and run this and see what we get as output. So as you see here, a is still holding the value 42 like we expect, but b is holding this strange data here. So what is that? Well, this is actually the numerical representation for the memory address that is holding the location of a. So at this location in memory, we actually have assigned the integer 42. So b isn't holding the value 42, it's holding the memory location that's holding a's data. And we can prove that by using the address of operator down here, and when we run this again, we should see, and in fact we do, see that the values are exactly the same. So the address of a in memory is this value here, and b is holding that exact value. And as a matter of fact, we can even go the other way, because while the address of operator is going to give us the address of a variable in memory, we can use a different operator in order to figure out what value is actually being stored at a memory location. And that's called the dereferencing operator. So if I go ahead and remove this, and then I'm going to put a dereferencing operator right here in front of this pointer. Now you notice we're using the same asterisk, but these have a little bit different meaning here. So up here on line 9, this asterisk before a type is declaring a pointer to data of that type. So this is a pointer to an integer. Now when I put the asterisk in front of a pointer, then that's going to dereference, which basically means it's going to ask the Go runtime to drill through the pointer, find the memory location that that pointer is pointing to, and then pull the value back out. So if we run this, we see that we get the value 42 printed out both times once again. Now what's the point of all of this? Well, the point is, since B is pointing at the same value of A, now both of these variables are actually tied together. So if we change the value of A once again, and then print out their data, now we see that both A and dereferencing B both give the value of 27 because they're both actually pointing at the same underlying data. As a matter of fact, we can even dereference the pointer and use that to change the value. So if I use the dereferenced B and assign the value 42 to it, and then print this out again, then we see that once again, both values are changing. A and the value that B is pointing to are both changed because it's in fact the same data. Now, if you come from a background in languages that allow you to work with pointers as variables, then you might be expecting to do something called pointer arithmetic. So if I drop this example in here, we're going to start to play around with something that's going to lead us to see how Go treats pointer arithmetic. So I'm going to start with the variable A, and that's going to hold an array of 3 values, 1, 2, and 3. And then I've declared B as a pointer to the first element in the array, to this value right here, and then C is pointing to this second element right here. Now if I use this print statement here, it's going to print the value of the array, and then this %p syntax is actually going to print the value of the pointer for B and C. So if we run this, we see that we do in fact get the array, and then we get these 2 memory locations printed out that B and C are holding. Now notice that C is holding a value that's 4 higher than B. And the reason for that is how Go lays out arrays in memory. Since this is an array of integers, and integers in this version of the runtime are 4 bytes long, each element of an array are 4 bytes apart. So this memory address ending with 124 is holding the first element in the array, and then 4 bytes later, we're going to hold the next element of the array. So you might be tempted to do something like this if you come from another language. If I take the address of C and subtract 4, then that actually should give me the address of B, and then I can dereference that, and both of these should be pointing to the head of the array. Well, if I run this, I in fact see that I get an error. And the reason for that is Go does not allow math like this to be done on pointers. Now once again, if you've come from C or C++, you're probably aware of the tremendous performance advantages that you can get if you're allowed to do pointer arithmetic, because you can jump around mapped memory very, very quickly and gain some pretty substantial benefits in the performance of certain applications. However, whenever you get into pointer arithmetic, you are typically getting into some fairly complicated code, and since Go has as one of its core design concerns simplicity, the decision was made to leave pointer arithmetic out of the Go language. Now, if you absolutely need to have something like this in your application, then what I would suggest is you can come into the Go packages and come down here to the unsafe package, and this is going to give you operations that the Go runtime is not going to check for you. So if you really need to do pointer arithmetic and things like that, then the unsafe package, which has a very appropriate name, is available for you for those very advanced scenarios. Now, those scenarios are advanced enough that what I'm going to suggest is if you need to know it, you're going to learn it, but generally you're not going to need to know how this stuff works. Now the next thing that I want to show you is how we can actually create pointer types. So we've seen this address of operator, and that's allowing us to instantiate a pointer to a certain variable. So if we look at the type of B, it's actually a pointer to an integer because we're pointing to one element in the array. But so far we've had to declare the underlying type first. Well, that's actually not necessary in Go because often you only want to work with the pointers and you don't really care where the underlying data is stored. You just need the ability to point to it wherever it's at. So in this example, we see how we can do that. Now, we've seen almost exactly the same syntax before because when we were talking about structs, we had an example that looked something like this. So we were declaring a myStruct object, we were instantiating it using the object initialization syntax, and when we print everything out, we print the value 42 out. Now if I make this ms variable a pointer to a myStruct, and then use the address of operator in this object initializer, then I actually get almost the same behavior, except for notice that when I print out the value of ms, I end up with this ampersand here, which is basically saying that ms is holding the address of an object that has a field with the value 42 in it. Now, the advantage of being able to do this is going to come to light in a future video, but for now, just be aware that you can do this. Now, this isn't the only way that we have available to us to initialize a variable to a pointer to an object. We can also use the built-in new function. Now, unfortunately, with the new function, we can't use the object initialization syntax. We're just going to be able to initialize an empty object. So if I go ahead and run this, we see that we do get an initialized object, but all of its fields are initialized to their 0 values. We can't initialize them using the object initialization syntax. Now, since I mentioned 0 values, it's important to understand the 0 value for a pointer, because as we talked about in a very early video, every variable that you declare in Go has an initialization value. So right here after line 8, ms is holding something. So the question is, what is that thing? So if I go ahead and copy this print statement up here, we'll be able to answer that question. So let me format this and run it. And then we see that we get the special value nil out. So a pointer that you don't initialize is actually going to be initialized for you, and it's going to hold this value nil. So this is very important to check in your applications, because if you're accepting pointers as arguments, it is best practice to see if that pointer is a nil pointer, because if it is, then you're going to have to handle that in a different way. So for example, if we try and drill through and get to this foo field, but ms is actually nil, then we're going to get a runtime exception and our program's going to crash on us. Now that actually leads us to an interesting point. How do we actually get at this underlying field and work with it? Well, the obvious way that we're going to need to do that is we're going to have to dereference the ms pointer in order to get at that struct, and then we can get at that field. So we're going to have to use something like this. Now you might be asking why the parens are there. Well, it turns out that the dereferencing operator actually has a lower precedence than the dot operator, so we need the parens in order to make sure that we're dereferencing the ms variable instead of dereferencing ms.foo. So now we can go ahead and set this to the value 42. Now in order to get at the value of foo to print it out, then we're going to have to repeat the same exercise. So I'm going to add some parens here, I'm going to wrap this ms variable, and then we'll print out the value of foo. So if I go ahead and run this, we in fact do set and get the value 42, which is the value of that field. Now I hope you'll agree with me at this point that this syntax is really ugly, because if we use this syntax every time we dereference a pointer, we're going to have to use a matched set of parens and have this dereference operator. Well, it turns out, because of the limitations that are put on pointers, the compiler is actually able to help us out a little bit. So in fact, we don't need this syntax at all. If we go ahead and remove this from the print statement as well, and run this, we actually get exactly the same behavior. Now again, if you're coming from a language which makes extensive use of pointers, this is probably freaking you out, because the pointer ms doesn't actually have a field foo on it. The pointer ms is pointing to a structure that has a field foo. So how is this working? Well, again, this is just syntactic sugar. This is just the compiler helping us out, because it understands we're not actually trying to access the foo field on the pointer. We're implying that we want the underlying object. And so Go is going to go ahead and interpret that properly for us and dereference the pointer. So the compiler really sees this statement the same as this statement. They're exactly the same to the compiler. It's just one reads a little bit more cleanly. Now the last thing that I want to talk about today is how Go handles variables when they're assigned one to another. So let me go ahead and paste this example in here. As you can see on line 8, we're initializing an array. On line 9, we're initializing another variable and pointing it to the same array as A. Then I'm going to print out both A and B. And then I'm going to change index 1 of the A array to 42 and print them out again. Now we've already done this example in the past, and hopefully you remember that A is going to change, but B is not, because B is a copy of the array that we stored in A, and so they update independently of each other. However, if I remove this index and turn this into a slice, the behavior changes a little bit. If we run this, now we see that both A and B are changed together. So what happened there? Well, the slice is copied just like the array, but the effect of the copying is a little bit different. Because in the version with an array, the values of the array are actually considered intrinsic to the variable. So A is holding the values of the array, as well as the size of the array. And that size is held, that way we can do bounds checking. So for example, if we ask for index 3, which is beyond the bounds of this array, and run, we can do bounds checking in the Go language, and that's a very good thing. However, with slices, remember, a slice is actually a projection of an underlying array. And so the slice doesn't contain the data itself. The slice contains a pointer to the first element that the slice is pointing to on the underlying array. So what that means is that when we work with slices, the internal representation of a slice actually has a pointer to an array. So while line 9 is still copying the slice A into the slice B, part of the data that gets copied is a pointer, not the underlying data itself. What that basically means is when you're sharing slices in your application, you're actually always going to be pointing at that same underlying data. Now the other built-in type that has this behavior is a map. Because maps, once again, have a pointer to the underlying data. They don't actually contain the underlying data in themselves. So if I take this example where I'm initializing a map of strings to strings and assigning that to A, and then B is assigned to A, then I print them both out, then I change one of the values in A and print them out again. If I run this, we see that both maps start out the same, and then when I change the key foo in the map A, we actually change that in the map B as well. So what does that mean? Well, what it means is when you're working with slices and maps in a Go application, you have to be very, very careful to keep in mind at all times who's got access to that underlying data. Because passing slices and maps around in your application can get you into situations where data is changing in unexpected ways. However, if you're working with the other data types, specifically primitives, arrays, or structs, then this generally isn't going to happen to you because when you copy a struct, it's actually going to copy the entire structure unless you're using pointers. Okay, so that wraps up what I have to talk about with pointers. Let's head into a summary and review what we've talked about in this video. In this video, we talked about pointers and how to use them in the Go language. Now, we haven't seen a lot of practical application for pointers yet, but we need to understand what pointers are before we get into that. So over the next couple of videos, we'll get into why you would want to use pointers and the benefits of them, but for now, we're just trying to introduce the basic subject. So we started by learning how to create pointers, and we learned that if we prefix a type with an asterisk, that's actually going to declare that type to be a pointer to that underlying data type. So for example, we have this asterisk int, which is going to be a pointer to an integer. We also learned how we can create pointers using the address of operator to get the address of an existing variable in memory. Then we learned about dereferencing pointers and how we can use that asterisk operator again, but this time in front of a pointer instead of in front of a type, and use that to drill through the pointer to get at the value that the pointer is pointing to. We also learned that when you're working with complex types, such as pointers to structs, those pointers are automatically going to be dereferenced for us, so our syntax doesn't get cluttered up by a whole bunch of dereference operations and parentheses. Then we moved on to learn how to create pointers to objects. And we learned that there's a couple of different ways. So the first thing that we could do is use that address of operator to get access to a pointer to an object that we've already created. So in this example, we've got an instance of a myStruct object called ms, and then we can use that address of operator to create a pointer p to that struct. But we can also do that directly. So if we precede an object initializer with that address of operator, then we can actually directly create a pointer, and we don't have to have an intermediate variable that's holding that value. We can also use the new keyword to initialize an object, but we can't initialize the fields at the same time. So the behavior is a little bit different because we're going to have to use the new keyword that's going to zero out all the fields in a struct, for example, and then we're going to have to come in later and initialize all the values. The last thing that we talked about was types with internal pointers. And we saw how, while they're treated exactly as any other variable type when we do an assignment, their behavior is a little bit different. So all assignment operations in Go are copy operations. So whenever you have a variable A and you create a variable B and set it equal to A, all of the data in A is going to be copied in order to create B. However, slices and maps contain internal pointers, and so even though they're copying pointers, and so they're pointing to the same underlying data. We're going to take a deep dive into functions and how you can use them in the Go language. Now, we've been talking about functions throughout this entire video series, but we've never really taken the time to focus on them because there's a lot of groundwork that we've had to go through building up to the point where we can understand what a function is and how we can use those in our applications. So in today's video, like all of our videos in this series, I'm going to break the discussion down into multiple parts. We'll start by talking about the basic syntax of a function. Then we'll talk about the parameters that you can pass into a function to influence how it works. Then we'll talk about the return values that you can get back out of a function. We'll talk about something called an anonymous function. We'll talk about how functions in the Go language are first-class citizens and can be passed around in your application like any other variable. And then we'll wrap up our discussion by talking about a special kind of function called a method. Okay, so let's get started by learning the basic syntax of a function. To start our discussion of functions, we don't have to go any farther than the basic application that the Go playground gives us. So as soon as you come into the playground, you're presented with this very simple application, and right here we have our first function. Now the way that a Go application is structured is you always have to have an entry point in the application. And the entry point of a Go application is always in package main, and within that main package you have to have a function called main that takes no parameters and returns no values. So we can see that right here. And so when we run the application actually starts right here. And so we print out the string hello playground, and that's all that our application has to do. So every Go application starts this way, and we see here the most basic function that we can create in the Go language. So there are several major parts that we need to understand about a function. First of all, they start with the func keyword. So as you can see here, we're not going to start with function or anything else. We start with the func keyword, and that's going to describe a function that we're going to create. Then we have the name of the function that we're going to create, and this follows the same naming convention as any other variable in Go. So you're going to use Pascal case or camel case for the names of your functions, and depending on if you have an uppercase or lowercase determines the visibility of that function. So just like with variables, an uppercase first letter is going to be published from the package so anything else can use it, and a lowercase function name is going to be kept internal to the package. Now after the name of the function, we have these matched parens here. Now we'll see as we get into parameters what these are for, but this is required syntax after the main function. So even if you don't take any parameters in your function, you have to have these matched parens. And then the actual body of the function is contained within these curly braces here. Now, there are a lot of holy wars in a lot of languages about where these curly braces should go. So some languages put them here, some languages put them down here, some languages like to indent them. There's all sorts of different conventions about where to put these curly braces. Well, in the Go language, there aren't any arguments because this is the convention that is enforced by the compiler itself. So you have to put the opening curly brace on the same line as the func keyword, and then the closing curly brace generally has to be on its own. Now there are a couple of situations where you can have that closing curly brace combined with a couple of other parens, and we'll talk about that a little bit later in this video, but generally speaking, when you're defining a function, the closing curly brace has to be on its own line. Now with functions defined like this, the execution path is static. We can't actually influence what our function's doing from the outside, because we're not passing any information into it. So if we do want to pass information into it, then we're going to provide what are called parameters into the function. So let me just drop an example that uses parameters. And you see here, our main function is now calling into another function called sayMessage. And that sayMessage function takes in this parameter MSG that's of type string. So when you're defining a function that takes parameters, the parameters go between these two parentheses here, and they're described like any other variable declaration except for you don't need the var keyword. So you're going to have the name of the parameter and you're going to have the type of the parameter. So then when we want to call that function, we have to pass in the value for that parameter, and that's called an argument. So we're going to pass in the argument hello go, and then inside of our function we're printing out the message that gets passed in, and so when we run this, we see that hello go prints out as a result. Now this MSG parameter isn't special in any other way than the fact that it's passed into the function. It's treated as a local variable just like any other local variable that we might create. So if we created another variable here, and we said hello go, that's treated exactly the same way as our MSG variable. So the only difference between the two is the MSG variable can be passed in from the outside, and of course that greeting variable was created locally. Now you aren't constrained to just pass a single parameter in. You can actually pass multiple parameters in. So if I drop in this example, we can see that in action. So here I've extended the sayMessage function to take two parameters. So I've still got the message parameter that's of type string, and then I've put this comma here, and I've added another parameter, and that's going to be an index, and that's going to be of type integer here. So as you can see, we can pass as many parameters as we want. We're just going to provide a comma delimited list of those parameter names and their types. So then when we call the function, we're going to pass in one value for each one of those parameters, and they have to be in the same order that they're declared. So the first argument that we're going to be passing is the string hello go, which is going to match this MSG variable. And then we're going to pass in the I that's going to be the loop counter here, and that's going to be passed into this IDX parameter. So then in this function, we're just going to print out the value of the message, and then we're going to say what index we receive. So when we run this, we see that the message prints out 5 times, and we get the same message, but the index variable changes because we're passing in a different value every time we call the function. Now often when you're defining a function, you're going to pass in multiple parameters of the same type. So you're going to be tempted to have syntax like this. So in this example, we've got a slightly different function. So instead of a generic say hello, we're going to have a say greeting function, and we're going to provide the greeting that we're going to have and the name of whoever it is we're going to greet. So in this case, we're passing in the string hello and the string Stacy. So when we run this, we're going to say hello to Stacy. Now, since these types are the same, the Go compiler actually provides us a little bit more syntactic sugar because this is a little bit more verbose than is strictly necessary. So instead of specifying the type every time, we can actually just specify a comma-delimited list of variables and then the type at the end. And what the compiler is going to do is it's going to infer that every variable that's in that comma-delimited list has the same type. So when we run this, we actually get exactly the same execution, but we just have a little bit more terse syntax. Now, so far, we've been passing parameters in as value types. If you remember from our last discussion, we were talking about pointers, and notice that I don't have any pointers in our function signatures right now. So let me drop in this example here, and then we can start playing around with the difference between passing in values and passing in pointers. So when I have this example here and I run it, we get exactly the same output that we had before, but I've got some variables that I'm using to pass in as arguments to this function. Now, what do you think is going to happen if I change the value of one of these variables inside the function? So for example, if I change the name variable to Ted, and let's go ahead and print that out just to verify that it printed. And then what do you think is going to happen if I print the same variable out again right here? So I'm passing in the name variable by value. So that means that the Go runtime is going to copy the data that's in this name variable and provide it to here. So what we would expect is when we change the value of the name variable right here, it should have an effect and we should print Ted out here. But since this is a copy of the name variable, we actually shouldn't have any effect out here. So if we run this, we see that in fact that is true. So this is a safe way to pass data into a function. You can be assured by passing by value that the data is not going to be changed when you pass it in. Now if I change this to passing in pointers by adding a pointer here, and then passing in the address of these variables right here, and then dereferencing the pointers right here, then let's see what's going to happen. Actually, I need to add another dereference right here, and now we're passing pointers to our variables around in our application. So now, instead of working with a copy of the name variable, we're working with a pointer to the name variable, and so when we run this, we actually see, looks like I missed a dereference operation right here, and now we see that we have in fact changed the variable not only in the scope of the function, but in the calling scope as well. So by passing in a pointer, we have in fact manipulated that parameter that we passed in. Now why would you want to do this? Well, there's a couple of reasons. First of all, a lot of times our functions do need to act on the parameters that are passed into them, and so passing in pointers is really the only way to do that. The other reason is passing in a pointer is often much more efficient than passing in a whole value. Because right now we're passing in simple strings, and strings aren't that large in Go, so passing in copies versus passing in pointers is pretty much going to be the same in terms of performance. However, if you're passing in a large data structure, then passing in the value of that data structure is going to cause that entire data structure to be copied every single time. So in that case, you might decide to pass in a pointer simply for a performance benefit. Now you do have to be a little careful when you're passing in pointers because of course you can't inadvertently change that value, and so you can cause some issues for yourself. Now just to remind you of something else that we talked about in the pointer discussion, if you're working with maps or slices, then you don't really have this option, because since those two types have internal pointers to their underlying data, then they're always going to act like you're passing pointers in. So just be careful when you're using those data structures, because you can inadvertently change the data in your calling function when you're manipulating them within the called function. The last thing that I want to talk about when we're working with parameters are what are called variadic parameters. So if I drop in this example here, we can see an example of a variadic parameter. So in this case, I've got a generic sum function that I'm creating here, and I'm passing in the numbers 1 through 5. Now I'm not receiving 5 variables here. Instead, I've got one variable here, and I've preceded its type with these 3 dots here. So what that's done is that's told the Go runtime to take in all of the last arguments that are passed in and wrap them up into a slice that has the name of the variable that we have here. So then inside of the sum function, we're going to print out what that values object is just so we can see that, and then we're going to go ahead and add up all the values in there. So since it's going to act like a slice, we can use a for loop and range over those values, and then we're going to print out the result of that. So when we run this, we see that we do in fact have a slice that's printed out. The sum is 15, so we got that result printed out properly, and there's no problem at all. Now, when you're using a variadic parameter, you can only have one, and it has to be the last one. So if I, for example, want to have a custom message string, I can pass that in, and then pass that in here, and then replace this, and this still works just fine. However, I couldn't, for example, put the message parameter as the last parameter, because the runtime doesn't have the ability to understand where the variadic parameters end and where additional parameters would begin. So if you're using variadic parameters, you can only have one, and they have to be at the end. Okay, now it's nice to be able to pass data into our function, because now, depending on the different data that I pass in, I can change the behavior of the function. But it's also very useful to be able to use our functions to do some work and then return a result back to the calling function. So in order to do that, we're going to use what are called return values. So if I drop in this example, we see it's basically the same as our last example, but instead of printing the message in the sum function, we're returning the result out, and then the main function is actually working with that. So there's a change we had to make in our function signature. So right here after the parameter list and before the opening curly brace, I've listed the return values type. So in this case, I'm expecting to return an integer, so I just put int right here. Inside of my function, I'm going to use the return keyword, and then I'm going to return the value of the variable that I've been building up throughout the course of the function. So in this case, I declare the result variable here, I populate it in this loop, and then I return that result back. Now up here in the main function, I can catch that return value by declaring a variable and setting it equal to the result of this function. So s is actually going to be an integer type, because that's what's returned out of this function, and then I can work with that integer. So if I run this, I get exactly the same behavior that I had before, but now the sum function is more of a pure function. It doesn't care what I do with that result, it's just going to generate the result and return it back to the caller. Now another feature that Go has that's actually pretty rare in a lot of languages is the ability to return a local variable as a pointer. So in our previous example, when we returned that result, Go actually copied that result to another variable, and that's what got assigned. But we can also do this. So if you look here, I'm returning a pointer to an integer now, and instead of returning the result, I'm returning the address of the result. And so s is now a pointer, so I've changed to a dereference operation. So if I run this, it works exactly the same way. Now, again, if you're coming from another language that uses pointers a lot and doesn't abstract away the differences between working on the stack and working on the heap, then this might freak you out a little bit. Because when we declare the result variable, it's actually declared on the execution stack of this function, which is just a special section of memory that's set aside for all of the operations that this function is going to be working with. So when this function exits, that execution stack is destroyed. That memory is freed up. And so in a lot of languages, this is not a safe operation, because now you're returning a pointer to a location in memory that just got freed. And so you've got no idea what value is going to be there. Well, in the Go language, when it recognizes that you're returning a value that's generated on the local stack, it's automatically going to promote this variable for you to be on the shared memory in the computer, what's also called the heap memory. So you don't have to worry about this value being cleared. The runtime is going to recognize that you're returning a pointer from the local stack, and everything is going to work for you just fine. And it makes a lot of things more convenient, because within the function, we can work with this as a true value, so we don't have to worry about dereferencing pointers. And then just right at the end, we can return the address of the result, and the runtime makes it all work for us. Another thing that we can do in the Go language, and this isn't done very often, but there are cases where it is valuable, is using named return values. So if I drop in this example here, notice that I've changed my return value now. I've got a set of parentheses here, and then I've got a name for the return value and a type for it. So when you do this, this is basically syntactic sugar for declaring a result variable. So this variable is going to be available in the scope of our sum function, and then that value is going to be implicitly returned. So we can work with that result variable right here within our function, and then we don't have to specify the name of the return variable down here on line 17. We just have to tell it to return. So when we run this, we see that once again we get exactly the same behavior, but the body of our sum function is actually quite a bit cleaner, because we don't have to do the maintenance of instantiating this result variable. Now this is actually not done very often in the Go language, and my suspicion is because it can be a little bit confusing to read, because your return variables are declared way up here at the top of the function, and your actual return is down here at the bottom. So if you're reading this code and you're trying to figure out what this function is actually going to return, you have to come all the way back up to the function signature. So this can be a very valuable technique to use, but I would be very careful with it, because if you've got long functions, then named result parameters can actually be more confusing instead of less confusing. So you have the option there. Pick whichever one makes the most sense for your application. The last thing that I want to talk about with return values is the fact that we can do multiple return values from a function. So in order to show you why this is valuable, let's take this example here. So I've created a simple divide function that takes in two parameters, a and b, that are float 64s. It's going to divide them and it's going to return that result back. So if I run this, I get 1.66666, like you might expect, and everything's fine. But what happens if I pass in a 0 here? Now when I run this, I get an unknown result. I get a positive infinity result, and I can't work with that in my application. So I'm going to probably cause some sort of a failure down the line. So in a lot of languages, the only thing we could do is throw an exception or panic the application in Go when we detect that there's this invalid value for the parameter b. So I guess we could do that. We could add some kind of logic here. If b equals 0.0, then we're going to panic, and we're going to say cannot provide 0 as second value. And that would work. But keep in mind, when we talked about control flow in Go, we don't want to panic our application as a general course of action, because panicking means the application cannot continue. Now, in fact, this application cannot continue if somebody provides a value of b. But it's reasonable to assume that we might pass 0 in for this b parameter occasionally. So instead of doing this, what we actually want to do is return an error back, letting the calling function know something that they asked it to do wasn't able to be done properly. So instead of doing this, we're actually going to add a second return variable. So to do that, we're going to add a paren here, and we're going to return an object of type error, and then close that parenthesis off. So we can return as many values as we want from a function, but this is a very idiomatic way of using the Go language. So we're going to return the intention of the function as the first return value, and then we're going to return an error object in case something went wrong. So in that case, what we're going to do is we're going to remove this panic, because we really don't want to be doing that, and we're going to return the first value. We're just going to zero it out because we can't do this operation, so we can't return anything meaningful. And then we're going to return an error object. Now you can generate one of those by using the errorf function, and we can say cannot divide by 0. So we're going to provide a value for that error, and then that's all we need to do here. So since we've returned out of this function in the error case, then if we get past it, we can continue as if our parameters are okay. And so in that case, we can actually do our operation. And then for the error value, we're going to pass nil because no error was present. And again, this is very idiomatic Go. We're going to return an error value if something went wrong, and then we're going to explicitly return nil if nothing went wrong. And then if you've read any amount of Go code, you've seen this quite a few times. We're going to check to see if that error, so we got our standard if error is not equal to nil, and then we're going to put our error handling logic in here. So in this case, all we're going to do is print out the error and return from our main function, so we're going to exit our application. If we don't have that, then we're going to just print out the result of our calculation. So again, this is a very common pattern in Go. Inside of your functions that can generate errors, you're going to return the expected value and then an error as the second parameter. Then you're going to have a guard that's going to check for those error conditions. You're going to return as soon as possible from your function with the error value if an error is present. And the reason for that is we're going to try and left justify our code as much as possible, so we don't end up with these pyramids of doom where we're going to have else checks and we do all of our error checking at the bottom. We're going to do our error checking at the beginning and then return out as soon as possible. So if we do get past that, then we're going to be on our happy path and we're going to return out the result of our calculation and then a nil error. Up in the calling function, we're going to have the standard test to see if error is not equal to nil. If it isn't equal to nil, then we're going to process that error because now we've got something we're going to have to deal with. And then again, we don't have an else block here. We just continue moving on. We're going to make sure our error handling logic either recovers from the error or exits out of the function. And that way we can keep our main thread of execution left justified. So our main thread of execution here is we're going to call this divide function and then we're going to print out the result. So any error handling should not force the main line of execution to be indented. So now if we run this, we see that I forgot to initialize my error parameter. So let's go ahead and add that. And this is something else I should talk about. When we're receiving multiple values out of a function call, we actually have a common delimited list of those return values. So this D parameter is going to match up to this float 64, and this ERR parameter is going to match up to this error parameter here. So now if I run, everything should work. And we see that we now get an error, cannot divide by 0. So our main function doesn't explode on us. We actually have something that we can work with. But if we put in a valid value, then we're on that other path of execution and we get the return value back out. Now, so far, we've been treating functions as this special thing because we're always using this func keyword. We're declaring these at the top level of our application, and we're working with them. But functions in Go are actually more powerful than that because functions themselves can be treated as types. They can be passed around as variables. They can be passed as arguments into functions. You can get them as return values. Pretty much anything you can do with any other type, you can do with functions. So let's take a look at that a little bit. So in this example, I'm actually declaring a function on the fly, and this is called an anonymous function. Now, we're going to continue to explore this over the next couple of minutes, but this is the simplest example I could come up with. So notice that I'm starting with the func keyword. I've got the parens for the parameters. I've got the opening and closing curly brace, but I don't have a function name here. So when you're doing this is what's called an anonymous function. And this is the basic structure of a function when you're not working with functions in this traditional scope, but instead you're working with functions as types. So inside of my function body, I'm printing out the message hello go, and then I've got accompanying my closing curly brace, these parens here. Now these parens here are basically going to invoke this function. So this is an immediately invoked function. I'm defining it and executing it at exactly the same time. So when I run this, it actually does execute that function, and we get the value hello go printed out. If I don't have these parens, then the compiler's a little confused. It doesn't know what to do with this function. It's just defined, but it's never used anywhere, so it fails a compilation check. But if I do invoke that function immediately, then I get this behavior here. Now, why would you use an anonymous function like this? I actually have no idea why you would use an anonymous function like this. I mean, there can be situations where you can declare variables inside of here. So if I declare a message variable here, and I set that equal to this string, and then print that out, that can be valuable because you're actually generating an isolated scope. So this message variable is not going to be available in the main function. It's only going to be inside of this anonymous function here. Now, another place that you might use this is if we've got a for loop. So if I start up a simple for loop, and I'll just count up to 5 and increment by 1. See if I can do this on the fly here. And then I come in here and I actually print the value of I out. So I'll get rid of this message here and I'll print out I. You're going to get a little bit of strange behavior. If I run this, this works okay. But as we start getting into asynchronous code, things are going to start behaving a little bit oddly. So we do have access to this I variable because we're in the scope of the main function. And so inner functions can actually take advantage of variables that are in the outer scope. But the problem is, if this function is actually executing asynchronously, then this counter variable is going to keep going, and we may actually have odd behavior here. So the best practice is actually to provide a variable inside of here and actually pass that I variable. And what that's going to do is we're not going to be reading from the outer scope anymore. We're going to be passing that into the function execution. And that way, even if this is running asynchronously, we're going to print out the value correctly. Now, this works correctly in the playground the way that we have this right now because we actually aren't doing anything asynchronously. This is all synchronous execution. And so we are safe to use this outer counter, but it's not good practice to do that. Instead, it is best practice to pass in that counter variable if you need that in your inner function. That way, changes in the outer scope aren't reflected on the inner scope. Now, taking this a little bit farther, we can work with functions as variables, like I said before. So in this case, I've declared an anonymous function, and I've assigned that to this variable f, and then I can execute f by just invoking it like any other function. So if I call that, we see that we do print hello go out. So now that I've got this function defined as a variable, it's free to pass around my application. Now, you might ask yourself, what is the signature for this function? So let's go ahead and go through that. So if I get rid of the short syntax and extend this out a little bit, then I'm going to start with the var keyword. And since this is a very simple function, the type is just like this. We have the func keyword and then an open and close parenthesis. So the parameters normally go in here. I don't have any parameters here. I don't have any return types. So the type signature for this variable is simply func with 2 parens there. So if I run this, that works just fine. Now we can go a little bit more complicated, and I'll drop an example of that in just to show you how that's going to look. So in this case, I'm declaring a function signature for a divide function. That's going to take in 2 floats, and it's going to return a float and an error. And you see this is the syntax for that. So we pass our parameter types in here, and then we have the return types in parens as well. If you have just a single return type, then you don't need these parens. We could just put the type there like that. But we do have that error type that's coming back, so we do need to include that. And then when I initialize that variable, I'm going to set it equal to an anonymous function that takes a and b. And this is exactly the same divide function that we had before. and I can call that exactly like we had before. So when I run this, it has exactly the same behavior as the last example we did with the divide function, but now we have the divide function declared as a variable, and we're working with it exactly the same way as when we declared it as a function. Now the difference between this and when we had the divide function declared globally is if I try and call it up here and run the application, notice that I get an error, because in this case, the function divide hasn't been declared yet because it's declared as a variable, and so I can't work with it yet. So that's just something to be aware of. If you're going to be working with functions as variables like this, make sure that they're defined before you actually try and execute them. Okay, the last thing that I want to talk about with functions today is working with what are called methods, and there's a couple of things to talk about with those. So let me just drop in an example that shows that, and we can walk through this and then see what it's going to do. So in this example, I've got a struct called greeter. That greeter struct has two fields, greeting and name, and then I've got this method on it, and we'll come back to this in a second. So in my main function, I'm declaring a greeter struct, and then I'm calling this function, preceding it with the struct that I have here. And this is how we're going to do method invocation. So we call the method just like we were accessing a field, except for we have the params here where we can pass some arguments in. Now my method declaration down here looks a lot like a function, except for it's got this odd bit right here. And this is what makes this function into a method. So a method is basically just a function that's executing in a known context. And a known context in Go is any type. Now it's very common that we can use structs, but you can use any type. So we can make a type for an integer. So maybe we have a type for an integer called counter, and then we can add methods onto that counter type and work with those. So when we declare that method, we're actually going to get access to that type right here in this part. So what's going to happen when we call the greet method is the greet method is going to get a copy of the greeter object, and that's going to be given the name G in the context of this method. So then when we print out, we can access the fields on that greeter object, so we can print out the greeting and the name. So when we go ahead and run this, we see that we get hello go printed out, and that's the basics of a method. So methods are basically the same as functions. They just have this little bit of syntactic sugar that's providing a context that that function is executing in, and when we do that, we call that a method. Now when we use this syntax right here, notice that we're specifying greeter as a value type. We don't have a pointer here. So this is what's called a value receiver. The received object in this greet method is the value greeter. So what that means is just like any other time that we're working with values, we are getting a copy of the struct. We're not actually going to get the struct itself. So if I change the value of the name field here, and then I print the name field out up here, so I say the new name is, and then I print the name field out, then it's no big surprise that even though I assigned an empty string to the name field here, up here in the main function, it didn't have any effect. Because down here in this method, we're operating on the copy of the greeter object. We're not operating on the greeter object itself. So again, that's very valuable if you want your methods to be able to access the data of their parent type without being able to manipulate it. Just keep in mind there is a cost with that. So if this greeter object was a very large struct, then we would be creating a copy of that struct every time we invoke this method. Now, as you might expect, there's another option that we have here, and that is to pass in what's called a pointer receiver. So if we make this a pointer and run the application again, now we're actually able to manipulate that underlying data. So we're going to print out hello ghost, so the method operates in exactly the same way, and we don't have to change the format here because we do have that implicit dereferencing of pointers that's working for us. But now when I change the value of the name field and print the name field out up here, we do in fact see that we've been able to reassign the value of that field. Okay, so that covers working with functions in the Go language. Let's go into a summary and review what we've talked about. In this video, we talked about functions and how to use them in the Go language. And we started out by talking about the basic syntax of a function. And we saw that this is about as simple of a function as we can get. So we start with the func keyword. We have a name for that function, and again, if that first letter is uppercase, then that function is going to be published and allowed to be executed from outside of the package, but with a lowercase first letter, it's going to be kept internal to the package. Then we follow with a matched set of parentheses, and then we have an open and closed curly brace. Now the open curly brace has to be on the same line as the func keyword, and the closed curly brace has to be on its own line after the final statement of the function. Then we moved on to talk about parameters, and parameters allow us to pass data into the function to influence how that function executes, basically providing some variables for the function that are passed in from the outside. So we talked about how parameters are passed in as a common delimited list of the name of the parameter and the type of the parameter. So we see here we're passing into the foo function two parameters, the bar parameter that's of type string and the baz parameter that's of type integer. Parameters of the same type can be comma delimited, and the type can be listed at the end there. So in this case, we're passing in bar and baz as parameters, and both of those are going to be of type integer. When pointers are passed in, the function can change the value in the caller. So by default, we're going to be passing in the values themselves, and so the Go runtime is going to be copying that data and passing it into the function, so any changes that are made inside of the function aren't going to be reflected in the caller scope. However, if you pass in a pointer, then you are going to be able to manipulate the value inside of your function, and that will have an effect in the calling scope. So the only exception to this rule is when you're working with slices and maps. Since they work with internal pointers, any changes inside of the function to the underlying data is always going to be reflected inside of the calling scope. We also talked about how you can use variadic parameters to send a list of the same types in. So it must be the last parameter in the parameter list. It's received inside of the function as a slice, and you see an example of the syntax right here. So we've got the function foo. It has one parameter bar that's of type string, and then a parameter baz that's a variadic parameter of integers. So inside of this foo function, we're going to have a slice called baz, and that's going to contain all of the integers that have been passed in. Once your function finishes doing its work, a lot of times we want it to return a value back out. And in order to get that information back out, we're going to use return values. So if you have a single return value, all you need to do is list the type. So in this case, our foo function needs to return an integer. We can also specify multiple return values. So if we're going to do that, we need to put parens around the types that we're going to be returning. So in this example, we're going to be returning an integer and an error. And this is a very common pattern that you're going to see in Go applications, where we're going to have our functions return the intended value and then an error value that's going to let the caller know if anything went wrong. That way, the function itself doesn't have to determine whether the application needs to panic or execution can't continue. It just knows it wasn't able to do what it was asked to do, and then it can delegate what that error means to the application to the calling function. You can also use named return values. So when you do that, instead of just providing the types in the return list, you're going to provide the name of that return value. So when you do that, the runtime is going to initialize that value for you to the 0 value for that variable. And when you use the return keyword, all you need to do is enter return on its own. Go is going to find the current value of those return variables, and that's what's going to be returned out of your function. Another special behavior of Go is you can actually return the addresses of local variables as return values, and those are going to be treated properly. So when you do that, those variables are automatically promoted from local memory or stack memory up into shared memory or heap memory, so you don't have to worry about those values being cleared out as the function's stack memory is reclaimed. We then started talking about anonymous functions, and we talked about a couple of different uses for those. So we have this immediately invoked function, which really isn't used too often in the Go language, but it's as simple of an anonymous function as I could get. The only potential advantage that you have here is that you can create an inner scope, so local variables that are created inside of this anonymous function aren't going to be available outside, but I haven't seen that very often. It's not going to be very often that you're going to need to use this kind of a function. Then we also talked about how we can take that anonymous function and actually assign that to a variable. So in this example, we've got the variable a assigned to the value of that function. And then we can invoke the a function just like any other function. The only difference between this and the normal declaration of a function is that the a function can only be invoked after it's been declared. So when you declare a function using the traditional syntax, it's actually declared at the time that the package is initialized, and so it's always available to you. When you're using this syntax, you have to make sure that a is initialized before you can call it. Extending on that discussion about the ability to assign functions to variables, functions are types just like any other type in the Go language. Anytime you can use a primitive or a slice or an array or a map, you can use a function. So you can assign them to variables, you can use them as arguments, they can even be return values from functions. Then we also talked about how, since a function is a type, we have to have the ability to create a type signature. So if you're declaring anonymous functions, it's often most convenient just to use that : syntax and declare your anonymous function, and the type is going to be inferred. However, if you're using a function as a parameter to another function, or as a return value from a function, then you're going to need to specify that type signature. So we see an example here. In this case, we've got the definition of a function f, and that function is going to take 3 parameters, 2 strings and an integer, and then it's going to return an integer and an error type. So it's basically the same as when you're declaring a function normally. The only difference is we don't have the names for those variables, because those names will be provided when we actually implement the function. We just need to know the types that are coming in and the types that are coming out at this point. The last thing we talked about were methods, and how a method is a special type of function that executes in the context of a type. Now, a type doesn't have to be a struct, although that definitely is a very common use case for methods. You can actually attach a method to any custom type. So you can create a type of an integer, and then you can add methods onto that integer. When we create a method, we're going to use a modified version of the basic function syntax. So before the name of the function and after the func keyword, we're going to provide another set of parens. We're going to provide a local name for the type that's going to receive that method, and then we're going to follow that with that method type. Now that variable is what's called the receiver for the method. So in this case, our G variable is what's called a value receiver, which means we're going to get a copy of that greeter object, and that's going to be passed into the greet method. However, we can also use what are called pointer receivers. So by adding an asterisk in front of that greeter type, the method is going to change. So instead of passing a copy of the greeter, we're going to get a pointer to the greeter object in there, and then any manipulations we make to the greeter object in the greet method are going to be reflected throughout your application. Now that's very powerful if you need the method to be able to manipulate the state of the object. It's also much more efficient if you're dealing with large structures, because instead of copying the entire structure, it only has to copy a pointer, and that's normally a much more efficient operation. I want to talk about one of the coolest features of the Go language, and that is interfaces. Now I know that interfaces are normally considered pretty humble features and they sit in the background. It's much more fun to talk about Go routines and channels, especially when you're learning the Go language. But I would argue that the way interfaces are implemented in the Go language are potentially one of the reasons why Go applications tend to be as maintainable and scalable as they have proven to be. So we're going to start this conversation like we start every conversation by introducing the basics. So we'll learn what an interface is and how to use them in the language itself. Then we'll move on to discuss how to compose interfaces together. Now, just like in other high-level languages such as Java or C#, we can actually make interfaces of interfaces, and we'll talk about how to do that and why that's a very good thing to do when you're writing your Go applications. Then we'll talk about type conversion. Now, we've touched on this a little bit before in a previous video, but when we talk about interfaces, things change a little bit, and it's worth revisiting the topic. Along the way, we're going to talk about the empty interface, which is a very useful general construct that we're going to deal with in our programming. We'll also revisit type switches, which we've talked about before, and we'll revisit them in the context of our interface discussion. Then we'll talk about how to implement interfaces, and there's actually two different ways that you can do that. One is by implementing with a value type, and one is by implementing with a pointer. And we'll talk about some of the subtle differences that you're going to run into as you implement interfaces with these two different types. And then finally, we're going to talk about some best practices that have been discovered over the last few years of working with the Go language about how to use interfaces in your actual production applications. Okay, so let's get started by learning the basics of using interfaces in Go. So to start our discussion about interfaces, I'm going to actually build our first application up a piece at a time. Now, often I just drop in code and talk about it, but I want to take this one step at a time so that we're working together and understanding what's going on. So the first thing that we're going to do is we're going to introduce our first interface. So interfaces are a type, just like structs or type aliases. So we're going to start with the type keyword, then we're going to enter the name of our interface, and then the type that we're creating is a type interface. And then we're going to surround the definition of this interface with curly braces, just like we do when we're defining a struct. Now with a struct, we would add in here the data that we want that struct to hold on to, because structs are ultimately data containers, and so that's how we work with them. Interfaces don't describe data, interfaces describe behaviors. So instead of entering a bunch of data types that we're going to be storing inside of our writer interface here, we're actually going to be storing method definitions. So I want to create a write method here, and this is actually an interface from the IO package. We're just going to be working with it here as if we created it. But this is exactly the same interface that you would find in the IO package under the writer interface. So this method is going to accept a slice of bytes, and then it's going to return an integer and an error. Now in the writer interface, the way this works is anything that implements this interface is going to take in that slice of bytes, write it to something. That something might be the console, it might be a TCP connection, it might be the file system. We don't know. We just know that we're writing a slice of bytes to something. And then the integer and error that get returned, of course the error is there in case something goes wrong with the write operation, and the integer is normally the number of bytes written. So now that we have the interface defined, let's go ahead and implement it. So we're going to implement this with a console writer implementation, and that'll be a struct. And that's all we need to do with the struct definition. Now, if you come from another language, you might be looking for an implements keyword or something like that. Well, in Go, we don't actually explicitly implement interfaces. We're going to implicitly implement the interface, and we're going to do that by actually creating a method on our console writer that has the signature of a writer interface. So let me just drop that in, because if I try and type all this out, I will screw it up and then I'll have bugs that I have to go through. So it's much easier just to drop it in. But notice what I've done here. I've got a method on my console writer called write. So it's got the same name as my writer interface. It's accepting a slice of bytes, and it's returning an integer and an error. Now the implementation is whatever I want it to be. Now in this case, all I'm going to do is convert that byte slice into a string and print it out to the console to keep things easy in the playground. But I could have my writer do whatever I want. So what's the value of doing this? Well, the value of doing this is up in my main method, I can actually create a variable that's of type writer, and let me just drop that code in and format it, and set that equal to a console writer instance. So the W variable here is holding a writer, which is something that implements the writer interface. I don't actually know the concrete type though. So when I call the write method down here on line 9, I know how to call that because that's defined by the interface, but I don't actually know in my main function what's being written to. That's the responsibility of the actual implementation. So I could replace this with a TCP writer, I could replace it with a file writer, I could replace it with any other kind of writer, and so I get what's called a polymorphic behavior. Line 9 doesn't care what it's writing to. I specify that behavior before that, but then anything that's going to use this W object just knows that it can write to it, and so it can take advantage of that behavior. So if I go ahead and run this application, you see that I do get Hello Go printed out to the console, just like I would expect. So the key takeaway here as we're learning the basics of interfaces is this concept of implicit implementation. So what that means, for example, is if you need to wrap a concrete type and somebody hasn't published an interface, you can actually create an interface that their type implements. So we did it the other way. We created an interface and then we created a concrete type that implemented it, but there's nothing to say we can't go the other way around. We could, for example, go to, if I travel to Golang.org and go into packages, this is actually something that I just ran into in order to test SQL database connections. So if I come down to the database package and go into the SQL package, if we look at this, notice that the DB type is a struct. So we don't have an interface here. So if our Go application is talking to a SQL database, we've got concrete types all over the place. So for our transactions, we're interacting with this DB object. Everything that we're doing, sending SQL statements, making queries, are all through this concrete DB object. So how do I test that without a database? Well, the way that you test that without a database is you actually create an interface that replicates this method signature, and the DB object from the SQL package will automatically implement it. So I don't have to worry about creating interfaces at design time if I don't need them for myself, because consumers of my library or whatever I'm creating can always create interfaces later, and their interfaces can be shaped to exactly what they need for their application. Now, another thing that I want to talk about before I move on here is a naming convention. Now, obviously, the name of the interface should represent what that interface is going to be doing for you. And there is one special case. If you've got single method interfaces, which are very common in the Go language, then the convention is to name the interface with the method name plus ER. So if we're defining an interface like we have here with the write method, then the interface name should be writer. If we're going to create an interface with a read method on it, then the interface name should be a reader. Now, if you got more than one method in the interface, things can get a little bit more challenging, but at the end of the day, you should name your interface by what it does, and in the case of a single method interface, just add ER onto the end of the method name. Okay, now in this example, we used a struct, which is probably one of the most common ways to implement interfaces, but you don't need to. Any type that can have a method associated with it can implement an interface. And as we've talked about before, any type can have methods associated with it. So in order to demonstrate that, let me just drop in this example here. Now in lines 16 through 18, I've defined a new interface called incrementer, and that increment is going to be a method that only returns an integer. So it's going to increment something. So whatever we're going to implement this thing with is going to increment values. So down here on line 20, I defined a type alias for an integer called an int counter. And then I've added a method to that custom type on lines 22 through 25, and that's going to be my implementation for the incrementer interface. So the method name is called increment, and it's going to return an integer. Now in this case, look at what I'm doing. I'm actually incrementing the type itself. Since I've got a type alias for an integer, it's a number, so I can go ahead and increment that, and then I'm going to return it as the result of this method call. So I've actually got a type defined on an integer, and the integer itself is storing the data that the method is using. So up here in my main function, I'm going to go ahead and create that integer counter, and I have to cast an integer to an int counter in order to do that. That's what I'm doing here on line 8. And then I create my incrementer and assign that to a pointer of the myInt object, and we'll talk about why that has to be a pointer toward the end of this video. And then I'm just going to loop from 0 to 9, and I'm going to print out the value of the increment method every time I call it. So if I go ahead and run this, I see no big surprise, I get the values 1 through 10 printed out. So what's the takeaway here? Well, you don't have to use structs to implement interfaces. You can use any kind of custom type. Now, I couldn't add a method directly to the int type because the int type isn't under my control. That's defined in another package, and as a matter of fact, that's a primitive type and you can't modify it. But any type that I do have control over that I can create, I can add methods to it, and if I can add methods to it, I can implement interfaces with it. Now, the next thing that I want to talk about is how to compose interfaces together, because this is another very powerful concept in the Go language and is one of the keys to scalability. Because if you remember, I mentioned a little while ago, single method interfaces are very common and very powerful in the language because they define a very specific behavior, but by having a single method, they don't have a lot of opinions, and so they can be implemented in a lot of ways. So for example, the io.writer interface is one of the most common interfaces in the entire Go language because all it does is talk about how to write to things. And we write to things all the time. So by taking as little opinion as possible, we actually make the interface very, very powerful and very, very useful. So let me go ahead and paste this example here, because what happens if we need more than one method, but we can decompose the interfaces down? So in this case, I've created an interface that's composed of other interfaces. So I've got my writer interface that we started the video with, and then I've added this closer interface that just has a close method on it and returns an error, just in case something happened when we tried to call this method. Now the writer closer interface is actually composed of the writer interface and the closer interface. And this is done exactly the same way that you do embedding with structs. We're just embedding interfaces within other interfaces. So the writer closer is going to be implemented if an object has this method on it and this method on it. Then we can treat that as a writer closer. So as an example, I've created this struct here, a buffered writer closer. Now I'm not saying that this is an efficient way of doing things. This is just an example of how you might use this writer closer interface in a way that runs in the playground easily. So in this case, I've got my write method that I'm going to be implementing. And what I decided to do is I'm going to write out whatever gets sent into the buffered writer closer. I'm going to print that out to the console in 8-character increments. So that's what all this code is doing. When you pass data into the write method, it's going to store that in this internal buffer that the struct defines. And then as long as the buffer has more than 8 characters, it's going to go ahead and write that out, but it won't write anything out if it's got less than 8 characters. So we're basically buffering the data that we're sending in. And then down here in the close method, I've got to implement that too. And so what we're going to do there is we're going to flush the rest of the buffer. So I'm pulling the next 8 characters out, and I'm going to write that out to the console and keep doing that until the buffer is empty. Okay, up here in the main method, I simply create a writer closer variable and define that using the new buffered writer closer function. And just to show you that, I didn't talk about it. That's down here at the bottom. That's just a constructor function that's returning a pointer to a buffered writer closer. And I need to do that because I need to initialize this internal buffer to a new buffer. So I have a constructor method there just to make sure that everything's been initialized properly. So if I come back up to the main function and look at that, then I'm going to call the write method. And I'm converting the string, hello YouTube listeners, this is a test, over to a byte slice because that's what the write method expects. And then I'm going to call the close method. So if I go ahead and run this, you see that I get the message printed out to the console in 8-character chunks. And eventually I get all this printed out. But if I comment out this last method call here, you see that I don't get the a-test part of the string because that's actually a partial. And so we didn't get that full 8 characters that's required for the write method to print it out. And so I didn't actually flush the buffer. Okay, So I know that may be a little bit of a complicated example to show a fairly simple thing, but I just wanted to show you this is how you can compose interfaces together. And as long as you implement all of the methods on the embedded interfaces, then you actually implement the composed interface as well. The next example that I want to talk about is how we can do type conversion. So I'm going to go ahead and replace my main function here with this code here. Get rid of the extra curly brace. Actually, I'm going to get rid of this too. I guess I pulled in the whole function signature. And then I've made a little bit of a change down here on line 13. So lines 9 through 11 are our original implementation, where we're creating the new buffered writer closer, we're writing a string out, and then we're calling the close method on it. But on line 13, I'm actually doing a type conversion. So using this syntax here, where I've got an object, dot, and then in parens, I've got a type that I'm going to try and convert this variable to, and then I can assign that to a variable such as this BWC variable right here. Now, if that succeeds, then everything's fine and I can go ahead and work with it. Now, there's nothing useful I can do with this, but I'm just printing out the variable because I have to use the variables in Go. So I'm just going to go ahead and print that out. So if I run this, I see I get exactly the same output I had before, but now I get the memory address of this buffered writer closer. So that type conversion succeeded, and therefore I can work with this no longer as a writer closer, but as a buffered writer closer. So for example, if I needed to access the buffer directly, then I would be able to do that now, whereas with the writer closer, it's not aware of the internal fields of a specific implementation, and so I wouldn't have access to that data. Now there is a problem, however, if I import the I/O package and try and convert this to a type that it doesn't implement. So for example, if I try and convert this over to an I/O reader, which is another interface, and that I/O reader interface requires a read method on it. So if I try that now, let's go ahead and run that, and we see here we've put the application into a state that it can't manage. And so what it does is what every good Go program does when it can't figure out what to do, it panics. And the panic message is interface conversion. It can't figure out how to cast a buffered writer closer into an I/O reader, and so it's going to fail on us. Now it does give us some useful information about why it couldn't do that. It says it's missing a method read, and then it's going to give us a stack trace letting us know where that error occurred. Now this isn't really great, because sometimes we need to try and convert an interface into something else, and we're not sure if it's going to work or not. So it's not going to be good for our application to be panicking all the time, because then we're going to have recovers and we're going to be using that as a primary control flow concept, and we want to avoid that in the Go language because panicking is pretty expensive, so we need another way around it. Well, we just so happen to have another way around it. And so I'm going to show you that. All we need to do, let me rename this variable because BWC doesn't make sense for a reader anymore. I'm going to paste this code in. So I'm going to now try and cast it to a variable called R. I'm going to do the same type conversion, but now I'm using this comma OK syntax. So we've seen this before when we were trying to pull a value out of a map and we weren't sure if it was there or not. Well, we have the same ability with type conversion. If we add a comma OK, this is going to be a Boolean result, and then we can test against that to see if we can work with it. So if the conversion succeeds, then we're going to get an OK value back out. If the conversion fails, then we're going to get the 0 value of whatever type we were trying to convert to. So an I/O reader is an interface, and so its 0 value is going to be nil. So if we go ahead and run this now, we see that our conversion failed, but our application didn't crash. If we switch this back to a pointer to a buffered writer closer, let me go ahead and drop that in, and we run that, we got to drop out our package here that we're no longer using. And then we see that we're back to having things successfully converted, and we could work with that however we needed to. So this is really important to be aware of, especially if you're not sure if you're going to get a pointer or a value type. So for example, it would be really easy to write this and have a problem because we implemented the interface with a pointer, not with the value itself. And so we can't actually do the conversion to the underlying value type. So let's go ahead and run this again. We see that that all works. And one more thing I want to show you. Let me just pull this error back up again. You notice that the reason this type assertion failed is because buffered writer closer does not implement writer closer. Now that might seem a little strange to you because our buffered writer closer has a write method and it has a close method and they have the right signature. So for some reason this works when I ask it to convert it to a pointer, but it doesn't work when I ask it to convert it to the underlying value. Now we'll come back in just a second and talk about why that happens, but I want to finish our discussion of type conversions first. So stay tuned and we'll talk about why that works the way it does. So the next thing that I want to talk about is something called the empty interface. Now the empty interface is exactly that. It's an interface that has no methods on it. And we describe that using this syntax here. Now this isn't a special symbol, this is just an interface that we're defining on the fly and we don't have any methods on it. So it's called the empty interface, but there's nothing special about it. We could create this as the empty interface exactly the same way by just deleting the method out. And that's an empty interface now. So you see it like this all the time. Just be aware, there's nothing special about this. It's just an interface defined on the fly that has no methods on it. Now the nice thing about the empty interface is everything can be cast into an object that has no methods on it, even primitives, because, well, an integer has no methods, and so it can be cast to the empty interface. And so this can be very useful in situations where you've got multiple things that you need to be working with, but they aren't type compatible with one another, and you need to apply some logic later to figure out exactly what you received. But we do have a problem with the empty interface. Because we now have this myObj variable that's defined as an empty interface, we can't actually do anything with it, because myObj has no methods that it exposes because it's an empty interface. So in order to do anything useful with a variable that has the type of an empty interface, you're going to need to do either a type conversion or you're going to need to start using the reflect package in order to figure out what kind of an object you're dealing with. So in this case on line 10, I'm actually trying to typecast into a writer closer, and I'm using the OK syntax to see if that worked. If it does, then I go ahead and call the write and close methods like I saw before, and then I've got this other type conversion that I've done down before just to keep things consistent. So if I run this, we see that I forgot to re-import the IO package, so let me go ahead and pull that back in. And we see that everything works as normal. So the empty interface is very common, but just keep in mind, it's almost always going to be an intermediate step. You're going to define a variable of the type empty interface, and then you're going to have to figure out exactly what you received before you can do anything useful with it. The last thing that I want to talk about in the context of type conversions are type switches. So I want to revisit that conversation from a few videos ago. And just to show you, we can do something like this. So in line 8, I've got a variable I that's defined as the empty interface, and I'm setting it equal to the integer 0. And then I'm going to use this switch block here, and I'm going to use this syntax. So I've got my variable name, I, and then I'm going to use this dot, and inside of parens, I'm going to put type. And so what this is called a type switch. So each of the cases in this type of switch are actually going to be a data type. So in this case, I'm looking to see if I've got an integer or a string, or I've got a default case, which is going to be handled by our application just saying it doesn't know what I is. So if I go ahead and run this, I properly identify I as an integer, so we execute this case here. If I put parens around this, then of course I is now going to contain a string, and so if I run that again, it identifies I as a string, and if I change this once again, maybe we can make this a boolean, I got to spell true correctly, and I run that, then it has no idea what I is. So this is commonly paired with the empty interface in order to list out the types that you're expecting to receive, and then you would add in the logic of how to process those different types. Now I promised you that we would come back and talk about that weird type conversion behavior where we could convert our writer closer into a pointer to a buffered writer closer, but we couldn't convert it into the value itself. So now I want to go through and have that conversation about why that happened. So let me just drop this code in. This is a much simpler implementation than what we had before. I've actually not really implemented these methods anymore in order to keep things as clean as possible for you to see. So all I'm doing is I'm going to create a myWriterCloser, and that's down here as a myWriterCloser struct with nil implementations for the methods. But I do have the methods implemented, so I can create this object as a writer closer. And then I'm just printing out the value of the variable just so we have some use for that variable so the Go runtime will actually compile and run this. And the interface for the writer closer is defined exactly the way we had before. So if I run this, everything works out just fine. However, what happens if I change the receiver of one of these methods to a pointer? Well, if I run this now, I get an error. And the reason that I get that error is it can no longer convert my writer closer into a writer closer interface. And it gives us an interesting message here. It says my writer closer does not implement writer closer. The write method has a pointer receiver. And this is the key to understand what happened with this. So when we define types and we assign methods to them, each one of those types has what's called a method set. Now, when you're working with the types directly, the method set is all of the methods, regardless of the receiver types, associated with that type. With interfaces, however, things change a little bit. When I implement an interface with the concrete value, so notice here I'm creating a MyWriter-Closer. I'm not taking the address of a MyWriter-Closer. I'm using MyWriter-Closer directly. So WC is defined as holding the value MyWriter-Closer. So the method set for a value when we're talking in the context of an interface is any method that has a value as the receiver. So the reason we're not implementing writer-closer is because a write method no longer has a value receiver, it's got a pointer receiver. And so its method set is incomplete. Now we could fix this by using the address of operator and running again, and notice now everything works. And the reason for that is the method set for a pointer is the sum of all of the value receiver methods and all of the pointer receiver methods. So let's go through that again. When I'm implementing an interface, if I use a value type, the methods that implement the interface have to all have value receivers. If I'm implementing the interface with a pointer, then I just have to have the methods there, regardless of the receiver type. So the method set for a value type is the set of all methods that have value receivers, but the method set for a pointer type is all of the methods with value receivers as well as all of the methods with pointer receivers. So there's a couple of ways that we could fix this. Now in this case we don't need access to the underlying data, so we could just go back to a value receiver, and then this is going to work just fine. This is actually the initial example we had. If we have one method that's got a pointer receiver, however, we're going to need to switch that over to a pointer type. And notice I can actually remove this, and it continues to work, or I can make both of these pointer receivers, and this continues to work as well. So this is an important concept when you're implementing your own interfaces. If any of the methods require a pointer receiver, you're going to have to implement that interface with a pointer. If not, though, if all of the methods accept value types, then you can go ahead and use a value type if that's what you want, but you could also use a pointer. Okay, the last thing that I want to talk about are some best practices when using interfaces in your own Go applications. So let's take a look at those. Okay, when we're working with interfaces, there's a couple of rules and guidelines that I'd like you to keep in mind. And these have been developed over the last few years by the Go community and are generally accepted as some of the best ways to use interfaces if it's practical in your applications. The first is prefer many small interfaces versus large monolithic ones. Now, if you need large monolithic ones, that's fine. Go ahead and compose smaller interfaces together to make those. But the smaller you can make your interfaces, the more useful and powerful they're going to be. And that's not actually unique to Go. No matter what language you're working in, if interfaces are there, generally having many smaller interfaces is preferable in the long run to having a few monolithic ones. Now, some examples that are in the Go standard library are the io.writer interface, the io.reader interface, and the empty interface. Now, these are arguably three of the most powerful interfaces in the entire language. And if you think about it, writer has one method, reader has one method, and the empty interface has 0 methods. So it's interesting support to the argument that smaller interfaces are better, that some of the most powerful interfaces in the language contain 1 or 0 methods on them. Now, when you're working with interfaces, if you're coming from a language that has explicitly implemented interfaces, you're going to be very tempted to create interfaces and export those. So here's the guidance for that. If you don't need to export the interface yourself, so if you don't have any particular reason to do it, go ahead and don't. So there are some good examples of why you would want to do that, but often it's perfectly acceptable to export the concrete type. I'll take as an example the database/SQL package that we looked at earlier in the video, where we saw that the DB object was exported as a concrete struct, and it had all sorts of methods that pointed to other concrete structs. So you can't directly mock that out for testing right out of the box. However, by not exporting an interface, it allows you as the consumer of that struct to define your own interface that you can use for testing. And the beauty of that is, if you don't use every method on the DB object, your interface doesn't have to have every method on it. You can just expose the methods that you need. However, do export interfaces for types that you will be using. So if you're going to pull a value in, go ahead and accept an interface instead of a concrete type if at all possible. So this is going to be almost exactly backwards from how other languages consider interfaces, and the reason is that whole idea about implicitly implementing interfaces instead of explicitly doing it. So if you were working in Java or C#, you could not do this. because you have to define the interface before you implement the interface because they're explicitly implemented. But since Go has implicit implementation, you can go ahead and defer the creation of the interfaces until exactly when you need them. So if you're creating a library that other people are going to consume, you can define the interfaces that you accept, and then they can provide whatever implementations that they want. Now, if your library has reasonable defaults, then you could export those concrete types as well, but make sure that you're accepting interfaces whenever possible. And that's what this third point is talking about. Design your functions and methods to receive interfaces whenever possible. Now, that's not always possible. If you need access to the underlying data fields, then certainly take in the concrete types. But if you're accepting behavior providers, then go ahead and try and accept those as interface types instead of the concrete types. Okay, so that covers what I want to talk about with interfaces today. Let's go into a summary and review what we've talked about. In this video, we've talked about interfaces and how to use them in the Go language. We started with a discussion of the basics of interfaces, so how to create them and how to implement them. And we ended up with code that looks something like this. So we're defining an interface as a type. So we're going to start with the type keyword, the name of the interface, and then the keyword interface. And then inside of curly braces, things are going to be a little bit different than if we were defining a struct, for example. If we were defining a struct, we would put data fields inside of the curly braces because we're defining the data that that structure is holding. With interfaces, we're defining behaviors, however. So instead of adding data fields, we're going to add method signatures. So we see here in this example, we're going to define a write method that accepts a slice of bytes and returns an integer and an error. And then we implement that interface by creating a method on our type that has the same signature. So we don't have to explicitly state that we're implementing the interface. We implement the interface by implementing the interface, by having the methods there that match the type signature for the interface's methods. Then we talked about how to compose interfaces together, and how this is a preferable approach versus creating a single monolithic interface. If you can, break that interface down into smaller types and then compose them together. And we did that something like this. So we're going to create multiple interfaces. So we have a writer interface and a closer interface. And then when we compose them together, just like when we compose structs by embedding, we can embed interfaces into one another. So we can create a writer-closer interface that embeds the writer interface and the closer interface. So to implement that writer-closer interface, you have to implement the write method because that's defined by the writer interface, and you have to implement the close method as it's defined by the closer interface. So by doing this, you can actually pass smaller chunks of your interface around your application. So for example, if a method only needs a writer, it doesn't need a closer, then you can actually pass this writer-closer as a writer, and it'll work just fine, versus passing the entire writer-closer along and potentially exposing methods to the consumer that aren't really necessary. Then we talked about type conversion and how we can drill through the interface to get at the underlying types in case we need to work with those directly. So we had an example here where we created a writer-closer instance, and the underlying type was a pointer to a buffered writer-closer, and how we could cast that back to a pointer to a buffered writer-closer by using this syntax here, where we have a dot after the object, and then inside of parens we put the type that we want to cast to. Now, we learned that when we did this, if the type assertion failed, then we're actually going to panic our application. So remember to use that OK syntax if you want to get a Boolean variable out that you can run tests against to see if that type conversion succeeded. And then we talked about the empty interface and type switches. The empty interface is nothing magic. It's just an interface defined on the fly that has no methods on it. Now, it's special in that every type in Go implements the empty interface. So you can store anything you want in a variable of type empty interface. And then very often we're going to pair that with what's called a type switch. And we see an example of that here, where we're going to use the switch keyword, we're going to have the object, and then dot and parens like we do with the type assertion, but instead of having a concrete type that we're asserting against, we put the keyword type in there. And then in our case statements, we're actually going to put in the data type that we're asserting against. So in this case, we're looking for integers or strings, or we have a default case in case the value stored in I is neither an integer nor a string. After that, we talked about implementing with values versus pointers, and we learned about a concept called method sets. Now, when you're working with types directly, you never have to think about this because the methods are always all of the methods assigned to that type. But with interfaces, the rules change a little bit. The method set of a value is all of the methods with value receivers. So if you're going to try and implement an interface with a value type, then all of the methods that implement that interface have to have value receivers. With pointers, things are a little bit more flexible. Because pointers always have access to the underlying type as well, the method sets for a pointer is all of the methods regardless of the receiver type. So all of the value receivers as well as all of the pointer receivers. So pointer types are definitely more flexible when you're implementing interfaces. Just keep in mind, you don't want to assign pointer receivers everywhere without thinking about the idea that that gives access to the underlying data of that type, and so that can allow methods to alter that underlying data even if you don't want them to. So be careful when you make that choice about using pointer receivers or value receivers. The last thing that we talked about were some best practices that have evolved over the last few years about using interfaces in the Go language. And we talked about use many smaller interfaces whenever possible, and then if you need larger interfaces, go ahead and compose those together with interface composition. Don't export interfaces for types that will be consumed. So if you're creating a library and somebody else is going to be consuming a type, go ahead and publish that concrete type out there. Don't create an interface assuming you know how people are going to use it. Allow them to create the interfaces that your type will implement. That way, they don't have to implement a whole bunch of methods in their test suite that they never even use. Do export interfaces for types that you will be consuming, however. So again, these 2 points are exactly opposite of how you're going to think about interfaces if you're coming from another language such as C# or Java that have explicit implementation of interfaces. So when you're defining a type that you're going to be consuming in your package, then go ahead and export interfaces. That way whoever's using your package can create their own concrete types and implement the interfaces that you need, so you don't need to worry about the implementation. You just need to worry about the behaviors that they're exposing to you. And then, if possible, define your functions and methods to receive interfaces. Don't get too crazy with this, so don't go over the top. Use common sense with this, but if you have the option of receiving interfaces, for example, if you don't need access to the underlying data, then go ahead and define an interface that you're going to be receiving. That way, it makes your methods and functions more flexible, since you can have multiple implementations that you never thought about at design time, and your functions and methods will continue to work even when those new concepts are thrown at your application. I want to have a conversation about the tools that we have available to implement concurrent and parallel programming in the Go language. Now, if you've come this far in the series, or if you've done any research in Go at all, concurrent programming is one of the hottest topics that is talked about, especially among people who are learning the Go language for the first time. So we're going to talk about this concept of a Go routine and how that enables us to create efficient and highly concurrent applications. We'll start our conversation by learning how to create Go routines themselves. So this is going to be the basics of how we create Go routines and how we can work with them a little bit. Then we'll move into a conversation about synchronization, and we'll talk about 2 concepts, wait groups and mutexes, and how we can use those to get multiple Go routines to work together. Because one of the challenges that we're going to have with Go routines is also one of the greatest advantages. Go routines are going to allow our application to work on multiple things at the same time. However, you're often going to run into situations where you need a certain bit of functionality in your application to wait until one or more of those concurrent calculations is complete. So we'll talk about how to use synchronization primitives in order to do that. Then we'll move into a discussion of parallelism. Now, up to this point, our conversation is going to be about concurrency in the Go language. And concurrency is just the ability of the application to work on multiple things at the same time. It doesn't mean it can work on them at the same time. It just means it has multiple things that it can be doing. When we talk about parallelism, we'll talk about how we can take our Go applications and enable them to work on those concurrent calculations in parallel, or in other words, introduce parallelism into our applications. And finally, we're going to wrap this video up again with a little section on best practices, just to talk about some of the gotchas that you can run into with concurrent and parallel programming, and some of the tools that are available to help keep your application safe and away from those minefields. Okay, so let's get started by talking about how to create Go routines. Okay, so the first thing that you're going to notice is that we're in Visual Studio Code right now. Now, the reason for that is, while we can certainly play with Go routines in the playground, when we start to get into parallelism, that's going to be limited by the playground because the playground only enables us to use one core at a time. So when we're running locally, we can use as many cores as we want, so we can truly run our applications in parallel. So some of the things that I want to show you are going to be easier to illustrate in this environment. So the first thing that I want to show you is how we can create our very first Go routine. So the first thing that we're going to need to do is we're going to need to have a function here. So I will create a function called say hello. And this is going to be a very simple function. All it's going to do is, well, say hello. So we'll start with that, and that's going to be just enough for us to get started, seeing what's going to happen with our application. So we can, of course, call the say hello function and call that from the main function, so we can run this application by just using go run and pointing it to that file. And of course it says hello, so no big surprises there. Now to turn this into a Go routine, all we have to do is in front of the function invocation, just type the keyword go. Now what that's going to do is that's going to tell Go to spin off what's called a green thread and run this say hello function in that green thread. Now I need to take a little bit of a moment here to talk about threads. Most programming languages that you've probably heard of and worked with use OS threads or use operating system threads. And what that means is that they've got an individual function call stack dedicated to the execution of whatever code is handed to that thread. Now, traditionally, these tend to be very, very large. They have, for example, about 1 megabyte of RAM. They take quite a bit of time for the application to set up. And so you want to be very conservative about how you use your threads. And that's where you get into concepts of thread pooling and things like that, because the creation and destruction of threads is very expensive. And so we want to avoid that in most programming languages, such as Java or C#. Now, in Go, it follows a little bit of a different model. And as a matter of fact, the first place I saw this model was used by the Erlang language. And this is using what's called green threads. So instead of creating these very massive, heavy overhead threads, we're going to create an abstraction of a thread that we're going to call a Go routine. Now, inside of the Go runtime, we've got a scheduler that's going to map these Go routines onto these operating system threads for periods of time. And the scheduler will then take turns with every CPU thread that's available and assign the different Go routines a certain amount of processing time on those threads. But we don't have to interact with those low-level threads directly. We're interacting with these high-level Go routines. Now the advantage of that is since we have this abstraction, Go routines can start with very, very small stack spaces because they can be reallocated very, very quickly, and so they're very cheap to create and to destroy. So it's not uncommon in a Go application to see thousands or tens of thousands of Go routines running at the same time, and the application has no problem with it at all. Now, if you compare that to other languages that rely on operating system threads that have 1 megabyte of overhead, there's no way you're going to run 10,000 threads in an environment like that. So by using Go routines, we get this nice, lightweight abstraction over a thread, and we no longer have to be afraid of creating and destroying them. So anyway, let's go ahead and run this and see what happens, and it's going to be a little disappointing because you notice that our message doesn't print out. And the reason for that is our main function is actually executing in a Go routine itself. So what we did here in line 6 was we told the main function to spawn another Go routine, but the application exits as soon as the main function is done. So as soon as it spawned that Go routine, it finished. It didn't have any more work to do. So the say hello function never actually had any time available to it to print out its message. So we can get around that a little bit by using a horrible practice, but it's good enough to get us started in understanding this. So we'll just put an arbitrary sleep call in here in order to get the main function to delay a little bit. Now when we run the application, we see that we do get our hello message printed out. Now as opposed to our first run of this, it's not actually the main function that's executing this code, it's a Go routine that we're spawning off from the main function, and that's what's responsible for printing out the message. Okay, now this is a pretty typical use case of a Go routine, where we're using the Go routine to invoke a function. But we don't have to do that. As a matter of fact, let me just drop in this example here, which is basically the same, except for instead of using a named function, I'm using this anonymous function here. So notice that I've got this anonymously declared function, and I'm invoking it immediately, and I'm launching it with a Go routine. Now what's interesting about it is I'm printing out the message variable that I've defined up here on line 9 down here inside of the Go routine. So if I run this, we do in fact see that it works. Now the reason that it works is Go has the concept of closures, which means that this anonymous function actually does have access to the variables in the outer scope. So it can take advantage of this MSG variable that we declared up here on line 9 and use it inside of the Go routine, even though the Go routine is running with a completely different execution stack. The Go runtime understands where to get that MSG variable, and it takes care of it for us. Now the problem with this is that we've actually created a dependency between the variable in the main function and the variable in the Goroutine. So to illustrate how that could be a problem, let me modify the example just a little bit. So I'm declaring the variable message and setting it equal to hello. I'm then printing it out in the Goroutine, and then right after I launch the Goroutine, right here on line 13, I'm reassigning the variable to goodbye. So if I go ahead and run this, you see that we in fact get goodbye printed out in the Goroutine, not hello, like you might expect based on how the program is written. And the reason for that, and it's not always going to be guaranteed to execute this way, but most of the time, the Go scheduler is not going to interrupt the main thread until it hits this sleep call on line 14. Which means, even though it launches another Goroutine on line 10, it doesn't actually give it any love yet. It's still executing the main function. And so it actually gets to line 13 and reassigns the value of the message variable before the Goroutine has a chance to print it out. And this is actually creating what's called a race condition, and we'll come back and talk about race conditions at the end of this video, but this is a bad thing, and generally it's something that you want to avoid. So while you can access variables via the closure, it's generally not a good idea to do that. So if that's not a good idea, what are your other options? Well, notice that we have a function here, and this is just a function invocation. There's nothing special about it just because we put the Go keyword in front of it, it's just a function. So functions can take arguments. So what happens if we add a message argument here, and then down in the parens where we're actually invoking the function, what if we pass in the message parameter? Well, since we're passing this in by value, so we're actually going to copy the string hello into the function, then we've actually decoupled the message variable in the main function from the Goroutine. Because now, this message that's going to print out is actually a copy that we're passing in when we're invoking the function for the Goroutine. So now if we run this, we see that we get hello printed out. So this is generally the way that you're going to want to pass data into your Goroutines. Use arguments to do that and really intend for the variables to be coupled together. Now this example so far is working, but it's really not best practice. And the reason it's not best practice is because we're using this sleep call, so we're actually binding the application's performance and the application's clock cycle to the real world clock. And that's very unreliable. So in order to get your applications to work, you're typically going to have to sleep for a very long time relative to the average performance time in order to get the performance to be reliable. So we don't want to use sleep calls in production, at least not for something like this. So what are the other alternatives? Well, one of the other alternatives that we have is to use what's called a wait group. So let's go ahead and add one in, and then while we're doing that, we'll talk about what they are. So I'm going to create another variable, and it looks like my auto formatting just helped me here, and we'll pull that from the sync package, and we'll create an object of type wait group. So I just need to put my curly braces here to initialize it. Now what a wait group does is it's designed to synchronize multiple Goroutines together. So in this application, we've got two Goroutines that we care about. We've got the Goroutine that's executing the main function, and we've got this Goroutine that we're spawning off here on line 13. So what we want to do is we want to synchronize the main function to this anonymous Goroutine. So we're going to do that by telling the wait group that we've got another Goroutine that we want it to synchronize to. It starts off synchronizing to 0, and so we're going to add 1 because we want to tell it that we're going to synchronize to this Goroutine right here. Now once it's done, we don't need this line anymore. Once it's done, we're going to go ahead and exit the application, and we will do that by just waiting on the wait group, and we do that by using the wait method right here. Now when the Goroutine is done, then it can tell the wait group that it's actually completed its execution. And we do that by using the done method. So if we execute that, basically what that's going to do is it's going to decrement the number of groups that the wait group is waiting on. And since we added 1 and it's going to decrement by 1, it'll be down to 0. And then the wait method will say, oh, okay, it's time for us to go ahead and finish up our application run. So if I save this off and I go ahead and run it, we see in fact that our application is performing as it did before, but now it's taking just enough time to complete the execution. We're not relying on the real world clock anymore and having to jimmy around with variables and hope that everything stays consistent. Now in this example, we're just synchronizing two Goroutines together, but only one of the Goroutines is really doing any work. The main function in this example is just storing data and spawning other Goroutines. But we can have multiple Goroutines that are working on the same data, and we might need to synchronize those together. And that can be a little bit tricky. So let me drop in this example here and we'll talk about it. So I'm creating a wait group again up here on line 8, and then I'm initializing a counter variable. Inside of my main function, I'm actually spawning 20 Goroutines, because inside of this for loop, each time I run through, I add 2 to the wait group to let it know there are 2 more Goroutines that are running, and then I spawn a say hello, and then I spawn an increment here. And then I just have a wait method call here on line 17, just to make sure that the main function doesn't exit out too early. Now in say hello, all I'm going to do is I'm going to print out hello, and then I'm going to print out the counter value. And then in the increment function down here, I'm just going to increment the counter by 1. Now after each one of those is done, I'm going to call the done method on the wait group, and everything should be just fine. Now notice that I've broken my own rule here. The wait group is actually being accessed globally in this application, and that makes sense because I actually do want to share this object, and the wait group is safe to be used concurrently like this. It's designed to be used in this way. So let's go ahead and run this application and see what's going to happen. So our intuition says that we're going to print say hello, so it should print say hello 0 because the counter's value is 0 right here, and then it's going to increment it, and then it's going to say hello again, it's going to increment it, so it should say hello number 0, hello number 1, hello number 2, and so on. So let's go ahead and run this and see what happens. And we see that we get a mess. We in fact don't have any kind of reliable behavior going on here. We printed 1 twice and then 2, 3, 4, 5, so that seemed to work consistently. And then we jumped all the way to 9. We printed 10 out twice, and then we went back to 9 for some reason. And if we run this again, we'll get a completely different result. So what's happening here is our Goroutines are actually racing against each other. So we have no synchronization between the Goroutines. They're just going hell-bent for leather and going as fast as they can to accomplish the work that we've asked them to do, regardless of what else is going on in the application. So in order to correct this, we need to find a way to synchronize these guys together. Now we could probably find a way to use a wait group on this, but we've already talked about wait groups, so I want to talk about another way to do this. So we're going to introduce this concept of a mutex. So with a mutex, let me paste this example in here, and then we'll talk about what it does. But a mutex is basically a lock that the application is going to honor. Now in this case, you see on line 11, I'm creating what's called an RW mutex, which is a read-write mutex. Now a simple mutex is simply locked or unlocked. So if the mutex is locked and something tries to manipulate that value, it has to wait until the mutex is unlocked and it can obtain the mutex lock itself. So what we can do with that is we can actually protect parts of our code so that only one entity can be manipulating that code at a time. And typically what we're going to use that for is to protect data to ensure that only one thing can access the data at a single time. With an RW mutex, we've changed things a little bit. We've basically said as many things as want to can read this data, but only one can write it at a time. And if anything is reading, then we can't write to it at all. So we can have an infinite number of readers, but only one writer, and so when something comes in and makes a write request, it's going to wait till all the readers are done, and then the writer is going to lock the mutex, so nothing can read it or write it until the writer is done. So in this modification, actually I don't want to talk about that line yet, we'll come back and revisit that. So in this modification, what I've done here is I'm attempting to use a mutex to synchronize things together. So the modification is down here. In my say hello, I'm just reading the value of the counter variable, and that's what I'm trying to protect. I'm trying to protect the counter variable from concurrent reading and writing because that's what was getting us into trouble. So on line 22, I obtain a read lock on the mutex, and then I print out my message, and then I release that lock using the runlock method. Now in the increment, that's where I'm actually mutating the data, so I need a write lock, and so I'm going to call the lock method on the mutex, increment the value, and then I'm going to call unlock. Now if I run this application, I actually haven't gotten quite where I want to be. So I don't get the weird random behavior that I was seeing before, but you notice that something seems to be out of sync still, because I get hello 1, hello 2, and then it stays at 2. And if I keep running this, I actually can get different behaviors, but notice that I'm always going in the proper order. So I fixed part of my problem, but I haven't fixed all of it yet. So I can keep running. Actually, that one got pretty close, but there's obviously something else going on here. Well, the reason that we have an issue here is we're still working within the Goroutines. So if this say hello function gets executed twice by its Goroutines, and the increment function doesn't get called in between, that's where we get this behavior here, where we actually get the same message printing out twice, because we don't have a chance to lock this mutex before we try and read it that second time. So the way to address this is we actually have to lock the mutex outside of the context of the Goroutine so we have a reliable execution model. So let's go ahead and paste in a small modification here. Now all I've done is I've moved the locks out here. So the locks are now executing before each Goroutine executes, and then I unlock them when the Goroutine is done. So if I run this, we actually see that I now get the behavior that I expect. I see 0 through 9 printed out, and if I run it again, and I run it again, and I run it again, everything is working great. So the reason that this is working is I'm actually locking the mutexes in a single context. So the main function is actually executing the locks, and then asynchronously I'll unlock them once I'm done with the asynchronous operation. Now the problem with this application is I basically have completely destroyed concurrency and parallelism in this application because all of these mutexes are forcing the data to be synchronized and run in a single threaded way. So any potential benefits that I would get from the Goroutines are actually gone. As a matter of fact, this application probably performs worse than one without Goroutines because I'm mucking around with this mutex and I'm constantly locking it and unlocking it. So this is an example where if this is all that this application needed to do, we would actually be much better served by removing the Goroutines and just running this with a single execution path and removing any concurrency at all. However, there are often situations where you can get a significant advantage by running things in parallel, and so you can use wait groups or mutexes in order to synchronize things together and make sure that your data is protected and everything is playing well together. Now I have this line in here, and I apologize for that. I really shouldn't have had that in these earlier examples, but I do want to talk about this function from the runtime package called gomaxprox. So in modern versions of Go, if you look at this gomaxprox variable, let's just go ahead and execute this simple program. All it's going to do is it's going to tell me the number of threads that are available. So it prints out that there are 4 threads available in the application. And as a matter of fact, let me just add this carriage return in here and run this again. That way things look a little better. And you see that I have 4 threads available. So by default, what Go is going to do is it's going to give you the number of operating system threads equal to the number of cores that are available on the machine. So in this virtual machine, I've exposed 4 cores to the VM, so I have by default 4 OS threads that I can work with. Now, I can change that value to anything I want. So for example, I can change that to 1, and now my application is running single-threaded. So now I have a truly concurrent application with no parallelism at all. So this can be useful in situations where there's a lot of data synchronization going on, and you really need to be careful to avoid any kind of race conditions that parallelism can incur, and maybe there's no better way to do it. Now, I would say there's an architecture problem there, but it is possible to run an application in a single-threaded way by setting gomaxprox equal to 1. Now, if you're wondering what this -1 does, when you invoke the gomaxprox function, it actually returns the number of threads that were previously set, and if you pass a negative number, then it doesn't change the values. So this gomaxprox -1, all that's doing is that's letting us interrogate how many threads we have available. Now, we can also set this to, for example, 100. There's nothing stopping us from creating a massive number of operating system threads. Now, what I've found in working with Go is that gomaxprox is a tuning variable for you to work with. So the general advice is 1 operating system thread per core is a minimum. But a lot of times you'll actually find that your application will get faster by increasing gomaxprox beyond that value. Now, if you get up too high, like for example 100, then you can run into other problems because now you've got additional memory overhead because you're maintaining 100 operating system threads. Your scheduler has to work harder because it's got all these different threads to manage. And so eventually the performance peaks and it starts to fall back off because your application is constantly rescheduling Goroutines on different threads. And so you're losing time every time that occurs. So as you get your application closer to production, I would encourage you, definitely develop with gomaxprox greater than 1 because you want to reveal those race conditions as early as possible. But just before you release to production, you might want to run your application through a performance test suite with varying values of gomaxprox to see where it's going to perform the best. Now, the last thing that I want to talk about are some best practices to keep in mind when you're working with Goroutines in the Go language. So let's take a look at those next. Goroutines in the Go language are very powerful, and it can be easy to let them get a little bit out of hand. So I want to go through and give you some advice on how to work with Goroutines in your own applications. The first bit of advice is if you're working in a library, be very, very careful about creating Goroutines yourself. because generally it's better to let the consumer control the concurrency of the library, not the library itself. If you force your library to work concurrently, then that can actually cause your consumers to have more problems synchronizing data together. So in general, keep things simple, keep things single-threaded, and let the consumer of your library decide when to use a Goroutine and when not to. Now, this advice can be softened a little bit if you have a function call that's going to return a channel that'll return the result. Then having the Goroutine in there might not be such a bad thing, because your consumer never really has to worry about how that unit of work is getting done. They don't really care if it's running concurrently or not, because they are just going to be listening for the result on a channel. But we haven't talked about channels yet, so we'll revisit that topic in the next video. But for now, if you're creating a library, try and avoid Goroutines, at least Goroutines that are going to be surfaced to the consumer, and have them forced to work with them. When you create a Goroutine, know how it's going to end. Now, we're going to see how to do this a little bit more when we talk about channels, but it's really easy to have a Goroutine launched as kind of a watcher Goroutine. So it's going to be just sitting out there listening for messages to come in, and it's going to process those messages as they arrive. However, if you don't have a way to stop that Goroutine is going to continue on forever. And so it's constantly going to be a drain on the resources of your application. And eventually, as the Goroutine ages, it could even cause other issues and cause your application to crash. The other thing that I want to give you some advice about is check for race conditions at compile time. So I want to jump back over to the editor and show you how to do that, but it's very important and very simple to do in most environments that Go runs in. So let's jump over to the editor and take a look at that. And in order to see it, we don't have to go any further than this example. Now I know this is right from the beginning of the video, and it's got sleeps in there, and it's got some bad practices. But if you remember, if we run this application, then it prints goodbye instead of the hello message that we originally printed. So how could we have detected this without running the application? Well, you might not think it's terribly important to be able to do that, because it's obvious we've got some kind of a problem here, and all we have to do is apply our debugging skills. But there are other cases where this is very, very subtle and very, very hard to track down without a little bit of help. Well, fortunately, the Go compiler has quite a bit of help available to you, and it's as simple to invoke as just adding a -race flag to go run, go install, go build, whatever you're using to get your application up and running. So let's go ahead and try that and see what it says about our little application here. And you notice it does run the application because we invoked go run, so we see goodbye printed here. But notice what we got up here. We got this data race message. So it's telling us it sees that the same area of data is being accessed by two different executing Goroutines. So it says the first one that it found was in Goroutine 6, which is an internal identifier. Unless we're profiling, we've got no idea what Goroutine 6 is. But it does tell us it was invoked on line 11. So apparently in this run, Goroutine 6 was this Goroutine right here, and it was accessing the MSG variable. It also sees that we accessed the MSG variable on line 13, which is in our main function. And so by adding the -race flag, we get all of this additional information where the Go compiler itself analyzes our application and tries to determine if we have any race conditions. So I would strongly encourage you, if you've got any kind of concurrency at all in your application, you're going to want to run this, because it's a very simple check, it runs very, very quickly, and it's going to help you prevent very subtle bugs from getting into your production code. Okay, so that's what I have to talk about with Goroutines. Maybe you were expecting more, but Goroutines are really quite simple. Now, when we get into our next conversation, which will be about channels, things get a little bit more complicated, but Goroutines are relatively straightforward. So let's go into a summary and review what we've talked about in this video. In this video, we learned about Goroutines and how we can use them to create concurrent and parallel execution paths in our applications. We started by learning how to create Goroutines themselves. And we learned that by adding the Go keyword in front of a function call, we've created a Goroutine, and that's all that it takes. There's no special semantics, there's no special things that need to be done. It's simply a function call with the keyword Go in front of it. Now, when we're using anonymous functions, we in general want to pass data as local variables. So you want to add a parameter into that anonymous function and pass data into the Goroutine instead of relying on the closures to prevent any kind of race conditions as you try and manipulate that data. Now, that's not always true. We saw with weight groups that we accessed that globally because that was our intention. We truly did want that to be available in multiple scopes. But even then, we could pass a pointer in order to be very clear about what information that Goroutine should have access to. Then we talked about the different ways that we can synchronize multiple Goroutines together. One of the challenges that we have with Goroutines is now we've got all sorts of things happening, and there's no way to ensure without synchronization how they're going to interact with one another. Now, for a lot of concurrent calculations, that's not a problem at all, because the two might not be related to one another. But often you get into situations where you're relying on the result of multiple calculations, or something needs to know the result of the work that's been done, or you've got a shared memory issue, and you need to make sure that those Goroutines aren't trying to manipulate the same data at the same time. So we can use wait groups to wait for groups of Goroutines to complete. So we saw that we have three methods that are interesting there. We have the add method to inform the wait group that there are more Goroutines for it to wait on. We have the wait method that's going to block the Goroutine that it's called on until the wait group is completed. And then we have the done method available on that wait group that lets the wait group know that one of the Goroutines is completed with its work. We also talked about the mutex and the RW mutex and how those are generally used to protect data. So if you have a piece of data that's going to be accessed in multiple locations in your application, then you can protect that access by using a mutex or an RW mutex to ensure that only one Goroutine is manipulating that data at one time. We then talked about parallelism and how parallelism can introduce some really tricky challenges into your Go applications. We talked about how by default Go will use the number of CPU threads equal to the number of available cores on the computer that it's running on. We talked about how we can change that by using the Go max procs function from the runtime package. And we talked about how more threads will generally increase performance, but too many can actually slow it down. So in general, if you're developing an application, you want to start from day one with Go max procs greater than 1 to find any concurrency and any race conditions early on in your application development. But don't settle on a final number until right as you get close to production and you have a performance test suite that you can work with to find out what the best value for Go max procs is for your application. Because while the starting number is a very good number to start with, a lot of applications actually perform better with a value higher or lower than that default value. And finally, we wrapped up with a discussion of some best practices to keep in mind when you're working with Goroutines. We learned that if you're a library developer, you should avoid the creation of Goroutines that are going to be exposed to the consumer of your library. Let the consumer control the concurrency of your application because they're the ones that are in the best place to know if something needs to be executed single-threaded or if it can be executed concurrently. When creating a Goroutine, know how it's going to end. It's very easy to get into situations where Goroutines start leaking memory because they're never cleaned up, because they never quite get done with their work. Now, normally a Goroutine is killed as soon as it finishes its execution. And we saw that with the main function. The main function runs in a Goroutine, and that Goroutine terminates as soon as the main function exits. We also saw in our say hello function, as soon as it printed its message out and the function exited, that Goroutine was killed and it was cleaned up. So it was very clear when those Goroutines' life cycle was going to be over. However, if you've got Goroutines that are listening for messages in a continuous loop, then make sure that you code in a way to shut those Goroutines down so that once you're done using them and clean up the memory that they're using. Also, as you're going along with your application development, check for race conditions. It's not that hard to do. You just have to add -race onto the Go command that's compiling your application, and then the Go compiler is going to analyze your application and try and locate places in it that have the potential of accessing the same memory at the same time or in an unsynchronized way, causing very subtle and potentially very disastrous bugs for your application when it gets to production. Over the course of this video series, we've talked about a lot of structures and techniques and tools that are available in order to get started successfully programming with the Go language. Well, I want to wrap up that discussion in this video by talking about one of the features that makes Go really stand out when you're looking for different languages to work with, and that is this concept of channels. Now, most programming languages that are out there were originally designed with a single processing core in mind. And so when concurrency and parallelism came into play, they were really kind of bolted onto the side. And so a lot of times you're actually going to be working with third-party libraries and packages in order to help with data synchronization and things like that. Well, Go was born in a multiprocessor world. So every computer that was out there when Go was invented had more than one processing core. So it made sense as the language was being designed to consider concurrency and parallelism from the beginning. Now, in the last video, we talked about Goroutines and how Go abstracts the concept of a thread into this higher concept called a Goroutine to allow hundreds or thousands or even tens of thousands of things to be going on in your application at the same time. Well, in this video, we're going to be talking about channels and how those can be used to pass data between different Goroutines in a way that is safe and prevents issues such as race conditions and memory sharing problems that can cause issues in your application that are very difficult to debug. So we're going to start this talk by talking about the basics of channels. So we'll talk about how to create them, how we can use them, how we can pass data through them. Then we'll talk about how we can restrict data flow. Now, a basic channel is a two-way street. We can send data in and we can get data out. But that's not always what you want to be able to do with a channel. Sometimes you want a send-only channel or a receive-only channel, and we'll talk about how to do that in this second section. Then we'll talk about buffered channels and how we can actually design channels to have an internal data store so that they can store several messages at once, just in case the sender and the receiver aren't processing data at the same rate. Then we'll talk about how we can close channels once we're done with them. We'll then revisit the topic of for-range loops, and we'll learn how we can use channels with a for-range loop. And then we'll wrap up our discussion by talking about select statements, which is kind of like a switch statement, but specifically designed to work in the context of a channel. Okay, so let's go ahead and dive in and learn the basics of working with channels. So when we're working with channels in the Go language, we're almost always going to be working with them in the context of Goroutines. And the reason is because channels are really designed to synchronize data transmission between multiple Goroutines. So let's go ahead and get started by creating some Goroutines. Well, actually, the first thing that I need to do is I need to create a wait group, because as you'll remember from the last video, we use wait groups in order to synchronize Goroutines together. So we're going to use the wait group to synchronize the Goroutines to make sure that our main routine waits for all of our other Goroutines to finish. And then we're going to use channels in order to synchronize the data flow between them. So we got two different synchronization mechanisms going on in this little application. The next thing we need to do is we need to create a channel. Now, channels are created with the built-in make function, and there really is no shortcut around this. Now, a lot of uses of the make function, you can actually use other forms. When you're creating a channel, there's enough internal mechanisms that need to fire that you have to use the make function in order to allow the runtime to properly set up the channel for you. Now, in the simplest form of the make function when working with channels, we're going to use the chan keyword to say that we want to create a channel, and then we're going to provide the data type that's going to flow through the channel. Now, you can pick any data type that you want. We're just going to be using integers here, but keep in mind that this means that the channel is strongly typed. You can only send integers through this channel that we're creating here. Similarly, if we provided strings, we can only pass in strings. If you provided pointers to integers, you can only send in pointers to integer. You get the general idea. So when you create a channel, you're going to create that channel to accept messages of a certain type, and it's only ever going to receive and send messages of that type. Now, in this initial example, we're going to have two Goroutines I'm going to spawn. So I'm going to add 2 items to my wait group, and then we'll go ahead and create those Goroutines, and then we'll talk about those. So let me just drop in the rest of the code here. And you can see my first Goroutine is an anonymous function. Actually, both of them are. And this first one is going to be receiving data from the channel. So this Goroutine is actually going to be my receiving Goroutine. And then this channel is actually going to be my sending Goroutine. So the way that we send a message into a channel is as you see here. We're going to use this arrow syntax, so we're going to use a less than and a dash. And when we're putting data into the channel, we list the channel first, then we have this arrow, and then the data that we want to pass in. So imagine that the arrow is pointing in the direction that we want the data to flow. So we want the data to flow into the channel, and so the arrow is pointing toward the channel. Similarly, if we want to receive data from the channel, then we're going to put the arrow on the other side. So we're going to use that same less than and dash, but it's going to be before the channel, and so we're going to be pulling data from the channel. So in this line right here on line 14, we're going to be receiving data from the channel and assigning it to the variable I. And then after we're done, we're going to call the done method on our wait groups, and we're just going to print the value out. So all we're doing here is this Goroutine is going to be sending the value 42. This Goroutine is going to be receiving whatever value comes out of the channel, which in this case, of course, will be 42, and it's going to print that out to the console. So let's go ahead and run that, and we see that, in fact, it does work. So the nice thing about doing this is since we're sending a copy of the data through the channel, we could manipulate the variable assigned here. So for example, we could actually start this off with I set equal to 42, and we can pass in I, and then afterwards we could reassign I, and it doesn't matter, because like with all other variable operations in Go, when we're passing data into the channel, we're actually going to pass a copy of the data. So when we manipulate it afterwards, the receiving Goroutine doesn't really care that we change the value of the variable. It's not affected by that at all. Now, another common use case for Goroutines is if you have data that's asynchronously processed. So maybe you can generate the data very, very quickly, but it takes time to process it. Or maybe it takes a long time to generate that data, so you've got multiple generators, but it can be processed very quickly. So you might want to have a different number of Goroutines that are sending data into a channel than you have receiving. So let's take a look at how we can do that. So it's a slight modification to the example that we just went through. Instead of just having the Goroutines fire once, I'm actually creating Goroutines inside of this loop here. So I'm going to create 5 sets of Goroutines. So each one of the groups is going to have a sender like we have here, which is exactly what we had before, and then we're going to have a receiver, which is, again, just like we had before. So by the time the application's done, we're going to spawn 10 Goroutines here, 5 senders and 5 receivers, and all of them are going to be using this single channel to communicate their messages across. So if we go ahead and run this, we see that we do get 5 messages received. Okay, so this works out really well, but I will warn you, if you start playing around with this and you decide to start moving the senders and receivers to make them asymmetrical, things won't work very well. So one of the things you might want to do to play with this example is take this Goroutine and move it outside of the for loop. So you're going to have one receiver and multiple senders at the end of this. Well, that actually isn't going to work right now, because if you think about how this Goroutine is going to process, it's going to receive the message coming in from the channel, it's going to print, and then it's going to exit. But then down here in the loop, we're actually going to spawn 5 messages into that channel. So we can only receive 1, but we're sending 5. And if we run this, we're actually going to run into a problem, and that is we see all routines are asleep, that we have a deadlock condition. And the reason for that is because we have these Goroutines down here that are trying to push messages into the channel, but there's nothing that can process them. Now, an important thing to keep in mind here is the reason that this is a deadlock. And the reason for that is this line of code here is actually going to pause the execution of this Goroutine right at this line until there's a space available in the channel. So by default, we're working with unbuffered channels, which means only one message can be in the channel at one time. So our first Goroutine in this loop gets happily spun up, it pushes a message into the channel, and then it exits, and it calls this done method on the wait group. And then that message gets processed by this Goroutine here, and everything's happy. However, this Goroutine then exits, and then our next Goroutine comes along and tries to push another message in. Well, it blocks right on this statement, and there's nothing in our application that's going to receive that message. And that's why we see the Go runtime notice that, and it's going to kill the application because it notices that we have a problem, and it doesn't know how to resolve it. Now, I want to go back to our previous example, and actually I'm going to modify things slightly here, because I want to show you that, notice that we're just working with the raw channel. So this is perfectly valid code for us to write. As a matter of fact, if I go ahead and run this, we see that we get 2 messages printed out, but look at how that's happening. So this Goroutine is pushing a message into the channel. That message is then being received up in this Goroutine and printed out. This Goroutine then, the one that received this message, is then putting a message back into the channel. And that is then being received down here in this Goroutine, which is then printing the message out. So both of these Goroutines are acting as readers and writers. Now, that may be a situation that you want, but very often you want to actually dedicate a Goroutine to either reading from a channel or writing to a channel. So in order to do that, what we're going to do is we're actually going to pass in the channel with a bias on the direction that it's going to be able to work with. So the way we're going to do that is by accepting variables in our Goroutines. So we'll start with this first one here, and we want this to be a receive-only channel. So the way we're going to do that is we want data to flow out of the channel. So you notice we're using that similar syntax. We're going to list the type of the channel, and then we're going to have this arrow coming out of it. So data is flowing out of the channel, and so this is going to be a receive-only channel. Similarly, if we want a send-only channel, we're going to give it the variable name. We're going to say that it's a channel. Now we put the send-only operator right here, and then we put the data type. So this is going to be sending data into the channel only, and this is going to be receiving data from the channel. And then of course we have to pass the channel into the Goroutines as arguments. So when we run this, we're actually going to get an error. And the reason we get an error is because we're trying to pass data into this channel, but this is a receive-only channel, so it's invalid to send data into it. And then similarly, we have an error down here on line 21 because we're trying to receive data from a send-only channel. So if we go ahead and wipe out these lines here, this line, and run, then everything works as it did before. But now it's much more clear what the data flow is in the Goroutine. We know that we're going to be receiving data on one side and we're going to be sending data on the other. Now, something that's a little unusual with this is notice that we're passing in a bidirectional channel, so this is just a normal channel, and we're receiving it a little bit differently. So this kind of feels like a little bit of polymorphic behavior, and this is a special aspect of channels. The runtime understands this syntax, and so it actually is going to, I'm going to use the word cast here, it's going to cast this bidirectional channel into a unidirectional channel, but that's not something you can generally do in the Go language. That is something that is specific to channels. Now, one of the problems we ran into on a previous example is we had a situation where we tried to push 5 messages into a channel, but we only had one receiver, and we noticed that the application deadlocked. Well, we can get around that in a couple of different ways. Now, I'm going to show you one way to get around that really isn't ideal for solving that problem, but I will talk about the problem that it is solving, and that is by using buffered channels. So if I go ahead and paste in this example here, we will see an example of the problem we might run into. I've simplified it a little bit from the previous example we ran into. So we've got our initial example where we've got a receive-only Goroutine, we've got a send-only Goroutine, but in our send Goroutine, we're actually sending 2 messages, but since we're only receiving one, we expect that we're going to run into a problem. So let's go ahead and run this. And we see that we do in fact have a problem. We received the 42 out and printed it, but there's nothing to deal with this message here that's in the channel, and so the application blows up because this Goroutine can never complete because it's blocked on this line. So we need a way to get around that. Now, a simple way to get around that is by simply adding a buffer here. So if we add a second parameter to the make function up here and provide an integer, that's actually going to tell Go to create a channel that's got an internal data store that can store, in this case, 50 integers. Now what that's going to do is it's actually going to allow our application to complete, but we do have a little bit of a problem here because this message is lost. So it did eliminate the panic, and I guess in one way you could say it solved the problem, but it did create another problem in that we lost this message. Now, this isn't the problem that buffered channels are really intended to solve, but I do want to show you that it does create that internal store so we can receive multiple messages back out. As a matter of fact, what we can do is we can just copy this line down here and reformat this, and we don't need this colon right here. And if we run this, we see that we do get both messages printed back out. Now, what a buffered channel is really designed to do is if the sender or the receiver operate at a different frequency than the other side. So you can imagine if we had a data acquisition system, and maybe we retrieve data from our sensors in a burst transmission. So maybe we're acquiring data from seismometers and we're monitoring earthquakes. Well, maybe those seismometers, in order to conserve power, don't send their data continuously. They're going to send a burst transmission maybe once an hour. So every hour, we're going to get a burst transmission that maybe lasts 5 or 6 seconds that's going to contain the entire hour's worth of data. So in that case, our sender is going to be inundated with data when that burst happens, and it's going to have a way to deal with it. Well, the receivers might take a little while to process that data. So in that case, what we might want to do is create a buffer here of these signals that are coming in from our seismometer that's going to be able to accept that 1 hour's worth of data, and then our receivers can pull that data off as they're able to process it and keep things working smoothly so that the channel that's receiving the data from our sensors doesn't get locked up because it doesn't have a place to put the next message. So that's really what buffered Goroutines are designed to work with, is when your sender or your receiver needs a little bit more time to process, and so you don't want to block the other side because you have a little bit of a delay there. Now, if this isn't the right way to handle this situation, what is the right way? Well, the way that we typically handle something that's going to happen multiple times, such as passing a message into a channel, is by using some kind of a looping construct. And that's no different with channels as it is with anything else. So let's paste in this example where instead of processing the message once and then having this first goroutine exit, I'm actually going to use a for range loop. But notice what I'm ranging over. Instead of ranging over some kind of a collection, such as an array, a slice, or a map, I'm actually ranging over the channel. Now the syntax changes just a little bit, because if this were a slice, the first index that we pull back is going to be the index in the slice. And then the second variable we pulled out, if we had, for example, a second variable here, would be the value. Well, when you're ranging over a channel, things are a little bit different. When you pull a single value, you're actually going to get the value that's coming out of the channel. And so if we run this, we see that we do in fact get 42 and 27, but we still have a deadlock condition. So what's causing that deadlock condition? Well, before we had this for range loop, we actually deadlocked this goroutine right here, and everything died. Well, in our new application, we're actually deadlocking in the for range loop. And the reason for that is because we're continuing to monitor for additional messages, but we stopped sending messages. And so now this for range loop doesn't know how to exit, and so this goroutine is now causing the deadlock condition. So we've improved the situation. We kind of moved the needle where we're no longer deadlocking in our sender, but we are still deadlocking in our receiver. So how do we handle that? Well, the way that we're going to handle that is we have to understand how the for range loop works. So if you're using a for range loop over a slice, how many times does that iterate? Well, it executes the loop once for every item in the slice. So if you've got a slice with 5 elements in it, you're going to run through the for range loop 5 times. Well, how many elements are in a channel? Well, there can be an infinite number of elements in a channel because you can constantly push a new message into it. So what is the way to signal a for range loop with a channel that there are no more messages coming? Well, the answer is we need to close the channel. So anything that has access to the channel can do this. We're going to use the built-in close function, and we're going to pass in the channel like you see here. So what we're doing on our sending side is we're passing in 2 messages. We're passing in 42 and 27, and then we're letting the channel know we're done working with you. So we're going to go ahead and close the channel. This for range loop is going to detect that, and when we run this, now everything runs well. Because we're passing in the message 42, that gets processed in the for loop. We're passing in 27, that gets processed. Then we close the channel, that gets processed by the for range loop, which notices that the channel is closed, and it's going to exit, and it's going to terminate the loop. So when we terminate the loop, then we call the done method on the wait group, and then we exit the goroutine. All of our goroutines exit properly, and we have no more deadlocks. Now, we do have to be a little bit careful in closing channels, because when you close a channel, you really have to mean that you're closing the channel down. So let's try closing the channel right here and then pushing another message into it. So if we run this, we actually get a bad thing happening. So in this case, the application panicked. And why did it panic? Because we tried to send a message on a closed channel. So the issue here is we close the channel right here on line 21, and then on line 22, we tried to pass another message into it. So that is a no-no. You are not allowed to pass a message into a closed channel because the channel is closed. So you might ask, well, how do I recover from this? How do I reopen the channel or undo that or whatever? And the answer is you can't. As a matter of fact, you can't even detect if a channel is closed except for by looking for the application panicking. So call that a limitation of the Go language or not, I don't know. But you do have to be very careful that when you close a channel, nothing else is going to send a message into it. So if that is a possibility, then the only option you really have is to have a deferred function and use a recover in there to recover from the panic that gets thrown. Because in this situation, you will have a panic and there is no way to avoid it. So if in your application that's a situation that's likely to happen, then again, you're going to have to use that recover function, and you can review the video where I talked about using those. Now, on the receiving side, we do have a little bit of a different story here, because this issue is on the closing side. So we cannot send a message into a closed channel, and we can't detect if a channel is closed before we try and send a message into it. However, if we go on the receiving side, then the story gets a little bit brighter. So you might ask the question, how does the for range loop know that the channel is closed? It has to have some way of detecting it. Well, it turns out that there's more than one parameter that you can pull back from the channel. So just like when we're querying maps and we're trying to get a value out of a map, and we can use that comma OK syntax, well, that syntax works for channels as well. So if I change this example up a little bit, and this is going to do exactly the same thing as our current example here using a for range loop, but instead of using the for range loop and having Go automatically process the closed channel for us, we're going to process this manually. So let me paste in this example and show you. So notice that I'm in a for loop in this Go routine, and I don't have any conditions on it. So this is going to execute forever. Down here then, I'm receiving a message from the channel, and I'm using the comma OK syntax. So I'm going to get the value from the channel in I, and I'm going to get a Boolean letting me know if the channel's open or not in the OK variable. So if the channel's open, then OK is going to be true. If the channel's closed, then OK is going to be false. So in the happy path, if OK is true, then I'm going to go ahead and print out my message. Otherwise, I'm going to break out of this for loop here because the channel's closed and I'm not going to be receiving any more messages from it. So this is functionally exactly the same as the for range construct, but we're explicitly seeing this comma OK syntax. So which one would you use? Well, in this situation, it would make more sense to use the for range construct, but there may be situations where you're receiving data from a channel and you are not in a loop. So maybe you're spinning off a new Go routine for every time you're processing a message, and so the loop is going to contain the spinning off of the Go routines, and so you're going to need this comma OK syntax because it might not make sense to use the for range loop. Now the last thing that I want to talk about in this video are what are called select statements. So let me go ahead and paste in this code here. So we talked about in the last video how there can be situations where you create Go routines that don't have an obvious way to close. And that's what I want to try and illustrate here. So if I go ahead and run this, we see that we do get these messages printed out. So I'm just doing a simple logger implementation. So what you see here is I've got some constants that are declaring my log level. I've got a struct that I've declared that's holding the timestamp for the log entry, the severity of the log level, and then whatever message I'm trying to print out. Then I'm creating a log channel. And the way this application works is the first thing the main function does is it spins up this Go routine that's going to be my logger. And what it's going to do is it's simply going to monitor that log channel for log entries that are coming from throughout my application. So the idea is I've got a central logger, and anything that could do logging in my application just needs to know about this channel, and all of my logging logic can be hidden within the processing of those log channel messages. So the logger is down here. We've got a for range loop that's listening for messages from the log channel, and all it's doing is it's printing out a formatted message that's got the timestamp, it's got the log level, and it's got the message from the log. So no big deal here, nothing terribly exciting. Then my main function goes on to exercise that a little bit. It sends two messages into the log channel, one letting it know that the application is starting, another one letting the application know it's shutting down. And then I've got a sleep call here just to make sure that the logger Go routine has enough time to process that. Now you notice my timestamps are a little funny here. That's because I'm working with the playground. I promise you this code does work. If you shift it over to Visual Studio Code, you will actually get real timestamps. But for some reason, the playground doesn't give you the current time when you call the now function. And so this is just something that we're going to have to work with in this example. Now the problem I want you to consider is, when does the logger Go routine close down? So obviously, the logger Go routine has to terminate sometime because the program finishes execution and we get the results back from the playground. So what's happening here is, remember, an application is shut down as soon as the last statement of the main function finishes execution. So when we finish this sleep call here, the application terminates and everything is torn down and all resources are reclaimed as the Go runtime returns all of the resources that it was using back to the operating system. So what that means is that our logger Go routine is being torn down forcibly. There's no graceful shutdown for this Go routine. It's just being ripped out because the main function is done. Now, in some situations, like this one, that may be acceptable. But there are many situations where you want to have much more control over a Go routine because, remember what I said in the Go routine video, you should always have a strategy for how your Go routine is going to shut down when you create your Go routine. Otherwise, it can be a subtle resource leak, and eventually it could leak enough resources that it could bring your application down. So there's a couple of different things we could do here, right? We could, of course, do a defer call here. We can pass in an anonymous function, and inside of that, we could go ahead and close the log channel. So what that's going to do is when the main function exits, it's going to go ahead and close the channel, and then we are gracefully shutting down that channel. And that works just fine. There's no issues with that. We are intentionally closing down the channel. We know how our Go routine is going to close, and so this is perfectly acceptable in this use case. But this isn't what I want to show you. So this is certainly something you could use in this use case, but I want to show you another way that's very commonly used in these kinds of situations. So the way that I want to show you is using what's called a select statement. So let me go ahead and paste in that code and we'll walk through that. So the application is basically the same. I've got the same constants over here. I've got the same struct. I do have this additional channel here, and notice the type signature for it. So it's strongly typed, but it's strongly typed to a struct with no fields. Now, struct with no fields in the Go language is unique in that it requires 0 memory allocations. So a lot of times you will see a channel set up like this, and the intention is it can't send any data through except for the fact that a message was sent or received. So this is what's called a signal-only channel. There's 0 memory allocations required in sending the message, but we do have the ability to just let the receiving side know that a message was sent. So this is pretty common. You might be tempted if you're new to the language, like I first did, you send a Boolean in here, but that does actually require a variable to be allocated and copied, so it is actually better to use an empty struct because it saves a couple of memory allocations. It's a little bit minor, but it is something that if you are going to use a channel as a pure message, then you might as well go with the conventions and use this approach. So our main function is exactly the same as it was before. We've got our logger, we've got our log channel sending in a couple of messages, and then we got a sleep call here. And then inside of our logger function, we've got an infinite loop now, and we're using this select block. So what this select statement does is the entire statement is going to block until a message is received on one of the channels that it's listening for. So in this case, we've got a case listening for messages from the log channel and a case listening for messages from the done channel. So if we get a message from the log channel, then we're going to print out our log entry. If we get a message from the done channel, then we're going to go ahead and break out of this for loop. So what this allows us to do is at the end of our application, we can go ahead and pass in a message into our done channel, and that is going to be an empty struct. And I'm just going to define that empty struct on the fly here. So this is a little bit confusing syntax, but this is the type signature for my struct. So I'm defining a struct with no fields, and then I'm initializing that struct using these curly braces here. So if I go ahead and run this, you see that the application runs properly. So I do process my log messages, and then I pass in this message into my done channel when I wish the logger to shut down. So this is a common situation for you to use when you're monitoring channels and you need a way to have the Go routine that's monitoring those channels be able to terminate. So very often you're going to send in, normally as a parameter, you're going to send in this done channel, and then whatever is ready to kill the Go routine will go ahead and send a message into that done channel, and it'll go ahead and kill it. Now, one more thing that I do want to talk about, and I'm not going to actually run it because it's going to break our application here, but you can have a default case here, and if you do, then this no longer becomes a blocking select statement. So what this is going to do is if there's a message ready on one of the channels that are being monitored, then it's going to execute that code path. If not, it will execute the default block. So this is useful if you want to have a non-blocking select statement, then you need to have that default case in there. If you don't have the default case, then the select statement will block forever until a message does come in. Okay, so that's what I have to talk about with channels. Let's go into a summary and review what we've talked about. In this video, we talked about channels and how we can use them to synchronize data transmission between Go routines. We started out by talking about the basics of working with channels. And we learned that we can make our channels using the built-in make function and how that's really the only way that we have available in the Go routine to make a channel. When we do make those channels are strongly typed. So we're going to use the chan keyword to indicate that we wish to create a channel, and then we have to follow that with a data type that the channel is going to be able to send and receive. Now that data type can be anything. It can be a primitive like we see here with an integer, it can be a struct, it can be an interface, but it does have to be strongly typed. We can send a message into the channel using this arrow syntax, and the position of the arrow kind of indicates the direction that the data is going to flow. So in this case, we list the channel, we have the arrow, and then the value that we wish to send into the channel. So notice that the arrow is pointing into the channel. But when we want to receive messages from the channel, then the arrow is leading out of the channel. And so we're going to use the same arrow syntax, but the channel is going to be added after the arrow instead of before. And we can have multiple senders and receivers. As a matter of fact, it's very common for one channel to be distributed among multiple Goroutines, and that way you can have multiple data generators that are sending messages into the channel, as well as multiple data receivers, and that allows you to balance the performance between senders and receivers. So if you can generate data 10 times as fast as you can process it, then you can create 10 times as many receivers, and that way you can balance the workload out between senders and receivers. We then talked about how to restrict data flow. By default, channels are bidirectional constructs, so you can send and receive data into a channel. Now, very often what we want, though, is our Goroutines to be designed to handle channel data only in one direction. So we saw that we can do that by passing in the channel, but then on the receiving side, so for example in the argument list of the function, we can actually specify the direction that we can work with by, again, adding that arrow, and we either add it before or after the chan keyword, depending on what kind of channel that we want to make. We can make a send-only channel by putting the arrow after the chan keyword, and we can make a receive-only channel by adding the arrow before it. We then talked about buffered channels, and how buffered channels contain internal data stores that allow us to get around this limitation of channels. That by default, a channel will block the sender side until a receiver is available, and the receiver side will be blocked until a message is available to come out of the channel. So you can actually block a Goroutine on the sending side or the receiving side of the channel. So if there's no position available in the channel to add the message, then the sending side will be blocked until a space does become available, and if there's no message in the channel, then the receiving side is going to be blocked until a message becomes available for it to work with. So in order to decouple that, we can add an integer as a second argument to the make function, and that's going to allow the channel to have an internal buffer to decouple your senders and receivers, just in case there are situations where data is generated faster than it's received. So just like it says here, we want to use buffered channels when sending and receiving have asymmetric loading. So if we can generate messages faster than we can receive them, then a lot of times a buffered channel is a really good way to go. We then moved on to talk about for range loops, and specifically how to work with them with channels. And we learned that they basically work the same way, but there are a couple of subtle differences. The first thing is, the first parameter that you're going to receive from the for range loop when working with channels is the value itself, not the index like we saw when we were using for range loops over arrays, slices, and maps. And we saw how we could use for range loops to monitor a channel and process messages as they arrive. So the for range loop is just going to keep pulling messages as they come in off the channel, and it'll process them as they come. Then when the channel gets closed, the for range loop is going to detect that, and it will go ahead and exit the loop. And finally, we talked about select statements, and how they work kind of like switch statements, but they work only in the context of channels, and how they allow a Goroutine to monitor several channels at the same time. Now, if they block if all channels are blocked, so if there's no messages available on any channel, then the select statement will block by default, and then when a message comes in, it will go ahead and process that on the proper case. If multiple channels receive a value simultaneously, then the behavior is actually undefined. So because of the highly parallel nature of many Go applications, you can get into situations where messages arrive on two channels at virtually the same time. So one of those cases will get the nod from the select block, but you can't be sure of which one's going to get it. So there is no rule like in switch blocks where the first one that matches is going to get it. It could be anyone. So the ordering of the cases in your select statements really doesn't matter from the standpoint of how those conflicts are going to get resolved. Now, if you do want a non-blocking select statement, remember that you can add that default case in there. So if there are no messages on any of the monitored channels, then the default case will go ahead and fire, and so the select statement will process and execution of the Goroutine will continue from there. Okay, so that wraps up what I have to talk about with channels, and really it brings us to the end of the discussion that I have for this Introduction to Go series. For now, this is Mike Vansickle wishing you luck in all of your Gopher endeavors. Take care.